For as long as humanity has looked to the stars, we've questioned our place in the cosmos. We've solved many puzzles, but still countless mysteries remain, hidden in the far reaches of our solar system and beyond, in the mind-bending realms of distant galaxies. Today, we embark on a journey through the unknown, uncovering some of the most fascinating facts about the universe. Take the Sun, for example, an awe-inspiring star at the center of our solar system. Its sheer size is almost incomprehensible. Imagine this: around 1,300,000 Earths could comfortably fit inside the Sun. That mind-boggling number puts into perspective the colossal scale of our nearest star. With a diameter of approximately 1,400,000 kilometers, the Sun is about 109 times wider than our planet. But it's not just about size. Volume matters too. The Sun's volume is roughly 1,300,000 times that of Earth. This makes its size even more staggering when you think about the space it occupies. It highlights not only the magnificence of the Sun, but also its vital role in supporting life on Earth. Without its warmth and light, our planet would be a frozen, inhospitable wasteland. Understanding the size of the Sun helps us grasp the sheer vastness of our solar system. It's a constant reminder of the intricate dance of celestial bodies that define our existence. The Sun is the backbone of the solar system, its gravitational pull holding the planets in their orbits. Without this delicate balance, life on Earth could not exist as we know it. Now, picture yourself standing on Jupiter. But wait, you can't. Jupiter is a gas giant, primarily composed of hydrogen and helium, and it doesn't have a solid surface. If you were to attempt a descent into Jupiter's thick atmosphere, you'd find yourself swallowed by swirling clouds of gas, facing crushing pressure long before you could even hope to reach a solid ground. As you ventured deeper into Jupiter's turbulent atmosphere, the conditions would grow increasingly hostile. The pressure would skyrocket, and temperatures would soar well above several hundred degrees Celsius. Any human or spacecraft would be obliterated long before they could get close to any solid ground. The planet's intense gravitational pull adds another layer of danger. Jupiter's gravity is more than twice that of Earth, making movement incredibly difficult, if not completely impossible. So, while Jupiter may be magnificent from a distance, it's an uninhabitable world, offering no hope for any would-be explorers who dream of setting foot on its surface. This is just a glimpse into the vast and mysterious universe around us, a universe full of wonders and dangers alike. As we explore, we continue to unlock its secrets, revealing just how much we still have to learn. Furthermore, Jupiter is home to some of the most ferocious storms in our solar system, including the legendary Great Red Spot, an enormous storm that has been raging for centuries. This storm is so massive that it could easily fit Earth inside it. The winds within these storms reach unimaginable speeds, creating an atmosphere that is both turbulent and chaotic. Even if one were somehow able to survive the crushing pressure and extreme temperatures, the violent weather would still pose a deadly threat. Standing on Jupiter, however, is beyond the realm of possibility. With its gaseous composition, extreme atmospheric conditions, and powerful gravity, the planet serves as a stark reminder of the diverse and often inhospitable environments that exist within our solar system. Saturn, on the other hand, is a spectacle in its own right. Its rings are perhaps the most striking and visually stunning feature of any planet in the solar system. The sheer visibility of these rings is a product of several unique factors that make Saturn stand out among the gas giants. Unlike Jupiter, Neptune, and Uranus, all of which have rings, Saturn's rings are far larger, more intricate, and composed of a wide variety of materials. The rings are primarily made up of ice particles, interspersed with smaller amounts of rock and dust. This icy composition allows them to reflect sunlight in such a way that they create a dazzling spectacle. The ice particles within Saturn's rings vary significantly in size, ranging from tiny grains to massive chunks, several meters across. This variation gives the rings a texture and brightness that makes them visible from Earth, even through small telescopes. Scientists believe the formation of Saturn's rings may be linked to the remnants of moons that were shattered by the planet's powerful gravitational forces, or material that never came together to form a moon in the first place. In cosmic terms, Saturn's rings could be relatively young, having possibly formed within the last few 100 million years. Over time, their evolution has been shaped by gravitational interactions with Saturn's many moons, which can either push material outward or allow it to spiral inward. While other gas giants possess rings, they are much fainter and harder to observe compared to Saturn's. The dynamic relationship between Saturn's rings, its moons, and the planet's magnetic field enhances the complexity and beauty of this iconic feature. Each of these elements contributes to the reason why Saturn stands out, offering us a breathtaking view of rings that tell a fascinating story of cosmic interaction and dynamics. As for Venus, a day on this planet, defined as one complete rotation on its axis, lasts approximately 243 Earth days. This is notably longer than a year on Venus, which takes just 225 Earth days to complete one full orbit around the Sun. This means that a day on Venus is longer than a year, which adds an intriguing layer of complexity to our understanding of this neighboring world. The unusual length of a day on Venus can be attributed to its slow and retrograde rotation. Unlike most planets in the solar system, including Earth, Venus rotates in the opposite direction, spinning from east to west. As a result, the Sun rises in the west and sets in the east, a phenomenon that is in stark contrast to what we experience here on Earth. Additionally, the tilt of Venus's rotational axis is a mere 3 degrees. This slight tilt means the planet doesn't experience significant seasonal changes like Earth does. The combination of this minimal tilt and its slow rotation leads to extended periods of daylight and darkness, with one side of the planet locked in eternal sunlight while the other is shrouded in darkness. Despite the long days, Venus is shrouded in an incredibly thick atmosphere, composed primarily of carbon dioxide, which creates an extraordinarily potent greenhouse effect. This greenhouse effect raises Venus's surface temperatures to levels that far exceed those on Earth, making it the hottest planet in our solar system. The slow retrograde rotation of Venus contributes to its elongated days, while its minimal axial tilt plays a crucial role in shaping its unique climate. These combined characteristics make Venus a fascinating object of study in planetary science, offering a striking example of how planetary behaviors can vary dramatically in our cosmic neighborhood. On another world, the colossal Olympus Mons on Mars stands as the largest known volcano in the solar system, reaching an astounding height of around 22 kilometers, nearly 3 times the height of Mount Everest. The immense shield of Olympus Mons spans roughly 600 kilometers in diameter, making it wider than the entire state of Arizona. This immense size is the result of volcanic activity that has been ongoing for billions of years on Mars. Olympus Mons is classified as a shield volcano, which is formed by lava with low viscosity that flows over vast distances. Unlike Earth, where tectonic plates can interfere with volcanic growth, Mars has a relatively static crust. This lack of tectonic plate movement allows eruptions at Olympus Mons to continue uninterrupted for long periods, contributing to the massive size of the volcano. Over time, repeated lava flows have built up the gentle slopes and expansive area that we see today. One of the most captivating features of Olympus Mons is its caldera, a vast depression at the summit created by the collapse of the volcano after massive eruptions. This caldera spans about 80 kilometers in width and contains several overlapping craters, which indicate multiple phases of volcanic activity. The presence of these features offers valuable insights into the dynamic volcanic processes on Mars, providing a window into the planet's geological past. Studying Olympus Mons not only deepens our understanding of Martian geology, but also invites comparisons with the volcanoes here on Earth. This gigantic volcano stands as a monument to Mars's rich geological history and highlights the extraordinary phenomena that can emerge in our solar system when volcanic activity is allowed to unfold without interruption. Turning our gaze toward the moon, the prevailing theory of its formation is the giant impact hypothesis. This theory suggests that around 4.5 billion years ago, shortly after Earth formed, a Mars-sized body, often referred to as Theia, collided with the young Earth. The impact was so cataclysmic that it ejected a vast amount of debris into space. Over time, this material coalesced under its own gravity, eventually forming the moon we see today. The moon holds immense significance for life on Earth in several ways. First and foremost, its gravitational pull plays a crucial role in stabilizing Earth's axial tilt. This tilt is responsible for the planet's climate and the changing seasons. Without the moon's stabilizing influence, Earth could experience much more extreme variations in climate, which would make life as we know it far more challenging to sustain. Additionally, the moon's gravitational forces drive the ocean tides, creating regular rhythmic movements of water that are vital for coastal ecosystems. Tides play a crucial role in distributing nutrients throughout the oceans, fostering dynamic environments that support diverse marine life. These tidal patterns also have profound effects on terrestrial weather and climate systems, further connecting Earth's land and ocean systems in an intricate, harmonious balance. The moon has long stood as a pivotal reference point for humanity, guiding us through history in ways both practical and inspirational. Its phases, predictable and steady, have played a crucial role in shaping agricultural cycles, navigating the open seas, and keeping time itself. Yet, beyond its utility, the moon has sparked a profound curiosity, inspiring countless cultural tales and fueling scientific pursuits. The moon's very formation, resulting from a cataclysmic impact, has had far-reaching consequences, influencing Earth's climate stability and sustaining life in ways we are still only beginning to understand. Indeed, the moon's impact on life on Earth is irreplaceable. It affects everything from the stability of our climate to the rhythms of our ecosystems. And as we look outward, its significance reaches even further, touching our explorations beyond the Earth. The moon's influence continues to echo not just in the natural world, but in the realm of human culture and the broader story of exploration. Meanwhile, our solar system harbors some of the most extreme environments we can imagine. Temperature differences between planets and moons span unimaginable extremes, from searing heat to freezing cold. For example, Venus, the scorching jewel of the inner solar system, reaches surface temperatures around 460 degrees Celsius, hot enough to melt lead. This blistering heat comes from a runaway greenhouse effect, where dense clouds of carbon dioxide trap heat, making Venus even hotter than Mercury, despite being further from the sun. On the other end of the spectrum, we encounter the coldest place we know, Triton, Neptune's largest moon. With surface temperatures averaging around 973 degrees Celsius, Triton's icy expanse paints a picture of the harshest conditions possible. Its thin atmosphere and vast distance from the sun make this frozen world even more extreme. Here, gases like nitrogen freeze directly onto the surface, creating an alien, ice-covered landscape. But the extremes don't end there. Pluto, once classified as the 9th planet in our solar system, experiences temperatures so low that its surface can plummet to -78 degrees Celsius. Though its atmosphere is mainly nitrogen, the thin air allows nitrogen to freeze onto Pluto's surface, forming massive ice plains. This frozen dwarf planet's harsh environment raises questions about life in such conditions. Whether or not Pluto should still be considered a planet has been a subject of much debate. In 2006, the International Astronomical Union redefined what constitutes a planet, and Pluto no longer made the cut. To qualify as a planet, an object must meet 3 criteria. It must orbit the sun, it must be spherical, and it must have cleared its orbital zone of other debris. While Pluto checks the first 2 boxes, it does not meet the third. Its orbit is shared with other objects in the Kyper Belt, a region beyond Neptune filled with icy bodies and dwarf planets. As a result, Pluto was reclassified as a dwarf planet, sparking emotional debates across the scientific community and the general public. Many still hold on to the idea of Pluto as the 9th planet, a symbol of a time when our understanding of the cosmos seemed simpler. This reclassification, though controversial, highlights how science evolves. As our knowledge deepens, so too do our definitions and classifications of celestial bodies. Pluto may no longer be considered a planet, but it remains an object of intense study, and its new status has opened new pathways for exploring other distant objects in our solar system. Among the most fascinating of these objects is Europa, one of Jupiter's largest moons. With a surface so smooth and icy that it gleams like a frozen mirror, Europa conceals a hidden secret, an ocean of liquid water lying beneath its icy shell. This vast ocean may harbor the conditions necessary for life, prompting scientists to consider Europa as one of the most promising locations to search for extraterrestrial organisms within our solar system. As we continue to explore and uncover the mysteries of the solar system, we are constantly reminded of the diversity of worlds that exist beyond our own. Each discovery, whether of heat or cold, water or ice, brings us one step closer to understanding the vastness of space, and perhaps the potential for life in places we never thought to look. In the vast expanse of our solar system, there are moons that not only captivate our imaginations, but also offer crucial clues about the dynamics of distant celestial bodies. Take, for example, the enigmatic surface of Enceladus, Saturn's sixth largest moon. Its icy shell is far from ordinary. Beneath the frozen surface, geological activity is still very much alive. Features that resemble drifting ice plates suggest a dynamic, ever-changing environment, one that invites further exploration. Enceladus stands out for its spectacular geysers, plumes of water vapor and ice particles shooting up from the moon's south polar region. These eruptions, scientists believe, have their origin in a subsurface ocean, a liquid water reservoir hidden deep beneath the icy crust. This is strikingly similar to the subsurface ocean suspected on Jupiter's moon Europa, fueling the ongoing debate about the potential for life beyond Earth. But what makes Enceladus even more remarkable is the discovery that these plumes contain organic compounds, molecules considered essential for life. As these geysers continue to erupt, they feed Saturn's stunning E-ring, a feature that contributes to the planet's breathtaking appearance. Enceladus, thus, isn't just important for understanding Saturn. It is an essential puzzle piece in the search for life in the cosmos. Now, moving outward to Neptune, we encounter yet another fascinating moon, Triton. Neptune's largest moon is unique for several reasons, the most notable being its retrograde orbit. Unlike most moons in our solar system, which move in the same direction as their planet's rotation, Triton travels in the opposite direction. This strange orbit suggests that Triton may not have formed in Neptune's gravitational well, but was instead captured by it, likely in the distant past. Its icy surface is also a spectacle to behold, with geysers spewing nitrogen gas into space. The nitrogen eruptions are strikingly similar to those observed on Enceladus, furthering the intrigue surrounding Triton as a dynamic and potentially habitable body. Triton's combination of retrograde orbit and active surface makes it an essential subject of study for those looking to understand the more unpredictable, fascinating aspects of our solar system. These moons, Enceladus, Triton, and others, are just a few examples of the incredible diversity of natural satellites that populate the solar system. Their unique features highlight the complex interactions between celestial bodies and provide us with glimpses into the conditions that could support life, even in the farthest reaches of space. As scientists continue to unravel the mysteries of these moons, they deepen our appreciation of the universe and the potential for life beyond Earth. Beyond the planets themselves, another region of our solar system offers a treasure trove of secrets, the Kyper Belt. Located beyond Neptune, the Kyper Belt is home to a staggering array of objects, many of which are still only faintly understood. Estimates suggest that there could be as many as 100,000 objects larger than 100 kilometers across within this vast region. When considering smaller objects, the number grows into the millions. These icy bodies include dwarf planets, comets, and other celestial objects primarily composed of frozen gases, rock, and dust, remnants from the early solar system. Among the more well-known Kyper Belt inhabitants are Pluto, Haumea, and Makemake. Each one offers valuable insights into the formation and evolution of our solar system. However, it's the multitude of smaller, lesser-known objects that truly make the Kyper Belt a fascinating area for study. The difficulty in cataloging these objects stems from their great distance from the Sun, which makes them faint and elusive to telescopes. But as technology improves and observational methods evolve, astronomers are discovering new objects at a rapid pace, steadily refining our knowledge of the region. The study of the Kyper Belt is more than just an exercise in cataloging distant bodies. Many of the objects in this region are thought to be ancient relics from the time when our solar system was forming, and by studying them, we gain a better understanding of the processes that shape the entire solar system. The diversity of objects found here provides a window into the conditions and materials present during that crucial period. making the Kyper Belt a focal point for both observational and theoretical research. As we continue to explore this distant region, our understanding of the solar system's architecture deepens, shedding light on the forces that shaped the world we live in. And then, in the farthest reaches of the universe, another extraordinary event occurs: the collision of two neutron stars. These incredibly dense remnants of stellar explosions, each more massive than the Sun, but only about 20 kilometers in diameter, spiral toward each other with a force so intense that it sends ripples through space-time itself. These ripples, known as gravitational waves, are detectable by observatories like LIGO, providing us with a way to study these violent cosmic events in real time. As the neutron stars draw closer, their immense gravitational forces distort space-time, intensifying with every passing moment. The inevitable merger leads to a cataclysmic explosion known as a kilonova, which produces a burst of energy powerful enough to outshine entire galaxies. The aftermath of the merger creates an accretion disk, a swirling mass of neutron-rich material that becomes incredibly hot. From this disk, intense gamma-ray bursts are emitted, short-lived but incredibly powerful flashes of radiation that provide scientists with unprecedented insights into the behavior of the most extreme objects in the universe. These neutron star collisions, though rare, are among the most energetic events known to humanity, offering clues not only about the fundamental nature of matter, but also about the behavior of the universe at its most extreme. As we continue to observe these cosmic fireworks, we gain deeper insights into the origins of the elements that make up the world around us, furthering our understanding of the universe's most mysterious and awe-inspiring phenomena. Neutron star mergers are cosmic events of immense significance, shaping the universe in more ways than one could ever imagine. When two neutron stars collide, they don't just produce a spectacular light show, they also create heavy elements like gold and platinum. This phenomenon occurs through a process known as rapid neutron capture, or the R-process nuclear synthesis. The collision's aftermath helps explain the origins of some of the heaviest elements in the universe. In fact, scientists believe that much of the gold, platinum, and other such elements on Earth may have been born in the heart of these violent cosmic collisions. The violent merging of neutron stars, while often leading to awe-inspiring cosmic displays, serves a far more profound purpose. It aids in our understanding of the fundamental processes of the universe. By observing these events, astronomers gain insights into the nature of gravity, the properties of neutron stars, and the formation of heavy elements. In doing so, they enrich our understanding of the cosmos, opening windows into some of its most mysterious processes. But neutron star collisions are not the only phenomenon helping us unravel the universe's secrets. To measure the vast distances between stars, astronomers rely on a variety of methods, each bringing its own set of tools and techniques. Among the most traditional and effective is parallax, which takes advantage of the apparent shift in a nearby star's position against the backdrop of more distant stars. This shift, observed as Earth moves through its orbit around the Sun, provides a means to calculate the distance to nearby stars. By measuring the angle of this apparent motion over a 6-month period, astronomers can apply simple trigonometry to determine the distance to these celestial objects. Parallax is particularly useful for stars that lie within a few hundred light-years from Earth. For stars located far beyond the reach of parallax, astronomers turn to standard candles, objects with known luminosity. Cepheid variable stars are one of the most reliable examples. These stars' brightness fluctuates in a regular pattern, providing a predictable gauge of their luminosity. By comparing the observed brightness of a Cepheid star to its known luminosity, astronomers can calculate its distance, even if the star resides in a far-off galaxy. This technique helps map the universe with remarkable accuracy. Another critical tool in an astronomer's arsenal is the study of redshift, which proves invaluable when measuring the distances to galaxies or groups of stars. When light from an object moves away from Earth, its wavelength stretches, shifting the light toward the red end of the spectrum. By measuring this redshift, astronomers can determine the velocity at which the object is receding from us. Using Hubble's law, they can then infer its distance. This method is essential for understanding the expansion of the universe and for gauging distances on a grand cosmological scale. Each of these techniques, parallax, standard candles, and redshift, provides essential data to map the vast cosmic landscape. Together, they offer a multifaceted approach to measuring distances, granting astronomers an intricate understanding of the structure and scale of our universe. At the heart of some of the most interesting phenomena in the universe lies the pulsar. A pulsar is a highly magnetized, rotating neutron star that emits beams of electromagnetic radiation from its magnetic poles. These fascinating objects are the remnants of massive stars that have undergone supernova explosions, collapsing under their own gravity into ultra-dense spheres made mostly of neutrons. A pulsar can have a mass greater than that of the Sun, but it may only span about 20 kilometers in diameter. The result is an environment dominated by incredibly strong gravitational and magnetic fields. The regular pulsation of these objects occurs because the magnetic axis of a pulsar is not perfectly aligned with its axis of rotation. As the pulsar rotates, its radiation beams sweep across the universe like a lighthouse beacon. If Earth lies in the path of these beams, we observe them as periodic pulses of light, or radio waves. The timing of these pulses can be extraordinarily precise. Some pulsars spin hundreds of times per second, emitting pulses at remarkably consistent intervals. What makes pulsars especially fascinating to astronomers is their exceptional accuracy in timing. The regularity of these pulses provides a natural cosmic clock, making pulsars invaluable tools for studying gravitational waves and testing the principles of general relativity. Their precision offers us a glimpse into the fabric of spacetime itself, allowing us to probe the universe in ways previously thought impossible. Moreover, pulsars play a crucial role in advancing our understanding of the universe. These cosmic phenomena provide invaluable data on extreme states of matter and nuclear physics, offering insights into conditions that are impossible to replicate here on Earth. As cosmic beacons, pulsars not only illuminate the life cycles of stars, but also unlock mysteries of fundamental physics and the nature of the universe itself. The pulses they emit travel across vast distances, deepening our knowledge of the cosmos with each detection. A star's mass is the driving force behind its life cycle and ultimate fate. Stars are born from clouds of gas and dust, and it's the mass of the collapsing material that determines the star's lifespan and what happens once it exhausts its nuclear fuel. For massive stars, those more than 8 times the mass of our Sun, the journey is rapid and dramatic. These stars burn through their hydrogen fuel much faster, leading to a swift progression through various stages of stellar evolution. Once hydrogen is depleted, heavier elements such as helium, carbon, and iron begin to fuse in the core. However, when iron builds up, fusion halts, and the star can no longer produce the energy needed to counterbalance gravity. The core collapses, triggering a supernova explosion. This cataclysmic event can leave behind a neutron star, or, if the original mass is great enough, even collapse into a black hole. In contrast, stars with masses similar to or less than the Sun undergo a more gradual process. After depleting hydrogen in their cores, they expand into red giants. Eventually, their outer layers are shed, forming a planetary nebula, while the remaining core cools into a white dwarf, fading over billions of years. The differences in the life cycles of massive and less massive stars illustrate the critical role mass plays in determining a star's evolution. It shapes not only the duration and intensity of a star's life, but also the elements produced and released into the universe. This process of nucleosynthesis is vital for enriching galaxies with the chemical elements necessary to form new stars, planets, and life itself. The title of the largest known star in the universe often goes to UY Scuti, a red supergiant located in the constellation Scutum. This gargantuan star is estimated to be about 1,700 times the radius of the Sun. If placed at the center of our solar system, its outer edges would extend beyond the orbit of Saturn, dwarfing the planets that orbit our star. Red supergiants like UY Scuti represent the final stage in a star's life cycle. These stars expand and cool significantly once they burn through their nuclear fuel, growing to immense sizes before ending in dramatic events such as supernova explosions. The sheer size of UY Scuti underscores the vast diversity of star sizes in the universe. While our Sun, a medium-sized star, measures about 1,400,000 kilometers in diameter, UY Scuti's enormous size serves as a humbling reminder of the immense scale of the cosmos. To put it in perspective, if Earth were the size of a grain of sand, our Sun would be the size of a beach ball, and UY Scuti would be closer in size to a large balloon. The study of these massive stars, like UY Scuti, not only captivates astronomers, but also provides critical insights into the processes of star formation and evolution. As we continue to explore the universe, new discoveries may even reveal stars that rival or surpass UY Scuti, highlighting that the cosmos is full of surprises waiting to be uncovered. Brown dwarfs are another intriguing class of astronomical objects that occupy a unique position between the largest planets and the smallest stars. These so-called failed stars are not massive enough to sustain the nuclear fusion of hydrogen in their cores, the hallmark of true stars. With masses between 13 and 80 times that of Jupiter, brown dwarfs are larger than gas giants but lack the mass to ignite stellar fusion. Their formation follows a similar process to that of stars, emerging from clouds of gas and dust that collapse under gravity. However, once a brown dwarf forms, it embarks on a peculiar journey unlike any other celestial body. These objects never reach the necessary internal pressure and temperature required to ignite hydrogen fusion, which is the hallmark of a full-fledged star. Instead, brown dwarfs shine faintly, fueled by the burning of deuterium and lithium, both isotopes of hydrogen. This limited source of energy keeps them glowing for only a brief period before they gradually fade into obscurity. The unique nature of brown dwarfs challenges traditional astronomical classification. They occupy a space somewhere between stars and planets. Their temperatures, ranging from about 1,000 to 2,000 degrees Celsius, are far cooler than most stars, yet still warmer than the cold, dark planets that populate our solar system. This intermediate temperature allows them to emit infrared radiation, making them detectable through specialized telescopes designed to observe in the infrared spectrum. The discovery of brown dwarfs has sparked a fascinating debate among astronomers. Are they stars, or are they closer to planets? Their existence pushes the boundaries of how we define celestial bodies. The study of these enigmatic objects has not only expanded our understanding of stellar formation, but also shed light on the incredible variety of worlds that populate the universe. Brown dwarfs invite us to reconsider our perceptions of how stars and planets come to be as they straddle the fine line between the two, offering new insights into the processes of star formation and the evolution of our galaxy. In the wider cosmos, binary star systems offer another intriguing avenue of exploration. These systems consist of two stars that are gravitationally bound to each other, orbiting a common center of mass. The dynamics of these stellar pairings lead to a range of fascinating phenomena, depending on the mass, size, and evolutionary stages of the stars involved. Over time, the interactions between these stars can significantly influence their evolution and behavior. There are two main types of binary star systems: close binaries and wide binaries. In close binaries, the two stars are in very close proximity to one another. This closeness can result in dramatic interactions, such as mass transfer from one star to the other. These transfers often lead to spectacular cosmic events like novas, in which the material accumulated on the surface of the smaller star ignites in a sudden burst of energy. On the other hand, wide binaries are stars that are much farther apart. Though their interactions are less dramatic, the gravitational pull between them still influences their paths over long periods, affecting their trajectories and evolution in subtle ways. Binary star systems are surprisingly common. Estimates suggest that around half of all stars in our galaxy exist in some form of binary system. This widespread prevalence highlights the significance of star interactions in the broader context of stellar evolution. Understanding these systems is essential for comprehending how stars form, evolve, and interact over time. The dynamics of binary stars provide crucial insights into stellar masses, distances, and compositions, information that would be nearly impossible to obtain from single stars alone. Beyond simply illuminating the nature of stars, binary systems are also pivotal in the creation of some of the most dramatic astronomical phenomena, such as supernovae. In some binary systems, when one star exhausts its nuclear fuel, it can explode, a process that may have a profound impact on the remaining star. These explosions can trigger further cosmic events, ultimately shaping the evolution of the system and the surrounding space. A particularly intense phenomenon that can occur within binary systems is the hypernova, an extraordinarily powerful explosion resulting from the collapse of a star much more massive than our Sun. Hypernovae are the final active stars that are greater than about 30 solar masses in size. These cataclysmic events release energy that is up to 100 times more intense than a typical supernova, making them some of the most energetic events in the universe. Though both supernovae and hypernovae mark the violent ends of massive stars, hypernovae are far more dramatic, pushing the limits of energy release and influencing the surrounding cosmic environment in ways that challenge our understanding of stellar death. In the grand tapestry of the universe, these phenomena, brown dwarfs, binary stars, and hypernovae, remind us of the boundless variety of objects and events that shape the cosmos. Each one, from the faint glow of a brown dwarf to the explosive brilliance of a hypernova, offers unique insights into the forces at play within our galaxy and beyond. As astronomers continue to observe and study these mysteries, we move closer to unraveling the complex and ever-evolving story of the universe. The primary distinction between a hypernova and a supernova is the sheer scale of energy released and the underlying processes that drive each cosmic explosion. Supernovae are generally categorized into two main types. Type 1, which occurs in binary star systems where a white dwarf accumulates matter until it reaches a critical mass, igniting a catastrophic explosion, and Type 2, which results from the core collapse of massive stars. In contrast, hypernovae, particularly those associated with long-duration gamma-ray bursts, represent a far more extreme phenomenon. These events often lead to the formation of a black hole or a neutron star, releasing powerful jets of high-energy gamma radiation that pierce through the surrounding space, further intensifying the explosion. Hypernovae are not only significantly more energetic than supernovae, but also eject vast quantities of material into the cosmos. This ejected material plays a pivotal role in the enrichment of the interstellar medium, dispersing heavy elements created through the star's nuclear fusion processes. As these elements scatter across the universe, they contribute to the formation of new stars and planets, thus fueling the cosmic recycling process that drives the evolution of galaxies. The explosive nature of hypernovae pushes the boundaries of our understanding of stellar evolution and the catastrophic forces shaping the universe. Research into hypernovae continues to unfold, bringing us closer to unlocking the full extent of these monumental events and their far-reaching impact on the cosmos. On a different note, the discovery of exoplanets, planets that orbit stars outside our solar system, has become one of the most thrilling frontiers in modern astronomy. To detect these distant worlds, astronomers utilize a variety of techniques, with two of the most widely employed being the transit method and the radial velocity method. Each of these approaches offers distinct advantages, providing unique insights into the characteristics of exoplanets. The transit method involves monitoring the brightness of distant stars over time. When an exoplanet passes directly between us and its host star, it temporarily blocks a fraction of the star's light, causing a dip in the star's observed brightness. By analyzing these periodic dips, astronomers can infer the presence of an exoplanet. This technique is particularly effective in large-scale surveys, such as NASA's Kepler Space Telescope mission, which has led to the discovery of thousands of exoplanets. Not only does this method reveal the existence of planets, but it also provides valuable information about their size and orbital periods, making it a powerful tool for exoplanet research. In parallel, the radial velocity method, also known as Doppler spectroscopy, is another essential technique for detecting exoplanets. This method detects the subtle wobble of a star caused by the gravitational pull of an orbiting planet. As the planet orbits, it tugs on the star, causing the star to move in a small orbit of its own. This movement alters the star's light spectrum, shifting the light to higher frequencies when the star moves toward us and to lower frequencies when it moves away. By measuring these shifts in the star's spectrum, astronomers can confirm the existence of an exoplanet and estimate its mass and orbital distance. In addition to these methods, astronomers are also exploring direct imaging techniques to capture actual photographs of exoplanets. This approach involves blocking out the light from the parent star to reveal the faint glow of the exoplanet itself. Although challenging due to the vast difference in brightness between stars and their planets, direct imaging has successfully yielded images of several exoplanets, providing a new dimension to our understanding of distant worlds. The continued exploration of hypernovae and exoplanets is reshaping our understanding of the universe, offering extraordinary insights into the processes that govern the birth, evolution, and death of stars, as well as the formation of planetary systems beyond our own. Each discovery brings us one step closer to unraveling the mysteries of the cosmos. The search for exoplanets has not only deepened our understanding of planetary systems beyond our own, but it has also sparked profound questions about the potential existence of life elsewhere in the universe. With each technological advancement, astronomers refine their methods, leading to the discovery of an increasing number of distant worlds, each one unique with distinct characteristics and a potential for habitability. And then there's the Magnetar, an extraordinary type of neutron star that carries one of the most powerful magnetic fields known to science. Magnetars, which are born from the collapse of a massive star in a supernova explosion, form a compact core made almost entirely of densely packed neutrons. Despite their small size, typically only about 20 kilometers in diameter, these neutron stars possess gravitational and magnetic forces so intense that they defy imagination. What truly sets magnetars apart from their neutron star cousins is their magnetic field, which is not just strong, but overwhelmingly powerful. These fields can reach strengths over 1,000 trillion Gauss. For comparison, the magnetic field of an average refrigerator magnet is about 1,000 Gauss. The source of this incredible strength is believed to lie in the rapid rotation of the star following its formation. As a neutron star spins, it can generate magnetic fields, and under the right conditions, these fields can increase exponentially, reaching the extreme levels seen in magnetars. The effects of these magnetic fields are far from trivial. Magnetars can unleash bursts of high-energy radiation, including X-rays and gamma rays, which can lead to extraordinarily energetic phenomena. These bursts are so intense that, for a fleeting moment, they can outshine entire galaxies. Yet, despite their incredible power, they are short-lived. Surrounding a magnetar is a magnetosphere filled with energetic particles, and the dynamic behavior of this magnetosphere produces powerful emissions. These emissions create the pulsar-like patterns of radiation that define magnetars, adding another layer to their enigmatic nature. Magnetars, however, are not merely cosmic curiosities. They are key players in understanding fundamental physics and stellar evolution. Their extreme environments challenge our understanding of magnetism, as well as the behavior of matter under conditions that are nearly impossible to replicate on Earth. As astronomers study magnetars, they unlock secrets about star life cycles, the nature of neutron matter, and the behavior of the universe's most extreme magnetic fields. Meanwhile, the observable universe itself is a vast, seemingly endless expanse. Current estimates suggest there are around 2 trillion galaxies scattered across this immense space. This staggering number, derived from observations conducted by powerful telescopes like the Hubble Space Telescope, highlights the sheer complexity and scale of the cosmos. Each galaxy, whether it be a small dwarf galaxy or a massive spiral or elliptical formation, houses billions or even trillions of stars, planets, nebulae, and countless celestial bodies. The diversity of galaxies, varying in size, shape, and structure, adds richness to the universe's cosmic tapestry. This variety provides astronomers with invaluable information about the processes of cosmic evolution, the formation of galaxies, and the mysterious nature of dark matter and dark energy. Recent studies, using cutting-edge techniques like deep field imaging, which captures light from the faintest and most distant galaxies, have led to surprising revelations. As a result, astronomers continue to refine their estimates, bringing the total number of observable galaxies into the trillions. And as our observational tools improve, Thanks to the launch of the James Webb Space Telescope and other advanced instruments, it's likely that even more galaxies will be discovered, pushing the boundaries of our knowledge further. This ongoing exploration reshapes our understanding of the universe, continually opening new doors to probe fundamental questions about the very nature of galaxies and their role in the unfolding cosmic narrative. The largest known structure in the universe, the Hercules Corona Borealis Great Wall, is an awe-inspiring cosmic entity that stretches an unimaginable 10 billion light-years across. This vast galactic supercluster complex was uncovered through detailed analysis of gamma-ray bursts and galaxy surveys. These observations revealed an intricate network of galaxies and galaxy clusters interwoven across an expansive region of space. Galactic structures like the Hercules Corona Borealis Great Wall are formed by the powerful gravitational pull between matter in the universe. As galaxies and galaxy clusters are drawn toward each other, they form massive, interconnected structures that span vast distances. The Hercules Corona Borealis Great Wall contains several galaxy clusters, linked together by filaments of dark matter and gas, the fundamental building blocks of the universe's large-scale structure. The sheer size of this colossal structure challenges our understanding of cosmic dimensions. The observable universe itself is about 8 billion years old, and when we consider the vast distances that such formations span, it reveals just how immense and intricate the cosmos truly is. The interactions and formations of galaxies on this scale offer significant insights into cosmic evolution, the distribution of matter, and the fundamental forces that govern the universe. As astronomers continue to explore the cosmos with cutting-edge technologies, it's conceivable that even larger structures could be discovered. Each new finding invites us to reflect on the distribution of galaxies and the underlying principles steering the evolution of the universe. The ongoing investigation of these monumental structures deepens our understanding and appreciation of the universe's astonishing vastness and complexity. Galaxies, the building blocks of the universe, form and evolve through an intricate series of processes that unfold over billions of years. Galaxy formation begins shortly after the Big Bang, during the universe's early years, when fluctuations in the density of hydrogen and helium gas caused regions of matter to clump together under gravity. These areas grew denser over time, attracting more gas and dust, which laid the foundation for the formation of stars and galaxies. As these regions continued to collapse under their own gravity, they gave birth to the first stars. These early stars played a crucial role in galaxy formation, producing heavier elements through nuclear fusion. When they reached the end of their life cycles, many of these stars exploded in massive supernova events, scattering newly formed elements into the surrounding space. This process enriched the interstellar medium with metals, which were essential for the creation of subsequent generations of stars and planets. As galaxies began to form, they underwent mergers and interactions with other galaxies. These gravitational encounters can dramatically alter a galaxy's shape, size, and star formation activity. For instance, when two galaxies collide, their gas can be compressed, triggering waves of new star formation. Such mergers were common in the early universe, and they can lead to the formation of larger structures, like elliptical galaxies from smaller spiral galaxies. Over time, galaxies continue to evolve through various processes, including star formation, supernova feedback, and interactions with neighboring galaxies. This ongoing evolution plays a key role in determining a galaxy's shape, as well as the distribution of its stars, gas, and dust. The story of galaxies is dynamic, shaped both by internal processes and external forces, resulting in the rich diversity of galaxy forms observed today, from stunning spirals to massive elliptical shapes. As researchers study these evolutionary processes, they uncover deeper insights into the history of the universe and the complex tapestry of cosmic evolution. A striking example of such cosmic phenomena is the Great Attractor, a massive gravitational anomaly located in the direction of the Centaurus and Hydra constellations. This enigmatic region exerts a powerful gravitational influence over galaxies across vast distances, causing them to move toward it at remarkable speeds. The Great Attractor is part of an even larger structure, the Laniakea supercluster, which is a vast collection of galaxies, including our very own Milky Way, bound together by this immense gravitational pull. In studying these immense cosmic structures, scientists are unveiling new layers of understanding about the universe's evolution, pushing the boundaries of human knowledge and reshaping our perception of the cosmos. The Great Attractor is a mysterious cosmic phenomenon believed to be an immense concentration of mass that includes entire galaxies and galaxy clusters. However, much of this mass is hidden from our view by the dense dust and gas of the Milky Way, making it difficult to study directly. It's estimated that the Great Attractor is home to thousands of galaxies and lies about 100 million light-years away from Earth. Despite its significant presence, the exact nature and composition of this region remain elusive, largely due to the thick cosmic material that obstructs our observations. This massive region exerts a powerful gravitational influence, affecting the motion of nearby galaxies. In the universe, galaxies aren't distributed evenly, and areas with dense concentrations of mass, like the Great Attractor, create gravitational wells that draw nearby galaxies toward them. Several galaxy clusters, such as the Norma and Centaurus clusters, are observed to be moving toward this enigmatic attractor, offering a clear illustration of how large-scale structures shape the movements of galaxies. Understanding the Great Attractor is crucial for unlocking the mysteries of the universe's large-scale structure. It exemplifies the importance of gravitational interactions in the cosmos, showing how galaxies and galaxy clusters are intricately linked within the vast cosmic web. As astronomers continue to investigate, they are uncovering the complex relationships that govern galaxy motions, revealing the forces at play in the expansive theater of space. Measuring the mass of a galaxy, however, is no easy task. It's a fundamental aspect of understanding a galaxy's structure, evolution, and dynamic behavior. One of the main techniques used to estimate a galaxy's mass involves analyzing the motion of its stars and gas. By observing the velocities of these components, astronomers can apply principles from Newtonian physics and gravitational dynamics to make their calculations. When astronomers study a galaxy's stars, they often use spectroscopy to measure their velocities. As stars move, the light they emit shifts due to the Doppler effect, with the wavelengths lengthening if the stars are moving away and shortening if they are moving toward Earth. By detecting these shifts, astronomers can determine the velocity of stars in different parts of the galaxy. From there, they can estimate the galaxy's total mass using the laws of gravitation, which link the speed of orbiting stars to the gravitational pull of the galaxy's mass. For galaxies that are too distant or too large to measure individual star motions, astronomers can look at the motion of entire galaxy clusters. By observing the speeds at which galaxies orbit a common center of mass within the cluster, they can infer the total mass of the cluster, including contributions from both visible matter, like stars and gas, and dark matter. Dark matter, which doesn't emit light and is difficult to detect directly, plays a crucial role in these measurements. Another key technique for measuring galaxy mass involves gravitational lensing. This phenomenon occurs when a massive object, such as a galaxy or a galaxy cluster, bends the light coming from more distant background objects. By studying the degree to which the light is distorted, astronomers can estimate the mass of the foreground galaxy or cluster. The amount of bending is directly related to the mass of the object causing the lensing. Using these various methods, astronomers piece together a more complete picture of a galaxy's mass. This knowledge is vital for understanding the galaxy's formation, its structure, and its behavior in the broader context of the universe. By gathering these mass measurements, scientists are gaining profound insights into how galaxies contribute to cosmic evolution and are slowly uncovering the nature of dark matter that permeates the universe, shaping the cosmos in ways we are only beginning to understand. Galaxy clusters are colossal assemblies of galaxies bound together by gravity, making them the largest known gravitationally bound structures in the universe. These vast collections can house anywhere from a handful of galaxies to thousands, alongside significant amounts of hot gas and dark matter. Serving as the backbone of the universe's large-scale structure, galaxy clusters play an essential role in cosmic evolution. They are not just places where galaxies reside, they are dynamic ecosystems that shape the very fabric of the cosmos. Within these clusters, galaxies interact constantly. The dense environment encourages regular encounters between galaxies, and when they pass close to one another, gravitational forces take charge. These interactions can result in a variety of phenomena, including galaxy mergers, tidal forces, and the stripping of stars and gas. Such processes often trigger bursts of star formation, especially when gas clouds are compressed. Alternatively, these interactions may lead to the creation of larger, more massive galaxies. This phenomenon, known as galactic cannibalism, occurs when larger galaxies absorb their smaller neighbors, steadily growing and altering the structure of the cluster. On a grander scale, galaxy clusters themselves can collide. When this happens, the resulting shock waves compress gas and may lead to heightened star formation within the member galaxies. These collisions often produce complex dynamics, with clusters exchanging members and merging into even larger, more intricate structures. The role of dark matter in these interactions is crucial. While ordinary matter, gas and stars, enter through electromagnetic forces, dark matter's influence is exerted through gravity, leading to fascinating and distinct observational effects. One striking outcome of these interactions is the creation of vast interconnected cosmic filaments. These are webs of dark matter and gas that link galaxies across enormous distances. Observed as filamentary structures stretching across the universe, these cosmic threads weave galaxies together into a grand, interconnected network. This cosmic web is a testament to the forces that govern the universe, and it continues to shape the evolution of both individual galaxies and the galaxy clusters they inhabit. The morphology of galaxies and the distribution of matter across the cosmos are continually influenced by these interactions, revealing a universe in constant motion and transformation. The study of galaxy clusters and their interactions offers astronomers valuable insights into the history and evolution of the universe. As these clusters grow and merge over billions of years, they illustrate the dynamic nature of cosmic evolution, providing a window into the interconnectedness of galaxies and the forces that drive their behavior. At the heart of many large galaxies, including our own Milky Way, reside supermassive black holes, objects whose masses range from millions to billions of times that of our Sun. These black holes, while invisible, exert a profound influence on their host galaxies, shaping various aspects of their structure, dynamics, and evolution. Their gravitational pull is immense, and it plays a central role in shaping the orbits of stars and gas within the galaxy. In particular, this gravitational influence can help regulate the movement and distribution of stars, often leading to the formation of dense stellar clusters around the black hole and impacting the overall shape of the galaxy. In addition to their gravitational effects, supermassive black holes also drive star formation through powerful feedback mechanisms. As matter falls into a black hole, it forms an accretion disk, where friction causes the material to heat up and emit vast amounts of energy, including X-rays and other forms of high-energy radiation. This energy powers fierce winds and outflows that expel gas away from the black hole's center, effectively halting star formation in the region. Without the influx of gas necessary for new stars to form, these feedback processes act as a cosmic thermostat, regulating the growth of the galaxy over time. Through these intricate mechanisms, supermassive black holes not only influence the galaxies they inhabit, but also play a critical role in shaping the overall evolution of the universe. As they continue to interact with their surroundings, they are key players in the complex cosmic dance that has been unfolding for billions of years. Furthermore, the energy output from supermassive black holes can lead to large-scale phenomena that shape the universe in profound ways. One of these phenomena is the active galactic nucleus, AGN, where the black hole actively accretes material. This process can result in powerful jets of particles which extend far beyond the host galaxy. These jets influence the intergalactic medium and even affect the evolution of neighboring galaxies by altering gas flows. This dynamic relationship between supermassive black holes and their host galaxies is one of mutual influence. As galaxies evolve, they likely impact the growth and activity of the black holes, and conversely, the black holes play a critical role in the evolution of their host galaxies. This intricate interplay is fundamental to shaping the characteristics of galaxies and ultimately affects their evolution and the formation of cosmic structures. Understanding these dynamics offers crucial insights into galaxy formation and the life cycle of celestial bodies. One of the most intriguing discoveries in this context is the Fermi bubbles, enormous lobes of high-energy gamma-ray emissions that extend above, and below the plane of our Milky Way galaxy. These structures are thought to represent outflows of hot gas and cosmic rays, possibly generated by the energetic processes surrounding the supermassive black hole at the center of our galaxy, known as Sagittarius A Psi. Each of the Fermi bubbles stretches about 25,000 light-years in height, making them one of the most striking features of the galactic center. Their discovery was made possible through data collected by the Fermi Gamma Ray Space Telescope, launched in 2008, designed to observe cosmic gamma rays across a wide range of energy levels. The telescope detected unexpected gamma ray emissions emanating from the galactic center. These emissions revealed the symmetrical lobes that extend far into surrounding space. Subsequent studies suggested that the Fermi bubbles are filled with high-energy particles and magnetic fields. Several theories have been proposed to explain their formation. One possibility is that they result from past outbursts of the supermassive black hole, while another possibility involves powerful star formation events that accelerate particles to extremely high energies. Additionally, interactions between cosmic rays and the interstellar medium could contribute to the observed emissions. The discovery of the Fermi bubbles has opened new avenues for understanding the dynamics of our galaxy and the processes that govern its evolution. By studying these massive structures, astronomers gain valuable insights into the relationship between supermassive black holes, star formation, and the surrounding environment. The Fermi bubbles serve as a captivating example of how high-energy astrophysics can reveal the complex activities occurring within our galaxy and beyond. Mapping the distribution of dark matter within galaxies is another key focus of astrophysical research. Dark matter constitutes a significant portion of the universe's total mass, yet it does not emit, absorb, or reflect light, making it invisible to conventional telescopes. Nevertheless, astronomers have developed several methods to infer its presence and map its distribution, primarily based on its gravitational effects. One of the primary techniques used to study dark matter is gravitational lensing. This phenomenon occurs when the gravity of a massive object, such as a galaxy or galaxy cluster, bends the light from more distant background objects, like galaxies. By analyzing the amount of distortion in the images of these background galaxies, astronomers can estimate the mass of the foreground object and infer the distribution of dark matter. Strong gravitational lensing, which produces significant distortions and phenomena like Einstein rings, provides particularly detailed insights into the underlying mass distribution. Another important method for studying dark matter involves examining the rotational dynamics of galaxies. By observing the rotation curves of spiral galaxies, tracking the velocities of stars and gas at various distances from the galactic center, astronomers can determine the amount of mass present in the galaxy. According to Newtonian gravity, the rotation speeds should decrease with distance if only visible matter were present. However, many galaxies exhibit flat rotation curves, suggesting that there is much more mass than can be accounted for by visible matter alone. This discrepancy points to the existence of a dark matter halo surrounding the galaxy, extending far beyond its visible boundary. In addition to these observational techniques, astronomers use simulations and computational models to explore how dark matter interacts with normal matter within galaxies. By comparing observed galaxy structures and motions with model predictions that include various distributions of dark matter, scientists can refine their understanding of its properties and spatial distribution. Cosmic simulations of large-scale structure formation play a pivotal role in unveiling the mysteries of dark matter. These simulations utilize the fundamental laws of physics to model how dark matter evolves over time and how it influences the formation of galaxies and clusters. As these simulations unfold, they offer us an increasingly detailed and comprehensive understanding of dark matter's role across the vast expanse of the universe. Through these various approaches, Astronomers are gradually piecing together a clearer picture of dark matter's presence and distribution within galaxies, ultimately leading to a deeper understanding of this elusive and enigmatic component that shapes the very structures we observe today. The cosmic web, often described as the largest scale of the universe's arrangement, is a vast and intricate structure that reveals the fundamental blueprint of the cosmos. Imagine it as a delicate, woven fabric consisting of galaxy clusters, filaments, and voids stretching across the universe. This web-like formation emerges from the gravitational attraction of matter, influencing the distribution of galaxies and providing a framework for their interaction across cosmic distances. At the heart of the cosmic web are massive galaxy clusters that serve as the nodes, surrounded by long, thin filaments made up of dark matter and gas. These filaments thread through space, either linking various clusters to one another. Between them, vast voids emerge, regions where few galaxies are found. This delicate balance of filaments and voids creates a dynamic, ever-changing environment in which galaxies grow and evolve. As they are pulled toward regions of higher density, galaxies interact with one another, merge, and undergo significant transformations. Understanding the cosmic web enhances our insight into how galaxies form and evolve over billions of years. Galaxies do not exist in isolation. Instead, they're part of a vast interconnected network that influences their growth and behavior. The gravitational pull within these filaments funnels gas into galaxies, fueling star formation and impacting their evolutionary paths. This interconnectedness also explains phenomena such as galactic mergers, where galaxies are drawn together, contributing to their growth and altering their shape and composition. Thanks to groundbreaking cosmic surveys and innovative observational techniques, scientists have mapped the cosmic web and studied its properties. Observations suggest that around 80% of the universe's mass is composed of dark matter, making it a significant contributor to the structure of the cosmic web. By unraveling the properties of this vast network, researchers gain invaluable insights into the history and fate of the universe, revealing how everything is intricately bound together in an expansive, interconnected tapestry. Turning to one of the most extreme and fascinating phenomena in astrophysics, the experience of falling into a black hole offers a surreal, otherworldly scenario. As you approach a black hole, you would encounter a bizarre phenomenon known as spaghettification. This occurs due to the immense gravitational field gradient near the black hole. If your feet were closer to the black hole than your head, gravity would exert a far stronger pull on your feet, stretching you into a long, elongated shape resembling spaghetti. This tidal force would relentlessly increase the closer you get, making it impossible to escape the black hole's grip. Crossing the event horizon, the point of no return surrounding a black hole, marks a critical moment in this journey. Once you pass this boundary, escaping becomes impossible, not even for light. According to the principles of general relativity, you would not experience anything particularly unusual upon crossing the event horizon itself. However, to an observer watching from a safe distance, you would appear to freeze at the edge. Meanwhile, you would continue your inward journey, unaware of the ultimate fate that awaits. This creates a captivating paradox between the perspectives of an outside observer and that of the object falling into the black hole. As you venture deeper into the black hole, the environment grows increasingly hostile. Inside, the laws of physics as we know them begin to break down. Theoretically, all the mass of the black hole is concentrated at a singularity, a point of infinite density where current physics fails to provide answers. What happens at this singularity remains one of the greatest mysteries in modern science. Some theories propose that the very fabric of space-time is altered in ways we cannot yet comprehend, and the concept of time itself could behave strangely. Ultimately, falling into a black hole leads to the destruction of anything that ventures too close, as the forces at play are unlike anything we experience on Earth. This exploration not only deepens our understanding of gravity and space-time, but also raises profound questions about the fundamental nature of the universe and the limits of human knowledge. The study of black holes remains one of the most profound and perplexing challenges in modern physics, compelling scientists to reconcile conflicting theories and delve deeper into the mysteries of the universe. These cosmic behemoths, particularly supermassive black holes, are scattered across the centers of most, if not all, galaxies. Yet, the exact mechanisms of their formation continue to intrigue researchers, as various theories offer differing views on how these colossal entities come into being. One leading theory suggests that supermassive black holes originated from the collapse of vast gas clouds in the early universe, just a few 100 million years after the Big Bang. In these early stages, immense quantities of gas drawn by gravity collapsed into dense regions, potentially serving as the seeds from which black holes would eventually grow. As these nascent black holes took shape, their growth accelerated at an astonishing rate. By accreting surrounding gas and merging with other black holes, they amassed more mass, expanding into the giants we observe today. This process is powered by the tremendous gravitational pull of the black hole, drawing in matter from the surrounding space. The influx of material doesn't just fuel growth, it also unleashes vast amounts of energy, which in turn can lead to the creation of active galactic nuclei, some of the brightest and most energetic objects in the universe, emitting radiation across the electromagnetic spectrum. In addition to accretion, another critical factor in the formation and growth of supermassive black holes is galaxy mergers. When galaxies collide, their central black holes can be drawn together by gravity, eventually merging to form an even more massive black hole. The dynamics of these galactic collisions funnel gas and stars toward the center of the newly merged galaxy, accelerating the black hole's growth. The resulting increase in mass solidifies the black hole's pivotal role at the heart of its galaxy, affecting the evolution of its surrounding environment. Recent research also points to the intriguing possibility of primordial black holes, hypothetical objects that could have formed in the very early universe due to fluctuations in density, even before stars and galaxies came into existence. If primordial black holes are real, they might offer an alternative explanation for the masses observed in today's supermassive black holes, further complicating the puzzle of their formation. As researchers continue to study the evolution of galaxies and black holes, the question of how these enigmatic structures emerge and influence their cosmic surroundings remains a captivating frontier in astrophysics. Each new discovery brings us closer to understanding the fundamental forces at play in the universe and the role black holes have in shaping the cosmos. One of the most revolutionary ideas in this field emerged in 1974 when physicist Stephen Hawking proposed a concept that would forever alter our understanding of black holes. This groundbreaking theory, known as Hawking radiation, arises from the intersection of quantum mechanics and general relativity. According to Hawking, black holes are not the pitch-black voids they appear to be. Instead, they emit radiation due to quantum fluctuations occurring just outside the event horizon. In the quantum vacuum of space, pairs of particles and antiparticles continuously form and annihilate. However, when this phenomenon occurs near the event horizon of a black hole, the situation takes an unusual turn. One particle from the pair may fall into the black hole while the other escapes into space. The escaping particle is what we detect as Hawking radiation. For an external observer, this radiation appears as thermal energy, leading to the conclusion that black holes slowly lose mass as they emit Hawking radiation over incredibly long time scales. Over time, this process could even result in the evaporation of the black hole, ultimately reducing it to nothing. This idea not only challenges our understanding of black holes, but also raises profound questions about the nature of information in the universe. If black holes eventually vanish due to Hawking radiation, what happens to the information contained within the matter that falls into them? This dilemma, known as the black hole information paradox, has sparked intense debate and remains one of the most perplexing issues in theoretical physics. The paradox poses a direct challenge to the foundations of quantum mechanics and has inspired a multitude of hypotheses about the fundamental principles governing the universe. Hawking radiation has far-reaching implications for several core areas of physics, including thermodynamics, quantum theory, and cosmology. Its study continues to push the boundaries of our understanding, offering new avenues for exploring the complex interplay between these fundamental forces. As researchers work to unravel the mysteries of black holes, they are also tackling some of the most profound questions about the nature of reality itself. The story of black holes is far from over, and with every new discovery, we come closer to understanding the true nature of the universe we inhabit. As researchers continue their quest to merge the theories of gravity and quantum mechanics, they encounter a fascinating phenomenon that challenges our understanding of the universe: gravitational waves. These elusive ripples in the fabric of spacetime are created when massive objects, like merging black holes or neutron stars, accelerate through space. First predicted by Albert Einstein in 1915 as part of his groundbreaking general theory of relativity, gravitational waves offer a remarkable insight into how the universe operates at its most extreme. Einstein's theory describes how massive objects warp space-time itself. Much like a heavy ball placed on a rubber sheet creates a distortion. When these objects move, they create tiny ripples in the space-time continuum, waves that travel outward through the cosmos. These waves carry energy away from their source and travel at the speed of light, stretching and compressing spacetime as they pass. Though the effects are incredibly minuscule, they alter the distances between objects just enough to be detected by highly sensitive instruments. The discovery of gravitational waves has opened a new chapter in astrophysics, unlocking doors to phenomena once hidden from our view. The detection of these waves is no simple task. It requires instruments known as interferometers, which measure incredibly small changes in space. The Laser Interferometer Gravitational Wave Observatory, LIGO, with its 2 facilities in the United States, is one of the most prominent detectors in this field. These 2 facilities, separated by thousands of kilometers, each contain 2 long arms arranged in an L shape. When a gravitational wave passes through, it distorts spacetime and slightly changes the length of these arms. This distortion creates a unique pattern of interference in the laser beams used to measure them. To detect these faint signals, LIGO employs sophisticated technologies such as laser systems, vacuum chambers to eliminate air fluctuations, and isolation platforms to shield against environmental vibrations. In 2015, LIGO made history by detecting gravitational waves produced by the collision of 2 black holes, located more than 1 billion light-years away. This monumental achievement opened up an entirely new way of observing the universe, providing scientists with the tools to study phenomena that were previously invisible. But the impact of detecting gravitational waves extends far beyond simply observing cosmic events. These waves offer us a fresh perspective on the fundamental forces that govern our universe. They deepen our understanding of gravity and space-time, answering age-old questions about the nature of the cosmos. As technology advances, new detectors are being developed with the promise of even greater sensitivity and the potential for discoveries that could revolutionize astrophysics. Amidst these exciting advancements in gravitational wave detection, a new theoretical concept has emerged: the white hole. Often viewed as the opposite of a black hole, a white hole is a hypothetical region of space-time that expels matter and energy rather than absorbing it. While black holes trap everything, even light, within their gravitational pull, white holes would theoretically act as one-way exits, pushing matter out into the universe while preventing anything from entering. The idea of white holes arises from the same equations of general relativity that describe black holes. When scientists ponder the nature of black holes, they often wonder what might exist on the other side of the event horizon, the point of no return. Could there be a white hole, a mirror image of a black hole, in some distant part of the universe, or even in a parallel universe? Some theories suggest that every black hole could have a corresponding white hole, forming a pair that stretches across dimensions. This intriguing possibility raises questions about the very structure of the universe. If matter can be absorbed by a black hole and then ejected through a white hole elsewhere in the cosmos, it could lead to fascinating new models of cosmic events, such as gamma-ray bursts, or even the formation of new universes. While empirical evidence for white holes is still lacking, these speculative ideas fuel continued exploration into the mysteries of spacetime, gravity, and the nature of the universe itself. Yet, despite their allure, white holes remain deeply elusive. Their defining feature, the inability to observe the interiors of these cosmic entities makes them nearly impossible to study. The laws of thermodynamics suggest that white holes, if they exist, would be inherently unstable, quickly fading away as the energy needed to maintain them dissipates. However, these challenges in observation only inspire further debate and exploration within the realm of theoretical physics. The possibility that white holes could be linked to black holes continues to ignite the curiosity of scientists, propelling research that pushes the boundaries of our understanding of the cosmos. The gravitational pull of black holes extends far beyond simply drawing matter into their depths. These cosmic giants influence both time and space in profound ways. According to Einstein's general theory of relativity, the intense gravity of a black hole curves spacetime around it, causing time to slow down relative to an observer at a distance. This phenomenon, known as time dilation, becomes increasingly dramatic as one approaches the event horizon, the boundary beyond which nothing can escape. For an observer watching someone fall into a black hole, it would appear that time for that person slows to a near halt as they approach the event horizon. The observer would see their companion seemingly frozen in time, never quite crossing that threshold. However, for the individual falling in, time would proceed normally, at least until they reached the event horizon, where the laws of physics break down in unexpected ways. In addition to warping time, black holes also distort space itself. Their powerful gravitational field can alter the paths of objects in their vicinity, causing them to spiral inward or be flung out into unpredictable trajectories. These dramatic shifts in motion have significant consequences for the behavior of matter near black holes. They play a crucial role in the formation of accretion disks, a swirling mass of gas, dust, and debris that spirals ever closer to the black hole's event horizon. This chaotic dance of matter around a black hole is one of the most fascinating phenomena in astrophysics. The study of these processes allows scientists to gain valuable insights into the behavior of matter under extreme gravitational conditions, pushing the boundaries of what we know about the universe and the fundamental forces that govern it. As we continue to observe the universe through the lens of gravitational waves and black holes, the very nature of reality itself seems to bend and twist in unexpected ways, reminding us how much we have yet to discover about the cosmos. Moreover, black holes have the remarkable ability to create a phenomenon called gravitational lensing. As light from distant stars passes near a black hole, the immense gravitational pull bends the light, distorting or even multiplying the images of those stars. This phenomenon not only helps astronomers observe objects that might otherwise remain hidden in the vastness of space, but it also serves as a stunning visual testament to the immense power black holes possess in shaping the very fabric of space-time. The way black holes interact with time and space opens up fresh avenues for understanding our universe and challenges our perception of reality at its most fundamental level. At the heart of our exploration of black holes is the Event Horizon Telescope, a groundbreaking network of radio telescopes spread across the globe designed to capture images of black holes. By combining observations from multiple telescopes around the world using very long baseline interferometry, this ambitious project creates a virtual Earth-sized telescope with the sensitivity necessary to detect the faintest signals from the regions surrounding a black hole. This innovative technique allows astronomers to study celestial bodies that would otherwise be too distant and too faint to observe individually. In April 2019, the Event Horizon Telescope achieved a historic milestone by capturing the first ever image of a black hole, one that resides at the center of the supergiant elliptical galaxy Messier 87, about 53 million light-years from Earth. This momentous breakthrough marked the first time a black hole was directly imaged. Before this, black holes could only be inferred from indirect evidence, such as their effects on nearby stars and gas. To capture this groundbreaking image, the Event Horizon Telescope Network collected data over the course of a week in April 2017 using 8 radio observatories scattered across the globe. Their observations focused on the region surrounding the black hole's event horizon, the boundary beyond which nothing can escape, not even light. The intense gravitational forces at play cause this region to emit powerful radio waves, Processing the data collected from these observatories using complex algorithms, scientists were able to synthesize a single striking image, a bright ring of light encircling a dark center. This dark region represents the shadow of the black hole, surrounded by glowing material bent and illuminated by the black hole's gravity. The image not only confirmed theoretical predictions about black holes, but also opened the door to further studies on black hole physics. It allows researchers to test the limits of general relativity under extreme conditions and explore how matter behaves when subjected to such intense gravitational forces. The success of the Event Horizon Telescope stands as a testament to the power of international collaboration in scientific research. It has provided us with an unprecedented glimpse into one of the most enigmatic structures in the universe, advancing our understanding of black holes and their role in the cosmos. Despite their elusive nature, astronomers have developed several innovative techniques to study black holes. Since these mysterious objects cannot be seen directly, because their gravitational pull is so strong that not even light can escape, scientists focus on observing their effects on nearby matter. One of the primary methods for identifying black holes involves studying the orbits of stars and gas clouds in their vicinity. By analyzing the motion of stars near a black hole, astronomers can deduce the black hole's mass. For example, the supermassive black hole at the center of our own Milky Way galaxy, Sagittarius A, was identified by tracking the high-velocity orbits of nearby stars. Another vital method for studying black holes involves the examination of accretion disks. As matter like gas and dust spirals toward a black hole, it forms a rotating disk. The intense gravitational forces and friction within this disk cause it to heat up, emitting radiation across various wavelengths, most notably in the X-ray spectrum. Observing these high-energy emissions allows astronomers to gather crucial information about the black hole's accretion process and the extreme conditions near its event horizon. Space-based observatories like the Chandra X-ray Observatory have been instrumental in detecting these emissions. Perhaps one of the most exciting new fields of study is gravitational wave astronomy. When black holes collide or merge, they produce ripples in the fabric of spacetime, known as gravitational waves. Instruments like the Laser Interferometer Gravitational Wave Observatory, LIGO, have detected these waves, offering scientists new insights not only into the black holes involved, but also into the events that led to their merger. Gravitational waves have expanded our understanding of the universe, opening up fresh avenues for exploring the nature and properties of black holes. The Event Horizon Telescope has revolutionized our understanding of the universe, providing astronomers with the unprecedented ability to image the dark and mysterious surroundings of black holes. This groundbreaking achievement offers indirect visual evidence of their existence by focusing on the light emitted by matter spiraling around a black hole's event horizon. By capturing this light, researchers are able to produce images that not only validate theoretical models of black holes, but also test the predictions of general relativity. Together, these innovative methods form a powerful toolkit for studying black holes, helping us unlock the secrets of these enigmatic cosmic entities and explore their profound influence on the cosmos. Black holes come in various sizes and are categorized into distinct classes based on their mass and formation processes. These categories include stellar mass black holes and intermediate mass black holes, each with unique characteristics. Stellar mass black holes are typically the result of the gravitational collapse of massive stars at the end of their life cycles. Once a star exhausts its nuclear fuel, it can no longer counteract the force of gravity, leading to a collapse under its own weight. The black holes that form from this process usually have masses ranging from about 3 to several tens of solar masses, with the most common ones hovering between 5 and 20 solar masses. In contrast, intermediate mass black holes occupy a mass range that bridges the gap between stellar mass black holes and the supermassive black holes found at the centers of galaxies. These mysterious entities are theorized to have masses ranging from 100 to 100,000 solar masses, but they remain elusive in terms of direct observation. The processes that give rise to intermediate mass black holes are still not fully understood, though some theories suggest that they may form through the merger of multiple stellar mass black holes or the direct collapse of massive gas clouds within dense star clusters. Despite the challenges in detecting them, intermediate mass black holes hold significant importance in our study of the universe's structure and evolution. Stellar mass black holes are more commonly identified through their interactions with companion stars or by the X-ray emissions produced by their accretion disks. In contrast, intermediate mass black holes are more difficult to pinpoint using these methods. Observations of specific environments, such as star clusters or the centers of galaxies, have led to the identification of several candidates that may be intermediate mass black holes. The increasing knowledge of black hole formation and their varied sizes offers important insights into astrophysics, especially in understanding how galaxies and their central supermassive black holes evolve over time. By studying the differences between stellar mass and intermediate mass black holes, researchers can shed light on the intricate processes occurring within the universe, helping to expand our understanding of cosmic history. One of the most fascinating phenomena in black hole research involves binary black hole systems. These systems consist of two black holes that are gravitationally bound to each other, orbiting around a common center of mass. Binary black holes can form through various processes, such as the remnants of massive stars that were once in close proximity, or through the mergers of stellar mass black holes in dense star clusters. The dynamics of these systems can be incredibly complex as the black holes interact with each other, influencing the gravitational environment around them. This interaction provides valuable insight into the nature of gravity and black hole physics. As binary black holes orbit each other, they emit gravitational waves, ripples in spacetime that carry energy away from the system. The rate of energy loss increases as the black holes spiral closer together, leading to an accelerating orbital motion. Eventually, when the black holes get close enough, they can merge into a single, more massive black hole. This merger releases a tremendous amount of energy, mostly in the form of gravitational waves, producing distinct signals that can be detected by observatories like LIGO and Virgo. The merger process itself is an extraordinary event, unfolding in several stages. Initially, as the black holes approach each other, they disturb their surrounding environments, potentially accreting gas and generating energetic jets. When the black holes enter the final stages of their merger, they emit powerful bursts of gravitational waves, carrying information about their masses, spins, and the dynamics of the merging process. This phase is marked by a peak in the oscillations of the gravitational wave signals, which allows scientists to infer the properties of the resulting black hole. After the merger, the newly formed black hole may undergo a phase known as ring-down, where it settles into a stable state, emitting further gravitational waves as it vibrates like a ringing bell. This ring-down phase is a crucial tool for researchers, as it helps them analyze the characteristics of the newly formed black hole, including its mass and spin. Applying the principles of general relativity, the study of binary black hole systems and their mergers has profoundly expanded our understanding of black hole behavior and the dynamics of gravitational interactions. Each binary black hole merger captured by gravitational wave detectors offers a fresh opportunity to test the limits of our current theories and deepen our knowledge of the universe. These observations provide unique insights into the fundamental nature of gravity, spacetime, and the underlying processes that govern the evolution of black holes and their interactions within galaxies. As we continue to capture and analyze these events, we gain a clearer picture of the dynamic and mysterious role that black holes play in shaping the cosmos. Dark energy, a truly enigmatic and elusive force, weaves through every corner of space, silently shaping the universe in ways we are only beginning to understand. It accounts for about 70% of the total energy content of the universe, yet its true nature remains one of the most profound mysteries in modern cosmology. Unlike the familiar matter and dark matter, dark energy does not clump together. Instead, it exerts a strange, repulsive force that drives galaxies apart, defying the gravitational pull that normally holds objects together. This paradoxical force first emerged in the late 1990s, when astronomers studying distant supernovae made a shocking discovery. The expansion of the universe, far from slowing down as had been expected, was accelerating. This unexpected revelation led scientists down a new path of inquiry, and dark energy quickly emerged as a leading candidate to explain the phenomenon. The most widely accepted theory to date suggests that dark energy is a form of energy with a constant density, evenly filling space and creating a negative pressure that propels the expansion of the universe. As the dominant form of energy in the cosmos, dark energy has profound effects on the large-scale structure and evolution of the universe. One of its most striking influences is the distribution of galaxies. Rather than clumping together under the influence of gravity, galaxies are being pushed apart at an ever-increasing rate. The relentless expansion means that over time, dark energy will continue to outstrip the gravitational forces holding galaxies together, ultimately dictating the universe's fate. Scientists are now at the cutting edge of astrophysics, probing dark energy's characteristics and unraveling its secrets. Projects like the Dark Energy Survey and the upcoming Euclid satellite mission aim to track the universe's expansion and gather critical data about dark energy's behavior over time. These studies not only promise to illuminate the nature of dark energy itself, but could also have profound implications for the ultimate fate of the cosmos. In parallel with the hunt for dark energy, astronomers also find themselves captivated by gamma-ray bursts, GRBs, some of the most powerful and mysterious events in the universe. These bursts of gamma radiation, which can last anywhere from milliseconds to several minutes, release more energy in a fraction of a second than the sun will emit over its entire lifetime. GRBs are detected as fleeting flashes of gamma rays from distant galaxies, their origins tied to some of the most energetic processes in astrophysics. GRBs come in two distinct flavors, long-duration and short-duration bursts. Long-duration GRBs, lasting over 2 seconds, are believed to arise when massive stars collapse into black holes. When a star exhausts its nuclear fuel, it can no longer withstand the force of its own gravity. As the core implodes, it often triggers the formation of narrow jets of material ejected at nearly the speed of light. This explosion releases intense bursts of gamma radiation that can be detected across vast distances. These long bursts are often associated with supernovae, where the collapse of a star not only forms a black hole, but also ejects powerful beams of energy. If these jets are aligned with Earth, they can be observed as a gamma-ray burst. On the other hand, short-duration GRBs, lasting less than 2 seconds, are thought to occur during the merger of compact binary systems, such as 2 neutron stars or a neutron star and a black hole. When these objects collide, the resulting gravitational interactions unleash enormous amounts of energy, expelling matter and triggering the emission of gamma rays. These short bursts are sometimes linked to the creation of heavy elements through rapid neutron capture during the collision, a process known as nucleosynthesis. The power of GRBs is so immense that they can be detected across the farthest reaches of the universe, offering astronomers a unique window into the distant past. These bursts provide critical insights into the life cycles of massive stars, the behavior of matter under extreme conditions, and the dynamics of neutron star mergers. Each GRB is a cosmic fingerprint, a snapshot of the violent forces shaping the universe and providing a deeper understanding of how galaxies, stars, and elements came to be. As the study of dark energy and gamma-ray bursts progresses, these fields are converging to reveal the universe's most fundamental forces at work. The answers they provide may unlock not only the mysteries of space, but also the very fate of the cosmos itself. Studying cosmic events is crucial in unraveling the mysteries of the universe. It allows us to deepen our understanding of the fundamental processes that shape galaxies and guide the evolution of the cosmos. Each gamma-ray burst, a fleeting yet powerful burst of energy, offers a unique opportunity to probe the very heart of the universe. These bursts illuminate the most extreme and energetic phenomena taking place in the vast depths of space. Cosmic rays, the high-energy particles constantly bombarding Earth from every direction, are among the most intriguing and enigmatic entities in our universe. These particles, mostly protons, but also including heavy nuclei, electrons, and even gamma rays, travel across the cosmos at nearly the speed of light. Despite their constant presence, the origins of cosmic rays remain one of the most exciting and unresolved questions in astrophysics. Scientists believe cosmic rays are produced through a variety of energetic processes scattered throughout the universe. The journey of these particles begins in the explosive environments of supernovae, active galactic nuclei, and pulsars, regions where immense forces accelerate particles to speeds approaching that of light. During the catastrophic death of a massive star in a supernova explosion, shock waves interact with the surrounding space material, propelling particles into a high-energy regime. Active galactic nuclei, where supermassive black holes lurk at the center of galaxies, are another source of cosmic rays. The swirling, accreting material and the energetic jets shot from these black holes generate intense environments capable of accelerating particles to extraordinary speeds. Once generated, these cosmic rays travel across vast stretches of space, propelled by magnetic fields that permeate both interstellar and intergalactic space. These magnetic fields cause the particles to curve and spiral, creating paths that are often difficult to trace back to their origins. Despite the challenges posed by these magnetic deflections, scientists can still study cosmic rays that reach Earth. By analyzing their energy levels and composition, researchers can make educated guesses about where these particles originated, whether from the remnants of a supernova or from the energetic heart of an active galactic nucleus. Detecting cosmic rays on Earth requires specialized instruments and detectors that capture the secondary particles created when cosmic rays interact with our atmosphere. This interaction results in cascading particle showers, which scientists can study to understand the energy and composition of the original cosmic rays. Through careful observation of these cascades, researchers gain invaluable insights into the high-energy astrophysical environments where these particles are born. But the study of cosmic rays is not just about understanding the most violent processes in space. It also holds the key to answering profound questions about the fundamental nature of particles and the evolution of the universe itself. In fact, cosmic rays provide a unique window into both high-energy astrophysics and particle physics. Equally captivating is the cosmic microwave background radiation, or CMB, a faint glow that permeates the entire universe. This radiation, which bathes the cosmos in microwave wavelengths, is one of the most important pieces of evidence supporting the Big Bang theory. The CMB is a relic from the very early universe, dating back to a time approximately 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This process, known as recombination, marked a key turning point as photons were finally able to travel freely through space for the first time. Today, the CMB is detected as a nearly uniform background radiation, isotropically distributed across the entire sky. This faint glow is the universe's ancient echo, offering scientists a snapshot of the cosmos when it was in its infancy, a critical clue in understanding how the universe came to be and how it continues to evolve. However, even the slightest variations in temperature and density offer crucial insights into the universe's intricate structure and its dynamic evolution. These temperature fluctuations, also known as anisotropies, mark regions where density is not uniform. These fluctuations were the birthplace of the galaxies and large-scale cosmic structures we observe today. By examining the characteristics of these fluctuations, astronomers can gain vital information about the initial conditions of the universe, its rate of expansion, and its material makeup. The detailed analysis of the cosmic microwave background, CMB, has unveiled essential parameters of the universe, including its age, composition, and geometry. Measurements from a series of cutting-edge observatories, most notably the Wilkinson Microwave Anisotropy Probe and the Planck Satellite, have led to groundbreaking discoveries. According to their data, the universe is approximately 13.8 billion years old, composed of roughly 24% dark matter, 72% dark energy, and only about 4% ordinary matter. The CMB also strengthens the theory of cosmic inflation, a rapid expansion of the universe that occurred just moments after the Big Bang. This event helps explain the uniformity we observe in the CMB across vast distances. In the grander scheme, the CMB has become a vital tool for cosmologists, providing a rare glimpse into the universe's infancy and allowing for precise measurements. These measurements continue to enrich our understanding of cosmic evolution, supporting key aspects of the Big Bang Theory, while propelling further investigations into the fundamental nature of the universe and its ultimate fate. Fast radio bursts, FRBs, are another astronomical enigma that has captured the attention of scientists around the world. These extremely brief, yet highly energetic bursts of radio waves emanate from deep space. Despite lasting only a few milliseconds, FRBs release energy comparable to the total energy output of the Sun over the course of several seconds. The first FRB was detected in 2007 as a solitary pulse, and since then hundreds more have been observed, some of them repeating, while others remain a single occurrence. The origin of these bursts remains one of the greatest mysteries in astrophysics. Several theories attempt to explain FRBs. Some suggest that they may be linked to catastrophic astrophysical events such as the collapse of massive stars or the collision of neutron stars. Others speculate that they could be signals from advanced extraterrestrial civilizations, though this remains a highly speculative and unproven hypothesis. The distance at which these bursts originate only adds to their mystique. Many of them come from billions of light years away, meaning their radio waves travel across immense stretches of space before finally reaching Earth. Along the way, these signals encounter various cosmic materials, which can alter their properties and complicate efforts to decode their origins. Adding to the challenge, not all FRBs behave the same way. While some emit a single pulse, others release bursts at unpredictable intervals. Although the study of FRBs is still in its infancy, advancements in technology and more sensitive telescopes hold the promise of shedding light on the true nature of these captivating cosmic events. In doing so, astronomers hope to uncover the fundamental processes at work in the universe, leading to a deeper understanding of the cosmos. Antimatter is another mysterious component of the universe that has long intrigued scientists. Antimatter consists of particles that are counterparts to ordinary matter particles. For instance, a positron is the antimatter equivalent of an electron. When antimatter comes into contact with regular matter, the two annihilate each other, releasing energy in the form of high-energy gamma rays. This annihilation process serves as a telltale signature, enabling scientists to detect and study antimatter in space. One of the primary ways to observe antimatter is by detecting the gamma rays emitted from areas where matter and antimatter are interacting. Space-based telescopes like the Fermi Gamma Ray Space Telescope play a key role in monitoring the sky for these gamma ray bursts. These observations help scientists identify potential sources of antimatter, such as pulsars or the intense regions around black holes. By studying these phenomena, astronomers are slowly piecing together the conditions that might lead to the creation of antimatter in the universe, opening up new frontiers in our understanding of the cosmos. In a groundbreaking endeavor, researchers have succeeded in creating antimatter right here on Earth using particle accelerators. This allows them to explore its properties in a controlled setting. While these experiments don't directly observe antimatter in the vastness of space, they provide valuable insights that help scientists build models and understand the behavior of antimatter under replicated conditions. This knowledge, in turn, can be applied to interpreting the data from cosmic observations, offering new avenues for exploration. One of the most intriguing aspects of antimatter research lies in its connection to the evolution of the universe itself. The imbalance between matter and antimatter remains one of the most perplexing mysteries in modern physics. According to current theories, the Big Bang should have created equal amounts of both matter and antimatter. However, the universe we observe today is overwhelmingly dominated by matter. How this asymmetry arose remains a profound question. By combining observations of cosmic phenomena with theoretical models, researchers hope to uncover why matter triumphed over antimatter in the early universe. Understanding antimatter not only deepens our knowledge of the cosmos, but also challenges the fundamental principles of modern physics. This research is integral to our exploration of the universe's birth and the forces that shaped it. An equally fascinating concept in cosmology is cosmic inflation, a theory that proposes the universe underwent an ultra-rapid expansion in the first moments after the Big Bang. This expansion, which occurred from around 10 to the power of -34 seconds to 10 to the power of -32 seconds, is thought to have increased the size of the universe by a factor of at least 100 trillion times, potentially even more. This explosive growth took place long before galaxies, stars, and large cosmic structures began to form, profoundly influencing the shape of the universe we observe today. One of the key implications of cosmic inflation is its ability to explain the striking uniformity of the universe. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, reveal that the universe appears nearly uniform, with only tiny fluctuations. This uniformity is remarkable, especially in a universe that expanded so rapidly. The inflationary model suggests that the extreme stretching of space itself smoothed out any early irregularities, making the universe appear remarkably consistent over vast distances. Additionally, cosmic inflation helps us understand the large-scale structure of the universe. The tiny variations in density present in the early universe were amplified during inflation, setting the stage for the formation of galaxies and clusters under the influence of gravity. These initial density fluctuations, rooted in quantum mechanics, were stretched to cosmic scales, leading to the formation of the universe's current structure. This theory seamlessly aligns with other cosmological observations, such as the distribution of galaxies, further solidifying inflation as a key piece in the puzzle of the universe's evolution from a hot, dense state to the vast expanse we study today. Equally captivating are the phenomena known as gravitational lenses, which arise from Einstein's theory of general relativity. This theory posits that massive objects like galaxies or galaxy clusters can bend the path of light that travels near them. When light from a distant object, such as a galaxy or a quasar, passes close to one of these massive objects, the gravitational field of the foreground mass distorts the light, making the distant object appear magnified, distorted, or even duplicated. This gravitational lensing is not only visually stunning, but also serves as a crucial tool for astronomers. One of its most important applications is the measurement of the mass of foreground objects causing the lensing effect. By studying the degree of distortion and magnification in the light from background objects, astronomers can determine the mass of the lensing galaxies or clusters. This method is especially valuable for studying dark matter, an invisible substance that doesn't emit light but influences the mass and gravitational pull of galaxies. Moreover, gravitational lensing can amplify the light from distant, faint objects, allowing astronomers to study sources that would otherwise be too dim to observe. This enhanced visibility has enabled scientists to discover and analyze some of the earliest galaxies that formed in the universe, offering new insights into galaxy formation and evolution during the universe's early epochs. In these ways, both antimatter research and phenomena like cosmic inflation and gravitational lensing contribute to an ever-deepening understanding of the universe. Each discovery, whether on Earth or in the farthest reaches of space, offers a crucial piece in the cosmic puzzle, unveiling the hidden forces and processes that have shaped the cosmos over billions of years. Moreover, gravitational lensing has emerged as a groundbreaking tool, enabling astronomers to map the elusive distribution of dark matter across the vast expanse of the universe. By observing the way light bends around unseen objects, scientists can reconstruct models that shed light on dark matter's profound influence on cosmic structures. This research not only deepens our understanding of the universe, but also plays a crucial role in answering some of the most pressing questions about dark matter, which remains one of the greatest enigmas in modern astrophysics. Through gravitational lensing, scientists are gradually unlocking the hidden secrets of the cosmos, enhancing our grasp of the universe's intricate structure and the fundamental forces that shape it. The Great Void, often referred to as the Giant Void, represents one of the most fascinating and enigmatic features in our universe. This immense, relatively empty region of space stands out due to its stark absence of galaxies compared to the denser, more populated sections of the cosmos. Stretching across hundreds of millions of light years, the Great Void is defined by a dramatic underdensity of both matter and cosmic structure, making it a prime subject of study. What truly sets the Great Void apart is the profound challenge it poses to our understanding of galaxy distribution and the large-scale structure of the universe. It forces scientists to reevaluate long-standing theories and assumptions about how galaxies are scattered across space. The discovery of the Great Void dates back to the early 1980s, when astronomers began conducting detailed surveys to map the distribution of galaxies within the nearby universe. These surveys, which cataloged the positions of galaxies, revealed vast stretches of empty space, regions where galaxies were notably absent, contradicting expectations based on earlier models of the universe's structure. These surprising findings spurred further research and observations, ultimately confirming the existence of enormous voids in space, including the Great Void itself. Further investigation using data from influential astronomical surveys such as the 2-micron All-Sky Survey and the Sloan Digital Sky Survey provided deeper insight into the Great Void's nature. By creating three-dimensional maps of the cosmos, astronomers were able to isolate this vast region of emptiness, noting that it is encircled by dense filaments of galaxies, structures that are characteristic of the cosmic web. This discovery confirmed that the Great Void is not a solitary anomaly, but rather a part of a much larger, intricate pattern in the distribution of galaxies across the universe. The Great Void poses significant challenges to traditional cosmological models, particularly regarding the formation and evolution of galaxies over the course of billions of years. It raises fundamental questions about the role of cosmic expansion and dark energy in shaping the universe as we observe it today. More than just a void, the study of these massive empty spaces holds the potential to unlock new insights into cosmic evolution, the role of dark matter, and the overall distribution of matter throughout the universe. In many ways, the Great Void serves as a compelling reminder of the complexity of the cosmos, a universe filled with layers of mystery waiting to be uncovered. As scientists continue to explore these vast cosmic voids, they are also delving deeper into one of the most profound questions in modern science: the ultimate fate of the universe. This topic has become a field of intense speculation and study, with numerous competing theories attempting to predict how the cosmos might evolve in the distant future. One of the most well-known theories is the Big Freeze, or heat death, which suggests that the universe will continue its unrelenting expansion, with galaxies moving farther apart. As stars burn out and galaxies drift into isolation, the universe will become increasingly cold and dark. In this scenario, the cosmos will reach a state of maximum entropy, where no thermodynamic free energy remains, and the universe will effectively grind to a halt. On the other hand, an alternative theory proposes the Big Crunch, in which the expansion of the universe eventually halts and reverses due to the gravitational attraction between galaxies. This reversal would trigger the contraction of all cosmic structures, gradually pulling galaxies back toward one another. Ultimately, everything could collapse into an infinitely dense point, resembling the conditions at the very beginning of the universe during the Big Bang. While current observations indicate that the universe's expansion is accelerating, this theory leaves open the possibility that the universe's future may take a dramatically different turn. A more recent concept gaining traction is the Big Rip. This theory envisions an accelerated expansion of the universe due to the increasing influence of dark energy, the mysterious force that is driving the cosmos apart. Over time, the repulsive force of dark energy would grow stronger, pushing galaxies, stars, planets, and even atomic structures farther and farther away from one another. In this scenario, the fabric of spacetime would eventually tear apart at an accelerating rate, leading to the disintegration of all matter as we know it. The end of the universe, according to the Big Rip, would be marked by the destruction of all cosmic structures, down to the very atoms themselves. As our understanding of dark energy and the universe's expansion continues to evolve, it is clear that the ultimate fate of the cosmos remains one of the most intriguing and uncertain questions in astrophysics. Whether it ends in the cold isolation of the Big Freeze, the catastrophic collapse of the Big Crunch, or the violent destruction of the Big Rip, the future of the universe promises to be as awe-inspiring and mysterious as its origins. Some theories propose the idea of cyclical universes, a mind-boggling concept where the universe goes through endless cycles of expansion and contraction. According to this hypothesis, after the universe reaches a big crunch, a moment when all matter and energy collapse back into a singularity, it could bounce back, triggering a new Big Bang. This cycle, in theory, would repeat endlessly, with each iteration potentially bringing variations to the properties and structure of the universe. The result is a constantly evolving cosmic landscape where each cycle builds upon the last. These ideas represent just one of the many profound mysteries that continue to captivate scientists, propelling ongoing research into the ultimate fate of the universe in this ever-changing cosmos. Meanwhile, space telescopes such as the James Webb Space Telescope offer a groundbreaking way to observe the universe, allowing scientists to peer beyond the limitations of Earth's atmosphere. Ground-based telescopes, while useful, have to contend with the distortions caused by the atmosphere, which can absorb certain wavelengths and create turbulence that blurs the images. In contrast, placing telescopes in space allows astronomers to bypass these obstacles, capturing clearer and more precise data. This precision is crucial, as certain wavelengths, particularly infrared and ultraviolet, are blocked by the atmosphere. Space telescopes like Webb, however, can detect a much broader range of wavelengths, including infrared, which is essential for studying cooler celestial objects, such as newly forming stars and far-off galaxies. The James Webb Space Telescope, for instance, is uniquely designed to operate in the infrared spectrum. This capability allows it to see through the dust clouds that often obscure the view of the early universe, providing an unprecedented look at distant objects where the light has been redshifted due to the ongoing expansion of the universe. Moreover, space telescopes are not hindered by the limitations of Earth-based observatories. They can operate autonomously for long durations without interruptions caused by the day-night cycle, weather conditions, or light pollution, offering astronomers an uninterrupted view of the cosmos. This ability to focus on specific targets over extended periods means that space telescopes like Webb can gather invaluable data, often in real time, providing insights that are otherwise impossible to obtain. The technology behind these telescopes is complex and sophisticated. Building space telescopes requires meticulous planning, precise engineering, and rigorous testing, ensuring that the instruments will survive and function in the harsh environment of space with minimal maintenance. This complexity translates into high costs, but the rewards are significant. Space telescopes offer a unique window into the universe, helping to answer fundamental questions about its origins, evolution, and the forces that govern it. With the combined efforts of both ground-based and space-based observations, astronomers are continuing to push the boundaries of human understanding, striving to unlock the mysteries of the cosmos. When it comes to sending humans to Mars, the challenges are equally daunting. The journey involves an array of technological, physiological, logistical, and psychological hurdles. One of the biggest obstacles is the sheer distance between Earth and Mars. Depending on their positions in orbit, this distance can range from about 55 million kilometers to over 400 million kilometers, translating into travel times of 6 to 9 months or more. This prolonged journey requires spacecraft capable of sustaining human life, including providing life support systems and shielding astronauts from harmful radiation. Without Earth's protective atmosphere and magnetic field, astronauts would face significant exposure to cosmic rays and solar radiation, factors that could increase the risk of cancer and damage to their central nervous system. To address these concerns, agencies like NASA are researching various habitat designs and advanced radiation shielding technologies to ensure the safety of crew members during their long voyage and while on the Martian surface. Yet radiation isn't the only issue to contend with. Prolonged exposure to microgravity, the condition astronauts will face for much of the journey, can have serious consequences on the human body. Muscle atrophy, bone density loss, and changes to cardiovascular and vision health are just a few of the effects. Researchers are investigating countermeasures, including specialized exercise regimens and dietary strategies to help maintain astronaut health and ensure their ability to carry out the mission's demanding tasks. As scientists continue to grapple with these challenges, the dream of sending humans to Mars remains a work in progress, one that pushes the limits of our technological capabilities and the resilience of the human spirit. Astronauts face a multitude of challenges when embarking on long-duration space missions, especially when it comes to psychological and logistical hurdles. One of the primary concerns is the mental strain of isolation, which can severely affect individual well-being and strain team dynamics. Being away from Earth for months or even years at a time in a confined environment demands exceptional mental resilience, and careful psychological planning is necessary to ensure astronauts' mental health is maintained throughout the mission. In parallel, logistical obstacles present their own set of complications, from ensuring the crew's physical health to providing reliable life support systems. In a place as remote as Mars, traditional methods of survival simply won't work. Crews will need to produce their own oxygen, recycle water, and grow food on the Martian surface. This requires not only advanced technology, but also innovations focused on sustainability and self-sufficiency. Moreover, the journey to Mars and back will require reliable, efficient, and cost-effective transportation systems. Developing such systems, while critical, presents numerous challenges in terms of cost, efficiency, and reliability. Each of these concerns, mental health, life support, sustainability, and transportation, requires careful planning and attention to detail. Only by addressing these issues head-on can we hope to send humans to Mars and pave the way for future exploration of the Red Planet and beyond. The propulsion systems that power spacecraft on such long journeys are just as important. One remarkable technology gaining traction for deep space exploration is the ion engine, or ion thruster. Unlike traditional chemical rockets, which burn fuel to produce thrust, ion engines work by ionizing a propellant, usually a noble gas like xenon, and then using electric fields to accelerate the ions. The result is a continuous, low-thrust but highly efficient force that gradually accelerates a spacecraft over long periods. While the thrust generated by ion engines is much weaker than that of conventional engines, the advantage lies in their incredible efficiency. They use far less fuel while achieving the same change in velocity. This makes them ideal for missions where fuel conservation is critical. The ability to operate for extended periods without needing to constantly replenish fuel opens up possibilities for interplanetary and even interstellar travel. Ion engines have already proven their worth in missions such as NASA's Dawn spacecraft, which explored the asteroid belt, and the European Space Agency's Bepi-Colombo mission, which is on its way to Mercury. These spacecraft show how ion propulsion can enable deep space missions, covering vast distances with minimal fuel. As we look toward future missions to Mars and even the outer planets, ion engines will likely be a crucial technology in our space exploration toolkit. Their efficiency and ability to function over long durations make them ideal for missions that extend beyond the limitations of current propulsion technologies. Another remarkable milestone in space exploration is the Voyager program, which was launched by NASA in 1977. The twin spacecraft, Voyager 1 and Voyager 2, were designed to study the outer planets and the vast reaches of the solar system. Equipped with scientific instruments, the Voyagers provided invaluable data on the planet's atmospheres, magnetic fields, and surfaces, as well as capturing breathtaking images of these distant worlds. Voyager 2, the first to launch, visited all four gas giants: Jupiter, Saturn, Uranus, and Neptune, while Voyager 1 focused on Jupiter and Saturn. The data gathered by the Voyagers greatly expanded our understanding of these massive planets and their moons. For example, discoveries made about Europa, Jupiter's largest moon, and Titan, Saturn's largest moon, suggested the possibility of subsurface oceans, raising the intriguing question of whether life could exist beyond Earth. These missions not only provided vital insights into planetary systems, but also revealed unexpected phenomena like Jupiter's intense radiation belts and Saturn's complex ring system. Voyager 2's flybys of Uranus and Neptune added to our knowledge, unveiling new moons and providing an in-depth look at their atmospheres and weather systems. Beyond planetary exploration, the Voyager spacecraft also made history by continuing to send back data as they journeyed beyond the influence of the Sun. In 2012, Voyager 1 became the first human-made object to enter interstellar space, offering a new perspective on the heliosphere, solar wind, and cosmic rays. The program has not only expanded our understanding of the outer solar system, but also helped frame humanity's place in the vast cosmos. Meanwhile, astronauts aboard the International Space Station, ISS, must navigate the unique challenges posed by the microgravity environment. One of the most critical aspects of life aboard the ISS is the absence of gravity, which can lead to muscle atrophy and bone density loss. To counteract these effects, astronauts engage in regular exercise using specialized equipment like treadmills with harnesses and resistance machines. These daily routines help maintain cardiovascular health and prevent the detrimental effects of extended weightlessness. Life aboard the ISS also relies on highly sophisticated life support systems. These systems must ensure that astronauts have a constant supply of breathable air, typically made up of 21% oxygen and 79% nitrogen. They also play a crucial role in removing excess carbon dioxide, which astronauts exhale, and converting it into a usable form. Given that astronauts may spend months or even years aboard the ISS, these systems must operate without fail, ensuring the crew's survival in the harsh vacuum of space. As we look to the future, each of these advancements, whether in propulsion, sustainability, or life support, brings us closer to expanding humanity's reach into the cosmos. From the innovative ion engines that could power missions to distant planets to the ongoing exploration of our solar system by the Voyager spacecraft, our understanding of space continues to grow. At the same time, the technological leaps aboard the ISS remind us of the delicate balance required to maintain life beyond Earth. With careful planning, innovation, and persistence, the challenges of space exploration can be met, and the possibilities are limitless. In space, water is a precious resource, constantly recycled through advanced filtration technologies. These systems allow astronauts to capture moisture from the air and reclaim wastewater, including that generated from personal hygiene and food preparation. This innovative process is critical for long-duration missions where resupply opportunities are scarce. The ability to reuse water in such a way helps ensure astronauts can maintain their health and well-being, even when distant from Earth for extended periods. Food, too, is an essential part of life aboard the International Space Station, ISS. Astronauts rely on specially prepared meals that are lightweight, nutritious, and designed for long-term storage. The menu features a variety of options, ranging from freeze-dried fruits to thermostabilized entrees, all carefully curated to provide the necessary nutrients while minimizing waste. Eating in microgravity presents unique challenges, but astronauts have adapted by using utensils designed to prevent food from floating away during meals, allowing them to maintain a balanced diet and avoid making a mess in the confined space. Maintaining mental health is equally crucial for astronauts. During their extended stays in space, they stay connected to loved ones through regular communication with family and friends on Earth. They also have access to movies, books, and games, offering some respite during their downtime. Beyond entertainment, astronauts are rigorously trained to handle emergencies, ranging from equipment malfunctions to medical situations. This preparedness ensures they can respond swiftly and effectively to any challenges that arise while in space, whether they are minor inconveniences or serious incidents. Together, these elements form a carefully orchestrated environment that supports the astronauts in their mission to conduct groundbreaking scientific research and experiments. Their work takes place in the unique and challenging setting of the International Space Station, where every aspect of daily life is carefully planned to sustain their health, safety, and productivity. However, the environment surrounding the ISS is not without its dangers. Space junk, or space debris, consists of non-functional discarded objects orbiting Earth, including defunct satellites, spent rocket stages, and fragments from past collisions. The amount of space debris has increased dramatically since the beginning of space exploration, raising serious concerns about the potential risks it poses to operational spacecraft and the ISS. There are currently tens of millions of pieces of space junk, ranging from tiny paint flecks to large, hazardous fragments. All of them present varying degrees of risk to the safety of astronauts and equipment in orbit. One of the major threats is a phenomenon known as the Kessler syndrome. This theory suggests that if the density of objects in low Earth orbit becomes too high, the risk of collisions increases significantly. Each collision creates more debris, which in turn leads to more collisions, setting off a dangerous cascade of events. The resulting fragments can damage or destroy active satellites and spacecraft, further complicating future missions and ongoing activities in space. As the number of objects in orbit continues to grow, space debris has the potential to create a perilous environment for future space exploration. It not only poses a risk to scientific research, but also threatens commercial activities and the safety of astronauts aboard the ISS. Addressing this issue will be vital in ensuring that humanity can continue to explore and utilize space safely in the years to come. Moreover, as private companies and nations around the world plan to launch thousands of new satellites for communication, data collection, and other essential purposes, the risk of collisions in space escalates rapidly. With the growth of these satellite networks, space traffic management has become more vital than ever. Operators of satellites now have the critical task of monitoring potential conjunctions, situations where satellites and debris may collide, requiring them to maneuver their assets to avoid impacts. The challenge lies not only in the complexity of tracking these objects, but also in the vast number of particles involved. Many of these pieces are too small to be cataloged, yet large enough to cause significant damage to satellites and spacecraft. This growing concern has sparked a wave of efforts to address the mounting issue of space debris. These efforts involve international collaboration and technological innovation, aimed at ensuring space activities remain sustainable and safe for future generations. Proposed solutions include the development of methods to capture and deorbit defunct satellites, alongside the creation of guidelines for responsible satellite design and end-of-life disposal. Additionally, space cleanup missions are being proposed to remove larger pieces of debris. As humanity's presence in space expands, it has become imperative to confront the issue of space junk, not only to protect current missions, but also to guarantee the long-term safety and sustainability of space operations. At the same time, asteroid mining has emerged as an exciting and lucrative prospect for scientists and space entrepreneurs alike. Driven by the potential to harness valuable resources, the idea of mining asteroids has captured the imagination of many. Asteroids, rich in metals such as nickel, iron, and cobalt, as well as crucial materials like water and rare earth elements, present a tantalizing opportunity. Plans to mine asteroids combine advanced robotics, space exploration, and cutting-edge technologies designed to extract these valuable resources in a sustainable manner. One of the first steps in asteroid mining involves identifying suitable targets. Scientists use telescopes and spacecraft to survey nearby asteroids, assessing their composition, size, and proximity to Earth. Spectroscopy and other analytical methods allow researchers to determine the materials present on an asteroid's surface. Once a potential candidate is identified, missions can be launched to gather further detailed information. The extraction process may involve robotic spacecraft equipped with advanced mining technologies. These robots would be capable of landing on or rendezvousing with asteroids, using techniques such as drilling, scoop systems, or cutting tools to collect materials. Water, for example, could be extracted to support life support systems for future crewed missions, or even converted into fuel for spacecraft. Meanwhile, valuable metals could be processed on-site or returned to Earth for industrial use. However, asteroid mining is not without its challenges. Operating in low-gravity and microgravity environments requires the development of new technologies, as traditional mining methods simply don't apply. Navigating the complexities of space travel and ensuring the safety of mining operations and the surrounding space environment are significant hurdles. Furthermore, the establishment of legal and ethical frameworks will be necessary to manage the ownership and exploitation of space resources. Despite these challenges, as technology advances and our understanding of asteroids deepens, the prospect of asteroid mining could become a reality in the coming decades. This endeavor holds the promise of not only providing critical resources for Earth's industries, but also facilitating future space exploration. In situ resource utilization could allow spacecraft to refuel and repair in space, eliminating the need for costly supply missions from Earth. This would be a game changer for long-duration space missions, but paving the way for deeper exploration of our solar system and beyond. Similarly, the concept of a space elevator presents a revolutionary vision for the future of space travel. This idea envisions a transportation system that could dramatically transform the way humans access space. Essentially, a space elevator would consist of a cable or tether anchored to the Earth's surface and extending into geostationary orbit, about 36,000 kilometers above the equator. A counterweight positioned beyond geostationary orbit would maintain tension in the cable, allowing vehicles to ascend the tether to reach space using energy-efficient mechanisms instead of traditional rocket propulsion. One of the most appealing aspects of the space elevator is its potential to drastically reduce the cost of launching payloads into orbit. Currently, launching spacecraft requires vast amounts of rocket fuel, resulting in high costs and significant environmental impacts. With a space elevator, payloads could be gradually lifted along the tether, requiring far less energy compared to conventional launches. This technological leap could make space more accessible for a wide range of applications, from satellite deployment and space tourism to even planetary exploration. In the coming decades, the development of space elevators, asteroid mining, and efficient space traffic management could redefine humanity's relationship with space, making it more sustainable, accessible, and interconnected than ever before. A space elevator could transform the way we access space, enabling a continuous flow of materials and people to and from orbit. This infrastructure would open the door to the construction of space stations and manufacturing facilities in orbit, potentially giving birth to entirely new industries and technologies that are currently out of reach due to the immense logistical challenges of space travel. Regular access to space would also provide a platform for ongoing research and international collaboration in fields like astronomy, planetary science, and advanced technologies. However, despite its promise, the construction of a space elevator is far from simple. One of the major obstacles is the need for an incredibly strong tether material. This material would need to possess a strength-to-weight ratio that far surpasses anything currently available, much stronger than steel or any of today's advanced materials. Carbon nanotubes and other next-generation materials are being explored, but they are not yet developed to the scale or strength required for such a monumental task. In addition, there are numerous environmental factors that must be considered, such as adverse weather conditions, orbital decay, and the unpredictable nature of space weather, all of which pose significant risks. These challenges are daunting, but the concept of a space elevator continues to inspire researchers, as it has the potential to radically change how we explore and commercialize space. If realized, this technology could make space travel a more routine endeavor for humanity, transforming the future of exploration and industry. With ongoing research and technological advancements, what seems like a distant dream today could become a reality in the not-so-distant future. Meanwhile, spacecraft already employ a clever technique known as gravity assists, or gravitational slingshots, to conserve fuel, adjust their trajectories, and gain speed. This maneuver takes advantage of the gravitational pull of a planet or moon to slingshot the spacecraft, increasing its speed without the need for additional propulsion. At its core, gravity assist relies on the conservation of momentum. As a spacecraft flies past a massive celestial body, it essentially steals a small portion of the body's motion, which results in an increase in the spacecraft's velocity relative to the Sun. The process is deceptively simple. As a spacecraft approaches a planet, it falls into the planet's gravity well. Once it swings around the planet, it gains speed as it's pulled in and is then flung outward on the opposite side, much like a stone tossed from a slingshot. The spacecraft's trajectory can be finely tuned during this flyby to optimize the resulting path. For instance, a spacecraft traveling to the outer reaches of the solar system might use a close approach to a gas giant like Jupiter to gain extra velocity, while also being redirected toward its next destination. This technique has been pivotal in numerous historic space missions. The Voyager spacecraft, for example, made multiple gravity assists at Jupiter and Saturn, extending their journeys far beyond their original scope. These assists allowed Voyager 1 and Voyager 2 to reach the outermost planets, while also providing a wealth of data about the gas giants and their moons. Gravity assists not only accelerate spacecraft, but they also drastically reduce the amount of fuel needed for long-duration missions, making them more feasible both financially and practically. As a result, gravity assists have become a cornerstone of deep space exploration, enabling missions that would otherwise be impossible. By utilizing the gravitational fields of planets and moons, spacecraft can travel farther, faster, and more efficiently, opening up new possibilities for the exploration of our solar system and beyond. Exploration of distant targets in space is a pivotal goal for future missions, where even the smallest fuel-saving advancements can extend the length and depth of these missions. By maximizing fuel efficiency, astronauts and robots can venture further into the solar system, opening the door to new scientific discoveries. Understanding and strategically utilizing gravitational assists will continue to be a cornerstone of mission planning, enabling exploration beyond what was once thought possible. As the goal of establishing a permanent human presence on the moon gains momentum, space agencies and private companies are intensifying their efforts. The United States, through NASA's Artemis program, plans to return astronauts to the lunar surface by the mid-2020s. This ambitious initiative will not only revisit the moon, but also lay the foundation for sustainable lunar exploration. A key focus is the lunar South Pole, where deposits of water ice have been discovered. These resources could be vital for human habitation, while also providing crucial insights into the moon's geological history. To support long-term exploration, NASA has ambitious plans for the Lunar Gateway, a space station that will orbit the moon. This gateway will act as a hub for missions to the lunar surface, facilitating activities from scientific research to operational tasks. It will also serve as a launch point for future missions, furthering humanity's reach into deep space. Through international collaboration and partnerships with private entities, the Gateway aims to bolster the capabilities necessary for exploring the moon while potentially paving the way for a thriving lunar economy. Parallel to this effort is the proposal for the Artemis Base Camp, which is designed to support astronauts in living and working on the moon for extended periods. This base would feature habitats, lunar landers, and equipment for surface exploration. Its primary purpose will be to search for resources, conduct experiments, and prepare for humanity's next great leap, missions to Mars and beyond. As NASA works to develop a sustainable presence on the moon, other countries like China and Russia are also ramping up their lunar exploration programs. These efforts could foster a global, collaborative approach to moon exploration, similar to the partnerships seen with the International Space Station. As nations and private companies unite in their pursuit of this goal, the moon is poised to become a bustling center for science, technology, and human progress, paving the way for deeper space exploration. In the grand scheme of space exploration, understanding the habitability of distant planets remains a crucial goal. For a planet to be considered potentially habitable, several factors must align to create conditions that support life. Water, often dubbed the universal solvent, is one of the most vital components. Life as we know it depends on liquid water for biochemical processes, and a planet must exist in the habitable zone of its star. This zone is the region where temperatures allow water to remain in a liquid state, not too hot to cause water to evaporate and not too cold to freeze it. Equally important is the planet's atmosphere. A stable atmosphere creates the pressure needed to sustain liquid water while shielding any potential life forms from the harsh cosmic radiation and extreme temperatures of space. For an atmosphere to support life, it must also contain essential gases like oxygen and carbon dioxide in the right proportions to maintain a climate conducive to life. Geological activity is another key factor. Tectonic processes help recycle vital nutrients and gases, maintaining a stable environment over vast timescales, which is essential for sustaining life. Moreover, a planet's magnetic field plays a critical role in protecting its atmosphere from solar winds. Without this shield, a planet's atmosphere could gradually erode, leaving it vulnerable to the harsh conditions of space. Thus, the interplay of water, atmosphere, geological activity, and magnetic protection forms the delicate balance that makes a planet potentially habitable, offering humanity a tantalizing glimpse of what lies beyond our own world. The discovery of organic molecules, carbon-based compounds that form the very foundation of life, offers a glimpse into the potential of distant worlds. These molecules can emerge through various natural processes, and their presence is crucial for the development of life as we understand it. When searching for planets that might harbor life, or at the very least, possess the conditions that could allow life to arise, these organic compounds serve as vital clues. Currently, scientists have identified thousands of exoplanets, and among them, a noteworthy number are considered potentially habitable. To date, over 4,000 exoplanets have been confirmed, with more than 100 of them classified as potentially habitable. These planets reside in what is known as the habitable zone of their stars, an area where the temperatures are just right to allow liquid water to exist, provided the atmosphere is suitable. This crucial zone becomes a focal point in the ongoing search for life beyond Earth. The exploration of exoplanets has been spearheaded by space missions such as NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS. These missions have significantly expanded our understanding of planetary systems beyond our own, identifying planets of various sizes, compositions, and orbital patterns. The criteria for determining whether a planet could potentially support life are based on several factors, including its size, its distance from its host star, and the presence of an atmosphere that could maintain the right conditions for life. The search, however, does not stop there. As technology advances, scientists are utilizing both ground-based telescopes and cutting-edge techniques to analyze the atmospheres of these distant worlds. By doing so, they hope to gather more data to refine our understanding of these planets and evaluate their potential to support life more accurately. This ongoing research is essential for pinpointing the specific elements and conditions that might make a planet truly habitable. With technological innovations continuing to unfold, the number of potentially habitable exoplanets identified is expected to increase. The quest for life beyond Earth remains one of the most compelling pursuits in modern astronomy, opening up endless possibilities for the existence of life across the cosmos. One of the key concepts in this search is the Goldilocks zone, a term derived from the classic fairy tale where Goldilocks finds the porridge that is just right. In astronomical terms, this zone refers to the region around a star where conditions are optimal for liquid water to exist on a planet's surface. Not too hot, not too cold, but just right. Liquid water is considered the essential ingredient for life as we know it, as it serves as a solvent for biochemical reactions and provides a medium in which life can thrive. The boundaries of the Goldilocks zone can vary depending on the size and temperature of the star. For example, a smaller, cooler star will have a habitable zone that is much closer to it, while a larger, hotter star will have its habitable zone much farther out. Earth, for instance, lies comfortably within the Sun's habitable zone, maintaining stable temperatures that support liquid water and, consequently, life. The identification of exoplanets within these habitable zones is a central goal for astronomers searching for signs of life beyond our solar system. When a planet is discovered within this zone, it raises the possibility that the conditions necessary for life may be present, prompting further investigation. However, simply being within the Goldilocks zone does not guarantee habitability. Other critical factors, such as the planet's atmospheric composition, geological activity, and the presence of a magnetic field, all play essential roles in determining whether life could truly exist there. In the end, the search for planets that could host life is about more than just finding a suitable location for water. It's about piecing together an intricate puzzle that includes many variables, each one bringing us closer to understanding the potential for life in the universe. Moreover, as our understanding of the cosmos deepens, the concept of the Goldilocks zone is expanding. Previously, this zone, the region around a star where conditions are just right for liquid water to exist, was thought to define the only possible place for life to thrive. However, discoveries of extremophiles, organisms that flourish in harsh environments, have dramatically shifted this perspective. Some of these life forms survive in places once deemed inhospitable, such as the boiling hot springs of Yellowstone or the frozen depths of Antarctica. These astonishing discoveries have led scientists to reconsider the boundaries of habitability, suggesting that life may be possible in environments far beyond our traditional understanding. This evolving view broadens the search for habitable worlds. As we learn more about life's adaptability, the quest to find planets that might host life becomes even more compelling. Scientists now explore regions beyond the Goldilocks zone, testing the limits of habitability and expanding the horizon of where life might exist in the universe. To search for signs of life beyond Earth, scientists employ a range of sophisticated methods. Atmospheric analysis and direct imaging are among the most common techniques used to study exoplanets, planets orbiting stars outside our solar system. One of the most powerful tools in this arsenal is spectroscopy. This technique involves studying the light that filters through a planet's atmosphere as it transits in front of its host star. By analyzing this light, scientists can identify the unique spectral signatures of gases like oxygen, methane, and carbon dioxide. On Earth, these gases are commonly associated with biological processes, so their presence on an exoplanet could suggest the possibility of life. Another approach involves astrobiological models, which use data from missions like NASA's Kepler and TESS, Transiting Exoplanet Survey Satellite, to locate potentially habitable exoplanets within the Goldilocks zone. Once promising candidates are identified, scientists use simulations to model atmospheric conditions and predict how they might behave under different scenarios. These models offer invaluable insights into the planet's potential for supporting life and can help determine whether such worlds are truly habitable. Direct imaging is another challenging but valuable method of exoplanet study. It involves capturing actual images of planets, which is difficult due to the overwhelming brightness of their parent stars. However, the upcoming James Webb Space Telescope, JWST, is expected to dramatically improve this capability. JWST's advanced technology may allow us to capture high-resolution images of exoplanets, revealing crucial information about surface conditions, atmospheric features, and potential signs of biological activity. This could bring us closer to answering the age-old question, are we alone in the universe? In addition to studying exoplanets directly, scientists are also focusing on the stars that host these distant worlds. The properties of these stars, such as their mass, stability, and the presence of stellar flares, can greatly impact the habitability of the planets orbiting them. For instance, a star's radiation and activity levels could either support or hinder the conditions necessary for life. By analyzing both stellar and planetary data, scientists are able to better assess which exoplanets hold the most promise for life. This holistic approach significantly improves the chances of identifying worlds where life may be possible. As technology advances and new missions are launched, the search for life beyond Earth continues to gain momentum. Our tools are becoming more powerful, and our understanding of the universe is expanding rapidly. In the coming years, the ability to detect signs of life on distant exoplanets is likely to advance significantly, enriching our knowledge of the cosmos. The study of exoplanets has already revealed an incredible variety of worlds, some that challenge our expectations and expand our understanding of planetary systems. One of the most fascinating examples is WASP-17b, an exoplanet classified as a hot Jupiter. This gas giant orbits very close to its star, causing surface temperatures to soar above 1,000 degrees Celsius, 1,832 degrees Fahrenheit. The extreme conditions on WASP-17b create an unusual environment where phenomena like rapid winds and molten glass rain are observed. This exoplanet offers an opportunity to study the effects of extreme environments on planetary atmospheres and surface conditions. Another intriguing discovery is HD 29458b, often called Osiris. This planet is notable for its dramatic atmospheric loss. Intense radiation from its star strips away the planet's gases, leaving behind a trailing tail of vapor. Observations show that the atmosphere of Osiris is being eroded at an alarming rate, providing valuable insights into the forces that shape a planet's atmosphere over time and the factors that might influence its habitability in the long term. Then there's Kepler 20b, a super-Earth with an intriguing, yet puzzling, density. Nearly twice the size of Earth, this planet is surprisingly dense, which suggests it may be composed mostly of rock or some other material not commonly found in our solar system. Understanding the composition of such exoplanets is crucial for unraveling the mysteries of planetary formation and the variety of environments that may exist beyond our solar system. As our technology improves and we continue to explore distant worlds, the search for life in the cosmos becomes more exciting and more complex. With each new discovery, we gain a deeper understanding of the conditions necessary for life and the incredible diversity of planets that exist in our universe. The possibilities are limitless, and the journey of exploration has only just begun. Planet LHS 8006, also known as the Pancake, is one of the most fascinating and peculiar worlds discovered beyond our solar system. This exoplanet is strikingly unusual due to its distinctly elongated shape, a result of its incredibly rapid rotation. The immense speed at which it spins causes it to flatten at the poles, distorting its form into something resembling a pancake. This bizarre structure raises important questions about how a planet's rotation can fundamentally alter its shape and composition. It also offers a unique opportunity for scientists to explore the myriad ways in which exoplanets can differ from Earth, expanding our understanding of the vast possibilities in the cosmos. The study of such extraordinary worlds also sparks our curiosity about the potential for life beyond our own solar system. To examine these far-off planets, astronomers employ a variety of sophisticated techniques to delve into the atmospheres of exoplanets. These methods provide essential insights into what these planets are made of and whether they might be capable of supporting life. One of the most effective tools in this pursuit is transmission spectroscopy. This technique involves observing an exoplanet as it crosses in front of its host star. When the planet transits, some of the star's light filters through the planet's atmosphere. By analyzing the spectrum of this filtered light, scientists can pinpoint the specific wavelengths absorbed by different gases, revealing key details about the planet's atmospheric composition. Another powerful method is secondary eclipse spectroscopy, which occurs when an exoplanet moves behind its star. During this phase, astronomers can compare the light from the star alone to the combined light from both the star and the planet. By examining the variations in the light spectrum during these two distinct phases, they can calculate how much light the planet emits or reflects. This provides valuable information about the planet's surface and atmospheric properties. Direct imaging is also an important tool for astronomers, although it is challenging due to the overwhelming brightness of the host star. Advanced imaging techniques like coronagraphy and the use of star shades allow astronomers to block out the star's light, enabling them to capture images of the planets themselves. These images help researchers collect direct data about the atmospheric features of certain exoplanets. In addition to these observational techniques, computer models play a crucial role in interpreting the vast amount of data gathered. Scientists use simulations to understand how different atmospheric gases interact with light, as well as to model how various atmospheric compositions might react to factors like solar radiation. By combining observational data with sophisticated theoretical frameworks, astronomers are able to create detailed and accurate models of exoplanet atmospheres, giving us a clearer picture of these distant worlds and their potential for supporting life. One of the most intriguing ideas to emerge from the study of exoplanets is the hypothesis of panspermia. This theory suggests that life on Earth and possibly elsewhere in the universe may have originated from microscopic organisms or organic compounds that traveled through space. According to panspermia, life could spread between celestial bodies via comets, meteoroids, or cosmic dust, hinting at the possibility that life's building blocks exist beyond our planet. This raises fascinating questions about the interconnectedness of life across the cosmos. There are several variations of the panspermia hypothesis. One version proposes that microscopic life forms, such as bacteria, could survive the harsh conditions of space travel. These organisms might remain dormant during their journey, only to become active upon reaching a planet with the right conditions for growth, conditions similar to those found on Earth. The endurance of extremophiles, organisms that thrive in extreme environments on Earth, supports the idea that life could potentially survive the journey through space. These extremophiles can withstand intense radiation, extreme temperatures, and even the vacuum of space, making it conceivable that life could endure the harsh journey across the cosmos. Another intriguing aspect of panspermia is the idea that not all spaceborne life would need to be fully formed organisms. Instead, it is possible that complex organic molecules like amino acids and nucleotide precursors could be delivered to planets via meteoritic impacts. Research suggests that such organic molecules could form in interstellar space and then be carried to planets by comets and asteroids. This aligns with laboratory experiments on Earth, which show that simple organic molecules can form under prebiotic conditions. If these molecules were indeed delivered to Earth or other planets, they might have played a crucial role in the emergence of life. In the search for life beyond our planet, the study of exoplanets, the exploration of panspermia, and the development of advanced astronomical techniques continue to captivate scientists. These groundbreaking endeavors deepen our understanding of how life might exist in the vast expanse of the universe, and they remind us of the many mysteries yet to be unraveled about our place in the cosmos. Panspermia is a theory that opens a window into profound questions about the nature of life in the universe. It proposes that life's building blocks, organic molecules, or even microorganisms, are widespread across the cosmos, transported by space dust, comets, or meteorites. This possibility doesn't just spark curiosity about life on Earth, but it also radically shifts how we might view life elsewhere. If the ingredients for life are scattered across the universe, then the probability that life could emerge on other planets increases significantly. It suggests that the universe could be brimming with life, its form shaped by the movement of materials across vast distances and varying celestial environments. This interconnection of planets, stars, and cosmic materials underscores the mysteries of life, both here on Earth and in the far reaches of space, prompting deeper exploration into the cosmos. Rogue planets add another layer to our understanding of the universe. These fascinating celestial bodies drift aimlessly through space, untethered to any star. Their formation is thought to occur through several mechanisms. One prominent theory posits that rogue planets begin their existence within planetary systems, but are ejected due to gravitational interactions, perhaps with larger planets or even the gravitational influence of a nearby star. This disruption could send the planet on a solitary journey across the galaxy. Alternatively, some rogue planets may form in isolation within a young star system's protoplanetary disk, but fail to be captured by the star's gravitational pull, either due to insufficient mass or other forces within the system. As a result, these planets wander freely through the vast expanse of space. Research suggests that rogue planets could be far more common than previously thought. Studies indicate that there might be billions of these wandering worlds in the Milky Way alone. Advanced telescopes and sophisticated planetary formation models have helped estimate the prevalence of these planets. As star systems often contain multiple planets, the likelihood that some will be ejected into interstellar space is high. The existence of rogue planets raises fascinating questions about the formation and evolution of planetary systems. Their solitary existence prompts further investigation into how they interact with other celestial bodies, what conditions they might harbor, and whether they could potentially support life despite the absence of a host star. Super-Earths, a category of exoplanets, have become one of the most intriguing subjects in modern astronomy. These planets have a mass greater than Earth's, but significantly less than that of the gas giants like Neptune or Uranus. Super-Earths can range in mass from 1 to 10 times that of Earth, with a wide variety of possible compositions and atmospheric conditions. Some may be rocky, resembling Earth, while others could be shrouded in thick gaseous envelopes. This variety makes super-Earths especially interesting to astronomers and astrobiologists, as they may hold the key to understanding the diversity of planetary systems. The allure of super-Earths lies largely in their potential to harbor life. Many of these planets reside in the habitable zone of their stars, where temperatures are just right for liquid water to exist, a fundamental ingredient for life as we know it. Additionally, the wide range of sizes and compositions among super-Earths raises important questions about their geological activity, atmospheric stability, and the likelihood that they could support life in diverse forms. Studying these planets gives scientists valuable insights into how life could potentially thrive in environments vastly different from our own, shedding light on the resilience and adaptability of life across the cosmos. The discovery of super-Earths has revolutionized our understanding of planetary formation and the potential diversity of planetary systems. These massive exoplanets, with their sizes surpassing Earth's yet smaller than the gas giants, challenge existing theories of how planets come into existence and what their environments might look like. The widespread presence of super-Earths suggests that planet formation is not a one-size-fits-all process. Instead, it can unfold in a variety of ways, influenced by a range of factors. Astronomers equipped with advanced telescopes and cutting-edge technologies are now turning their attention to the atmospheres and surface conditions of these intriguing worlds. With each new discovery, they hope to unlock the secrets of how these planets evolve, and perhaps how life might adapt and emerge in conditions unlike anything we've ever known. As the search for extraterrestrial life intensifies, super-Earths have quickly become one of the most promising frontiers in this exploration. Their proximity to us and their often Earth-like conditions make them prime candidates for future missions, whether through direct observation or by analyzing their atmospheric compositions for potential biosignatures. With each study, we are broadening the scope of where life might exist beyond our solar system. In this quest, one particularly fascinating area of research is the possibility of life on planets orbiting red dwarf stars, objects that are both the most abundant and the most mysterious type of stars in our universe. These stars are much smaller and cooler than our Sun, and their lifespans far exceed that of our central star, sometimes lasting tens to hundreds of billions of years. This extended lifespan could offer a stable environment for planets orbiting within the habitable zone, a region where liquid water could exist, crucial for the development of life as we know it. Interestingly, the habitable zones of red dwarfs tend to be much closer to the star compared to larger stars like our Sun, which presents its own unique set of challenges. One of the most pressing concerns is the habitability of planets around red dwarfs, particularly due to the high levels of stellar activity. Red dwarfs are notorious for their intense and frequent stellar flares, bursts of radiation that can bombard nearby planets, potentially stripping them of their atmospheres. This radiation could have devastating effects, leading to a hostile environment for any potential life forms. However, if a planet can somehow maintain a stable atmosphere despite these constant solar eruptions, it could offer a refuge for life. The organisms that evolve here would likely need to develop remarkable adaptations to survive in such a harsh, radiation-heavy environment. These might include biological shields against radiation, or perhaps life could seek refuge in subsurface habitats, sheltered from the relentless surface radiation. In addition to the challenges posed by stellar flares, the proximity of a planet to its red dwarf star brings another unique factor into play: tidal locking. In many cases, planets orbiting these stars become tidally locked, meaning that one side of the planet is always facing the star, while the other remains in eternal darkness. This creates an extreme contrast between the scorching heat of the day side and the frigid cold of the night side. Such dramatic temperature differences could result in unique climate patterns, potentially fostering environments that challenge life to evolve in ways we've never imagined. Life on these worlds might not survive across the entire surface, but could thrive in the twilight zones, those regions along the border between day and night, where conditions are more temperate and sunlight is still accessible. These narrow, habitable bands could offer the perfect balance of warmth and shelter for the development of life, adapted to survive in this extreme world. In conclusion, as we continue to explore the cosmos, the study of super-Earths and planets orbiting red dwarf stars is reshaping our understanding of what constitutes a habitable world. These distant planets challenge our assumptions, broaden our perspectives, and offer a tantalizing glimpse into the many possible forms life might take across the universe. Through ongoing exploration and research, we inch closer to answering the ultimate question: are we truly alone? The long lifetimes of red dwarf stars offer extraordinary timeframes for life to evolve and adapt. These stars, which can burn for tens to even hundreds of billions of years, provide an immense window for evolutionary processes. Over billions of years, ecosystems may develop in ways that we can't yet fully imagine, perhaps leading to life forms that are resilient to even the most extreme environmental conditions. Although the specific pathways life might take around red dwarfs remain largely speculative, studying these stars and their systems is essential in our pursuit of understanding how life might emerge in diverse stellar environments. As red dwarfs make up the majority of stars in our galaxy, their sheer prevalence opens the tantalizing possibility that they could host life unlike anything we've encountered here on Earth. The observable universe, meanwhile, is staggeringly vast. It spans an estimated diameter of around 92 billion light years, a mind-boggling distance that represents the limits of what we can observe, determined by the finite speed of light and the age of the universe. Since the Big Bang, which occurred approximately 13.8 billion years ago, the universe has been expanding, with light from distant objects taking billions of years to reach us. This provides us with a snapshot into the very early stages of cosmic history, offering a glimpse into the universe as it was just after its inception. Scientists have pieced together this understanding through a combination of astronomical observations and sophisticated theoretical models. One of the key tools used to trace the history of the universe is the study of cosmic microwave background radiation, the faint afterglow of the Big Bang. By examining the uniformity of this radiation and its slight fluctuations, astronomers gain valuable insights into the early conditions of the universe, its expansion, and the large-scale structure that emerged over time. Instruments like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have been pivotal in gathering data, helping scientists refine our understanding of the universe's age and size. Another critical approach to measuring the universe involves observing distant galaxies and analyzing their redshift. As the universe expands, galaxies are moving away from us, causing their emitted light to stretch into longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift, scientists can calculate how far away these galaxies are and how fast they are receding. This, in turn, allows us to determine the rate of the universe's expansion, known as the Hubble constant. While the observable universe is vast, it's important to recognize that it is only a fraction of the entire cosmos. Beyond what we can see, the universe may extend infinitely, or there may be regions that lie beyond our observational reach. The methods we use to map the observable universe blend cutting-edge observational astronomy with complex theoretical frameworks, creating a detailed picture of our cosmic surroundings. However, as our tools and techniques improve, we continue to uncover new mysteries that lie beyond our current understanding. When we talk about light years, we're referring to a unit of distance that represents how far light can travel in 1 year in a vacuum. Given that light moves at an astounding speed of approximately 300,000 kilometers per second, a single light year is equivalent to about 9 trillion kilometers. This unit allows astronomers to convey the vast distances between objects in space in terms that are easier to grasp. For instance, when we say that Proxima Centauri, the closest star to our solar system, is about 4 light years away, we mean that light from this star takes 4 years to reach us. This vast scale helps astronomers communicate the size of cosmic distances, which are often beyond the scope of everyday human experience. For example, our Milky Way galaxy spans about 100,000 light years across. The observable universe, with its billions of galaxies, stretches even farther, up to billions of light years in every direction. The use of light years as a unit of measurement allows scientists to chart these immense distances and helps us comprehend the staggering size of the universe, from the nearest stars to the most distant galaxies. In the end, these measurements, tools, and insights all work together to deepen our understanding of the cosmos, an understanding that is still evolving. Whether we're studying red dwarf stars as potential cradles for alien life, or examining the farthest reaches of the universe, The quest for knowledge pushes us to constantly explore and expand the boundaries of our understanding as we continue to discover just how vast, mysterious, and full of possibility the universe truly is. Understanding light years is pivotal for astronomers seeking to study the vast stretches of space that lie beyond our planet. As the universe continuously expands, the light emitted by distant galaxies reveals critical information about their motion and the history of the cosmos. By measuring cosmic distances in light years, scientists gain invaluable insights into the dynamic forces shaping the universe. This approach serves as a bridge linking our observable world with the ever-expanding cosmos beyond. To navigate these immense distances, astronomers employ the cosmic distance ladder, a systematic method used to measure distances across the universe. Much like the rungs of a ladder, each step in this technique builds upon the previous one, allowing scientists to explore increasingly distant objects. The first rung of this ladder is parallax, a method that measures the distance to nearby stars by observing their apparent movement against the backdrop of more distant celestial bodies. By noting this shift, astronomers can calculate the star's distance based on the angle of its apparent motion. This technique is effective for stars within a few hundred light years, providing an essential baseline for future measurements. Climbing higher on the ladder, astronomers turn to standard candles, particularly Cepheid variable stars. These stars exhibit a predictable relationship between their pulsation period and their intrinsic brightness. By measuring a Cepheid's apparent brightness from Earth, astronomers can compare it to its actual brightness and determine its distance. This method extends the reach of the cosmic distance ladder to thousands of light years, unlocking a broader view of the universe. For even greater distances, astronomers rely on Type 1a supernovae, which serve as excellent standard candles due to their consistent peak brightness. When these supernovae occur in distant galaxies, their light allows astronomers to calculate the distance to those galaxies with impressive accuracy. But it doesn't end there. Combining this distance data with redshift measurements, how much the light from distant galaxies shifts toward the red end of the spectrum due to the universe's expansion, astronomers can measure vast distances across billions of light years. Each rung of the cosmic distance ladder is essential in building a comprehensive understanding of the universe's structure. As astronomers ascend higher, they gain a clearer, more detailed picture of the universe's scale and its dynamic evolution. This hierarchical method allows scientists to map out the cosmos with increasing precision, revealing the fundamental characteristics of celestial objects and ultimately deepening our understanding of the universe itself. The concept of cosmic horizons delves into the very limits of our observable universe. These horizons mark the boundaries beyond which we can no longer receive any form of information. But why does this happen? It's due to the ongoing expansion of the universe itself. As space stretches, certain regions of the universe are moving away from us at speeds faster than the speed of light. In this cosmic race, light from those regions will never be able to reach us. This creates an invisible wall, a boundary beyond which our instruments cannot detect or observe. The two primary types of cosmic horizons, the particle horizon and the event horizon, play a pivotal role in shaping how we view the universe. The particle horizon represents the farthest distance from which light has had the time to travel and reach us since the beginning of the universe. This boundary defines the observable universe, telling us how far we can see with our telescopes. It encompasses everything from distant galaxies to cosmic background radiation, offering a snapshot of the universe's early history. But here's the fascinating part. The particle horizon is constantly growing. As the universe continues to expand, more regions become observable, allowing us to glimpse ever farther corners of the cosmos. With each passing moment, the observable universe extends further, revealing more of the universe's intricate tapestry. On the other hand, the event horizon paints a different picture. It draws a line around our universe, not from the past, but from the future. This boundary marks the limit beyond which events will forever remain hidden from our view. As the universe accelerates in its expansion, more and more regions will slip past this horizon, effectively disappearing from our observation. This will result in an observable universe that over time shrinks in size. This idea raises profound questions about the ultimate fate of the universe. Will we one day be left in a cosmic void, unable to witness the events unfolding in distant realms? The study of cosmic horizons is central to our understanding of cosmology. These horizons help astronomers and physicists piece together the history and evolution of the universe. By studying them, scientists can test theories about the early universe, the formation of galaxies, and the mysterious nature of cosmic expansion. More intriguingly, cosmic horizons offer a window into concepts like dark energy, a force driving the universe's accelerated expansion. Understanding these horizons allows scientists to grasp the dynamics that govern not just the structure of the universe, but also its potential fate. Yet, cosmic horizons are more than just theoretical concepts. They force us to confront the limitations of human observation. They highlight the fact that there are vast stretches of the universe beyond our reach, beyond our comprehension. The expansion of the universe has an unsettling yet awe-inspiring effect on our ability to observe distant objects. Galaxies, once within our grasp, are no longer just moving away from us. They are becoming increasingly distant as time marches on. This stretching of space itself leads to a phenomenon known as redshift. The very fabric of space is expanding, and as it does, light from distant galaxies is stretched as well. This stretching causes the wavelengths of light to elongate, pushing them toward the red end of the electromagnetic spectrum. What does this mean for us? Objects billions of light years away may have emitted their light long before the universe reached its current size. When that light finally reaches Earth, it's often no longer the same. What was once visible light might now be infrared or even microwave radiation. This shift complicates how we detect distant galaxies. Traditional optical telescopes designed to observe light within the visible spectrum may miss these objects entirely. Instead, astronomers must turn to more specialized instruments that can detect the longer wavelengths of light, such as infrared telescopes, in order to peer deeper into the distant reaches of space. Ultimately, cosmic horizons shape not just our understanding of the universe's structure, but also our perception of space and time. They remind us of the vastness of the cosmos and our small place within it. Every discovery, every observation reveals just how much more is out there, just beyond the reach of our current capabilities. The boundaries of the observable universe are constantly shifting, leaving us with an ever-expanding frontier to explore, even as some regions drift beyond our sight forever. As the universe continues to expand, the increasing distance between galaxies brings with it profound consequences. Not only are galaxies moving farther apart, but they are also drifting beyond the reach of our observations, leaving us with a cosmos that is ever more elusive. Over time, as these galaxies soar away from each other, some will cross the threshold of our observable horizon, effectively vanishing from view. This phenomenon marks the beginning of a universe that will become progressively darker and more sparsely populated. As more and more galaxies retreat beyond our observational limits, the very fabric of the cosmos will seem to fade into obscurity. Yet, this cosmic dance is more than just a loss of sight. It is a challenge to our understanding of the universe itself. Our current technological capabilities, including powerful instruments like the Hubble Space Telescope, have allowed us to peer deeper into the universe's past than ever before. These observations have granted us glimpses into the universe's infancy, capturing the moments of its earliest stages. But as the universe continues to expand at an accelerating rate, the future of such observations is in jeopardy. What we perceive now could be drastically different in the coming eons, pushing the very limits of our comprehension. One of the most fascinating features in this ever-expanding universe is the existence of vast cosmic voids. Among the largest of these voids is the Great Void, also known as the Giant Void or Central Void. This extraordinary expanse spans approximately 100 million light-years across, making it one of the most remarkable structures in the universe. Located at the heart of the local supercluster, it is a region where galaxies are few and far between, providing a striking contrast to the densely packed clusters that surround it. These voids are not entirely devoid of matter. While the density of galaxies within them is much lower than in other parts of the universe, there are still scattered clusters of stars and galaxies. Such voids are the result of gravitational interactions on the grand scale, forming as a byproduct of the universe's large-scale structure. Over billions of years, matter has clumped together under gravity, forming galaxies, clusters, and superclusters. In the areas where matter fails to accumulate, vast empty spaces emerge. Spaces like the Great Void. The Great Void stands as a testament to the universe's complex and intricate structure. It highlights how the cosmos is not just a random scattering of matter, but a finely woven tapestry, where dense regions of galaxies are surrounded by vast, empty expanses. These voids are not passive. They actively shape the movement and distribution of galaxies, playing a crucial role in the way matter is organized on a grand scale. Studying the Great Void, then, is not merely an exploration of emptiness, but a journey into the deeper mechanisms of cosmic evolution. The insights we gain from these vast, empty spaces help unravel the mysteries of the universe's past. By studying the voids, researchers are also uncovering clues about the presence and distribution of dark matter and dark energy, two of the most elusive and mysterious forces in the universe. As our tools and techniques for observation improve, the study of these cosmic voids is opening new windows into the forces that govern the universe's evolution. At the heart of our understanding of the universe's age and history lies the concept of cosmic expansion. Astronomers have long relied on a combination of observational data and theoretical models to measure the age of the universe. One of the most critical tools in this process is the Hubble constant, which quantifies the rate at which galaxies are moving away from us due to the expansion of space itself. By studying the redshift of light from distant galaxies, astronomers can calculate how long it has taken for those galaxies to reach their current positions, offering a glimpse into the timeline of the universe's expansion. Another crucial element in determining the age of the universe is the analysis of cosmic microwave background, CMB, radiation, the faint afterglow of the Big Bang. This radiation, which is detected almost uniformly across the sky, contains vital information about the universe's early conditions. The temperature fluctuations in this radiation reflect the density variations that existed in the early universe, providing astronomers with a way to infer the density and composition of the universe. By studying these fluctuations, scientists can refine their models of the universe's evolution, leading to increasingly accurate estimates of its age. These methods, from the study of cosmic voids to the analysis of the CMB, allow us to piece together the universe's history, not just as a distant, static entity, but as a dynamic and evolving system. Each discovery, each observation, is a small step towards understanding the forces and processes that have shaped the cosmos. As the universe continues to expand, our understanding of its past, present, and future will only grow deeper, illuminating the complexities of existence on a cosmic scale. Astronomers focus their attention on some of the oldest stars known to humanity to uncover the age of the universe itself. These stars, called population 2 stars, are found within globular clusters and offer crucial insights into the universe's timeline. Because these ancient stars formed soon after the Big Bang, studying them can provide a minimum age for the universe. Current estimates suggest that the universe is approximately 13.8 billion years old, a figure derived through a blend of detailed measurements and sophisticated models. This collaboration between observational data and theoretical physics allows scientists to piece together a more complete understanding of the universe's history. As technology advances and our ability to observe the cosmos improves, astronomers continually refine their models and measurements. This ongoing effort not only sharpens our knowledge of the universe's age, but also illuminates its intricate and complex evolution over time. One of the key theories that helps explain the universe's early development is cosmic inflation. This theory proposes that immediately after the Big Bang, the universe underwent an incredibly rapid expansion. In just a fraction of a second, approximately 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds after the Big Bang, the universe expanded exponentially. This expansion was so swift that it transformed the cosmos from subatomic scales to a size comparable to a grapefruit, altering the universe's dimensions in mere moments. The concept of inflation is critical in solving several profound mysteries about the universe. It helps explain the large-scale uniformity, flatness, and distribution of cosmic structures we observe today. Before the theory of inflation was proposed, scientists struggled to understand why distant regions of the universe seemed so strikingly similar in terms of temperature and density, despite being too far apart to have exchanged any information. Cosmic inflation offers a solution. It suggests that these regions were once much closer together before being rapidly separated by the swift expansion. This idea provides a compelling explanation for the uniformity seen in the cosmic microwave background radiation, a relic of the early universe. Cosmic inflation, a crucial phase in the early moments of the universe, is more than just a theory of expansion. It provides a comprehensive framework for understanding the vast structure of the cosmos. During this period, quantum fluctuations in the very fabric of space-time were stretched to macroscopic scales, seeding the density variations that would eventually evolve into the galaxies, stars, and clusters we see today. Without inflation, the universe as we know it would lack the intricate distribution of matter that has shaped its present form over billions of years. But inflation's implications reach far beyond merely explaining the observable size of the universe. It has profound effects on how we understand the cosmos as a whole. It suggests that our universe, with all its complexity and vastness, could be just one of many within a grander, more enigmatic structure, the multiverse. This bold and exciting idea continues to inspire astronomers and physicists alike as they explore the mysteries of our universe's origins and its ongoing evolution. In the pursuit of these mysteries, astronomers employ various techniques to measure distances and map the vast reaches of space. One of the most fundamental methods is parallax, which allows us to calculate the distances to nearby stars with remarkable accuracy. By observing the apparent motion of stars against the distant background of other celestial objects, such as more distant stars or galaxies, astronomers can track how their positions change as the Earth orbits the Sun. Parallax is based on simple geometry. As Earth shifts in its orbit, nearby stars appear to move relative to more distant objects, creating a measurable shift in their position. This shift, or parallax angle, provides the key to unlocking the star's distance from Earth. To measure this angle, astronomers take two observations of a star, spaced 6 months apart, when Earth is on opposite sides of its orbit. The baseline distance between these 2 points, essentially the diameter of Earth's orbit, forms the foundation for the calculations. Using basic trigonometry, astronomers can then apply a formula to determine the distance to the star. The parallax angle plays a pivotal role. A smaller angle means the star is farther away, while a larger angle indicates it is closer. The distance to a star is measured in parsecs. 1 parsec is the distance at which 1 astronomical unit subtends an angle of 1 arcsecond. This technique is highly effective for stars within approximately 300 light-years of Earth, but as stars grow more distant, the parallax angle becomes smaller and harder to measure accurately. This limitation has been addressed through technological advancements. Space-based telescopes like the Gaia spacecraft have significantly enhanced the precision of these measurements, allowing astronomers to refine our understanding of star distances and consequently the structure of the Milky Way and beyond. Parallax remains a cornerstone of astrometry, offering a direct link between geometry and the exploration of the cosmos. At a larger scale, the local group of galaxies provides insight into the complex structure of the universe. This collection includes our own Milky Way, the Andromeda Galaxy, and about 50 smaller galaxies, all bound together by gravity. Spanning roughly 10 million light-years, the local group is a key part of the Virgo supercluster, a massive collection of galaxies that forms one of the primary building blocks of the universe. Within the local group, the Milky Way and Andromeda are the 2 dominant galaxies, with numerous smaller companions, such as the Magellanic Clouds, orbiting them. Though modest in size compared to the entire cosmos, the local group plays an essential role in shaping the universe's overall structure. Galaxies cluster together, and these clusters in turn form superclusters, creating an intricate network of filaments and voids that characterize the large-scale architecture of the cosmos. Gravitational interactions within the local group influence the dynamics of its member galaxies, impacting their motion and future evolution. For example, the Milky Way and Andromeda are on a collision course, set to merge in approximately 4 billion years. These kinds of interactions are pivotal for understanding galaxy formation, star birth, and the mysterious role that dark matter plays in shaping the clusters of galaxies. By studying the local group, astronomers gain valuable insights into how galaxies form, evolve, and interact on larger scales. Observations of our immediate cosmic neighborhood not only illuminate the processes that govern galaxy dynamics, but also help to piece together the broader narrative of the universe's history. Through this lens, smaller groups like the local group are seen as vital components of the universe's intricate tapestry, offering clues to the larger, more expansive story of the cosmos. The conditions near the surface of a neutron star are among the most extreme and hostile environments in the entire universe. Neutron stars are born from the remnants of massive stars that have gone through catastrophic supernova explosions. When these stars collapse under their own immense gravity, they form a dense core primarily composed of neutrons along with other exotic particles. A typical neutron star has a mass greater than the Sun's, yet it is squeezed into a sphere that is only about 10 kilometers in radius. This extreme density creates a surface gravity that is 2 billion times stronger than that of Earth. The gravitational pull near a neutron star is so intense that it warps the very fabric of space and time, as predicted by Einstein's theory of general relativity. This results in some mind-bending phenomena. For instance, the escape velocity at the surface of a neutron star exceeds the speed of light, creating an environment where traditional physics no longer holds. In this space, time itself behaves differently, a phenomenon known as gravitational time dilation. The surface temperature of a newly formed neutron star can reach over 1 million degrees Celsius. While this temperature gradually decreases over time as the star cools, even older, cooler neutron stars still radiate significant amounts of X-rays. The surface of a neutron star is believed to be made of a solid crust of molten iron, under which lies a superfluid ocean of neutrons. Beneath this crust, the core may contain exotic forms of matter that are entirely unlike anything we can observe on Earth. Moreover, neutron stars often generate magnetic fields that are 1 trillion times stronger than Earth's magnetic field. These magnetic fields can accelerate charged particles to high speeds, producing beams of radiation. As these beams sweep across the sky, they can be detected as pulses of energy, giving rise to the phenomenon known as pulsars. The combination of intense density, gravity, temperature, and magnetic fields makes neutron stars one of the most fascinating and mysterious subjects of study for astronomers, offering deep insights into fundamental physics under conditions that are simply unattainable on our planet. In contrast, the core of the Sun reaches temperatures of around 15 million degrees Celsius. This incredible heat is produced through the process of nuclear fusion, where hydrogen nuclei collide and fuse to form helium, releasing vast amounts of energy in the form of light and heat. This fusion process powers the Sun and sustains life on Earth. Directly measuring the temperature of the Sun's core is impossible due to its dense and opaque outer layers. However, scientists have developed clever techniques to estimate these temperatures indirectly. One of the primary methods involves studying solar oscillations, vibrations that travel through the Sun, often referred to as heliosysmology. These oscillations are similar to sound waves, and by analyzing their patterns and frequencies, scientists can infer details about the Sun's internal structure. Different layers of the Sun, including its core, reflect these waves in distinct ways, allowing researchers to create models that reveal temperature and pressure at various depths. In addition to helioseismology, researchers also apply theoretical models of stellar evolution to estimate the Sun's core temperature. These models simulate how stars like the Sun evolve over time, taking into account variables such as mass, luminosity, and chemical composition. By refining these models with observational data, scientists can make highly informed estimates about the core temperature and other key properties of the Sun. In the quest to unlock the mysteries of the universe, scientists on Earth have turned to experimental fusion laboratories to simulate the intense conditions that exist in the Sun's core. By studying the behavior of hydrogen under immense pressure and temperature, they can validate their models of the fusion processes that fuel our star. These experimental techniques, combined with theoretical models, bring us closer to understanding the extreme conditions deep within the Sun, bridging the gap between observation and theory. While the Sun may be the star of our solar system, it's not the only celestial body to host extreme environments. The planets themselves provide a stunning array of atmospheric phenomena, each one unique in its composition and behavior. Take, for example, Jupiter's Great Red Spot. This enormous storm, larger than Earth itself, has been raging for centuries, its winds roaring at speeds of over 400 kilometers per hour. The storm's striking reddish hue results from complex atmospheric chemistry, creating a spectacle that has fascinated scientists and stargazers alike. Not far from Jupiter, Saturn offers a particularly mind-boggling weather system, a hexagonal storm at its north pole. This unusual formation, spanning roughly 25,000 kilometers, features swirling winds that reach speeds of up to 225 kilometers per hour. As the seasons change, so too does the storm's behavior, with its shape and dynamics shifting in response to Saturn's unique meteorological cycles. Mars, with its thin atmosphere, presents one of the most dramatic weather phenomena in the solar system: planet-wide dust storms. These storms can engulf the entire planet, sometimes lasting for weeks on end. They can drastically reduce visibility and alter surface temperatures. The largest of these storms can even cause a rise in the global temperature by several degrees Celsius, turning the Martian landscape into an inhospitable and volatile environment despite its overall cold climate. Venus, a planet cloaked in thick clouds of sulfuric acid and composed mainly of carbon dioxide, offers yet another extreme atmospheric phenomenon. Its surface temperatures hover around 460 degrees Celsius, and its atmospheric pressure is a crushing 92 times that of Earth's, creating a surface environment reminiscent of the deepest ocean trenches on our planet. In Venus's atmosphere, winds move much faster than the planet's rotation, generating superrotational weather patterns that add another layer of complexity to this hostile environment. These diverse and extreme weather systems across our solar system provide an unprecedented window into the unique atmospheres of other worlds. By studying these phenomena, we gain a deeper understanding of the immense variety of conditions that exist beyond Earth, revealing the vast complexity of our cosmic neighbors. Beyond the boundaries of our solar system, in the depths of space, temperatures plummet to almost incomprehensible lows. The average temperature of the cosmos hovers just above 2.7 Kelvin, a mere whisper above absolute zero, equivalent to around minus 270 degrees Celsius. This incredibly cold environment serves as a backdrop to the endless mysteries of the universe, where even the most extreme weather phenomena are just a small part of the cosmic puzzle. However, in certain regions of space, especially where vast expanses are devoid of matter, temperatures can approach absolute zero, a theoretical state where the motion of molecules completely halts. The coldest known location in the universe was discovered in a region of the Boomerang Nebula, where temperatures plummet to around minus 272 degrees Celsius. This nebula is located approximately 5,000 light years from Earth. The extreme cold in the Boomerang Nebula is largely due to the rapid expansion of gas ejected from the dying star at its center, cooling as it expands. This unique combination of factors allows the nebula to reach such frigid temperatures. On Earth, scientists have been able to replicate similarly low temperatures in controlled laboratory settings, especially through experiments involving laser cooling techniques. In these settings, temperatures have been reduced to within a billionth of a degree above absolute zero. Such extreme cold offers researchers the opportunity to study quantum mechanical effects, allowing deeper insights into the behavior of matter under conditions that are far beyond everyday experience. These investigations into the cold expanses of space not only contribute to our understanding of the cosmos, but also reveal the fascinating processes that take place within it. They help astronomers and physicists uncover the fundamental principles that govern the universe, from the behavior of atoms at near absolute zero to the forces shaping distant nebulae. As we explore these areas, we are reminded of the incredible extremes that exist beyond our warm, comfortable world. Standing on the surface of Venus, by contrast, would be an astonishing experience, but one that is completely hostile and inhospitable to humans. Often referred to as Earth's twin due to its similar size and proximity, Venus offers a starkly different reality. The atmosphere of Venus is mainly composed of carbon dioxide, with clouds of sulfuric acid adding to the oppressive conditions. The runaway greenhouse effect traps immense heat, raising the surface temperature to around 460 degrees Celsius, hotter than Mercury, despite Venus being farther from the Sun. The atmospheric pressure on Venus is approximately 92 times that of Earth, equivalent to the pressure found nearly 1 kilometer beneath the Earth's oceans. This crushing pressure would obliterate any human or spacecraft not designed specifically to withstand it. The thick clouds obscure the surface from direct sunlight, creating an almost constant overcast sky where visibility is limited to just a few meters. Although the clouds are made of sulfuric acid droplets that rain down, they evaporate before reaching the surface due to the searing heat. Despite these extreme conditions, Venus's landscape is surprisingly varied. It features mountain ranges, vast volcanic plains, and massive volcanic structures. Some scientists believe Venus may still have active volcanoes, with recent studies hinting at potential volcanic activity. The rocky terrain, however, is barren, showing no signs of water or life as we know it. In addition to the extreme temperatures and pressures, the chemical composition of the atmosphere is highly toxic, with corrosive clouds and an abundance of dangerous gases that pose serious challenges for any exploratory mission. In summary, standing on Venus would be a surreal experience, one bathed in a hellish environment, an experience that starkly contrasts with the warmth and comfort of Earth. Venus serves as a potent reminder of how drastically planetary conditions can differ within our own solar system. Although the planet continues to be an object of significant scientific interest, it presents immense challenges for exploration and remains inhospitable to life as we understand it. In the crowded centers of globular clusters, stars manage to thrive despite the intense density of stars and the gravitational interactions surrounding them, thanks to several fascinating mechanisms. Globular clusters are tightly packed collections of stars, often containing hundreds of thousands to millions of them, all contained within a relatively small area of space. This extreme concentration of stars leads to frequent gravitational interactions, which can result in various stellar behaviors. One of the key factors that allows stars to survive in such environments is their ability to maintain stability, even when they encounter other stars at close range. While these gravitational interactions can result in the ejection of some stars from the cluster or cause them to merge with others, many stars find a balance that enables them to remain in stable orbits around the cluster's center. The gravitational potential well of the cluster acts to hold stars in place, preventing them from spiraling into the center or being flung outward. Another key process at play in globular clusters is known as dynamical relaxation. Over time, stars within the cluster interact with each other, redistributing their velocities and energies through a series of close encounters. This process leads to a more stable configuration, allowing stars to settle into predictable orbits. While these interactions can occasionally lead to violent outcomes, such as the formation of binary star systems or even supernovae, many stars find equilibrium and continue to coexist within the dynamic environment of the cluster. Globular clusters, fascinating celestial entities scattered across the universe, are more than just dense collections of stars. Many of them are ancient, some even older than our solar system itself, containing stars with a strikingly low metallicity compared to those found in other regions. This characteristic has profound effects on the lifetimes of the stars within them, often granting them extended lifespans. These low metallicity stars tend to be older red giants or yellow giants, capable of surviving for billions of years without the external influences that typically impact younger, more volatile stars. The crowded, dynamic environment of a globular cluster presents a unique backdrop for stellar evolution. Here, stars interact gravitationally, influencing one another in ways that shape their fates. This delicate interplay between gravity, stellar collisions, and evolutionary processes allows stars to flourish in an environment where resources are scarce, yet competition is fierce. Ultimately, these stars persist, continuing their slow, steady burn for eons, unaffected by the external forces that might otherwise disrupt their existence. Beyond the glittering clusters of stars lies the vast and empty expanse of interstellar space, a realm vastly different from the bustling regions where stars and planets form. The vacuum between the star systems in a galaxy is nearly devoid of matter, with an average density of about 1 atom per cubic centimeter. In such conditions, the environment is starkly removed from the high-energy, high-density conditions found in the interiors of stars or planetary atmospheres. Yet, this emptiness is not devoid of significance. While most of interstellar space is barren, it is not entirely absent of elements. The majority of the gas in this region is composed of hydrogen and helium, with trace amounts of heavier elements scattered throughout. In certain regions, however, pockets of higher density material known as molecular clouds can form, providing the raw ingredients for new star formation. These clouds are rich in dust and molecules that serve as the building blocks for stars and planetary systems. Temperatures in interstellar space vary dramatically, but they are typically extremely cold. The average temperature hovers around 7 Kelvin, the temperature of the cosmic microwave background radiation that permeates the universe. Within denser molecular clouds, however, temperatures can rise significantly, sometimes reaching several tens of degrees Kelvin. This pervasive cosmic background radiation is a relic from the Big Bang, a faint glow that infuses the cosmos with a dim, universal light. Interstellar space is also home to high-energy cosmic rays, fast-moving particles that travel at nearly the speed of light. These rays, primarily protons and atomic nuclei, originate from distant cosmic events such as supernovae and active galactic nuclei. While they are a natural part of the cosmic environment, they can pose a significant threat to spacecraft and astronauts, making their study an essential part of space exploration. Magnetic fields, along with dynamic forces from nearby stars and supernova remnants, also influence the conditions of interstellar space. These forces can impact the movement of particles and alter the local environment, creating a constantly evolving landscape. Despite its vast emptiness and extreme cold, interstellar space plays a pivotal role in the grand scale of the universe, offering a unique setting for the ongoing processes of star formation and cosmic evolution. The study of interstellar space also deepens our understanding of the very fabric of the cosmos. It opens up profound insights into the dynamics of the universe, from the birth of stars to the expansive nature of galaxies. By exploring this seemingly desolate expanse, scientists are unraveling the mysteries of how matter and energy behave on an interstellar scale, shedding light on the fundamental processes that govern our universe. On Earth, extremophiles, organisms that thrive in extreme environments, provide a valuable window into the possibilities of life beyond our planet. These resilient creatures survive in conditions that would be inhospitable to most other forms of life, such as extreme temperatures, high radiation levels, acidic or alkaline environments, and crushing pressures. By studying these organisms, scientists expand their understanding of what constitutes a viable habitat, which is crucial for the field of astrobiology, the search for life beyond Earth. One of the most remarkable groups of extremophiles are thermophiles, bacteria that thrive in environments of extreme heat, such as hot springs and hydrothermal vents. These organisms have evolved specialized enzymes and cellular structures that allow them to function optimally in temperatures that would denature the proteins of most life forms. The study of thermophiles informs the search for life on other worlds, such as Europa, one of Jupiter's moons, and Enceladus, a moon of Saturn, both of which are believed to harbor subsurface oceans beneath their icy crusts, potential habitats for similar heat-loving life forms. Another fascinating group of extremophiles are halophiles, organisms that thrive in highly saline environments, such as salt flats or salt mines. These resilient creatures provide valuable insights into how life might exist in environments with high salt concentrations, which could be relevant for understanding the conditions on planets like Mars or in the subsurface oceans of icy moons, where salinity levels may fluctuate dramatically. The biochemical adaptations of halophiles help astrobiologists gauge which metabolic processes might be possible in extraterrestrial environments with extreme salinity. These studies not only deepen our understanding of life on Earth, but also expand the possibilities for life elsewhere in the universe. By investigating the extremes to which life can adapt, scientists are uncovering clues that may one day help us find life in the most unlikely places, whether it be on distant exoplanets or the hidden oceans of icy moons scattered across our solar system. Through the lens of extremophiles, the search for life beyond Earth becomes a journey into the unknown, where the boundaries of life as we know it are constantly being pushed to new extremes. Life on Earth is already full of remarkable survival stories, but some organisms defy our expectations in ways that stretch the boundaries of what we thought possible. Take, for example, certain types of bacteria found in the Chernobyl exclusion zone. These microorganisms have evolved to thrive in environments saturated with intense radiation, surviving where most life forms would perish. Their resilience not only fascinates scientists, but offers key insights into how life could exist on planets or moons in space, environments that might face constant bombardment by cosmic rays or solar flares. These extremophiles, as they're called, offer a glimpse of hope in our search for life elsewhere in the universe. By understanding their genetic and biochemical makeup, researchers are refining their theories on habitability in conditions far harsher than anything Earth has to offer. If life can survive in Chernobyl's radioactive wasteland, could it also endure on distant worlds with harsh environments, like the surface of Mars, the moons of Jupiter, or even further into the far reaches of space? This growing body of knowledge is critical for the future of astrobiology, shaping the way we design missions to search for extraterrestrial life. It fuels optimism, especially when considering the possibility of finding life in the most unlikely of places, perhaps on planets bathed in radiation, far from the protective embrace of a sun. The more we learn about extremophiles, the better we can predict what forms of life might exist beyond Earth, across our solar system, and even in galaxies light years away. Radiation in our solar system is far from uniform, and its presence fluctuates depending on where you are and the protective forces at play. Close to the sun, radiation levels are incredibly high, influenced by a constant stream of charged particles from the solar wind. This solar wind, a continuous outflow of energized protons, electrons, and electromagnetic radiation, plays a dominant role in the environment of the inner solar system. In fact, regions closest to the sun, like Mercury and Venus, are exposed to levels of radiation that would be lethal to most life forms without protection. Mercury, for example, lacks a meaningful atmosphere to shield it from the sun's radiation, resulting in extreme temperature fluctuations. The planet scorches under intense heat during the day and freezes at night. Venus, though shrouded in thick clouds, still faces dangerous radiation levels. These harsh conditions make human exploration of Venus highly challenging, if not impossible. As we move outward in the solar system, Earth's atmosphere and magnetic field provide us with a crucial shield from radiation. The atmosphere absorbs much of the sun's harmful ultraviolet radiation, while Earth's magnetic field deflects solar wind and cosmic rays. But even our planet's defenses are not foolproof. Beyond Earth's protective layers, radiation levels begin to climb, especially as we venture higher into the atmosphere and into space itself. Out beyond Earth, radiation risks intensify, particularly around the gas giants like Jupiter and Saturn. Jupiter's immense magnetic field, generated by the planet's dynamo effect, captures high-energy particles from the solar wind and traps them in radiation belts. These Van Allen belts, named after the scientist who first discovered them, contain radiation levels that are extreme and potentially deadly to spacecraft. Without the proper shielding, any human explorers traveling to Jupiter would be at immense risk. The farther we venture into the outer solar system, the radiation levels gradually decrease. In regions like the Kyper Belt, the density of cosmic radiation and solar wind drops, creating a much more hospitable environment. The distant reaches of space offer a more benign radiation climate, at least compared to the radiation-laden regions near the sun. Understanding these variations in radiation is crucial for the future of space exploration. Knowing where the radiation is high, where it's low, and how to protect against it can guide the design of spacecraft and help ensure the safety of astronauts as they venture beyond our home planet. It also informs our knowledge of habitability. If radiation is a barrier to life in some regions of the solar system, it may explain why we haven't found life in those places, or help us identify areas where life could thrive. Gas giants like Jupiter are particularly fascinating in this regard, thanks to the massive magnetic fields they generate. Jupiter's magnetic field, for instance, is 20 times stronger than Earth's and extends far beyond the planet's surface. This field is the result of a process known as the dynamo effect, a natural mechanism that occurs deep within a planet. In Jupiter's case, the combination of rapid rotation, conductive materials, and heat-driven motion creates a powerful magnetic field. The key to Jupiter's magnetic strength lies in its interior, particularly its metallic hydrogen core. Under the extreme pressure and temperatures inside the planet, hydrogen becomes metallic, a state that is highly conductive. As Jupiter rotates rapidly, completing one full rotation every 10 hours, this metallic hydrogen moves and flows in turbulent currents. These currents generate electric currents, which, in turn, create magnetic fields. The interaction between the movement of these conductive fluids and the planet's rapid rotation amplifies the magnetic field, making it one of the most powerful in the solar system. In essence, Jupiter's magnetic field is a product of both the dynamo effect and the planet's internal composition. As a result, this magnetic field not only shapes the environment around Jupiter, but also influences the solar system itself, extending far beyond the gas giant and into the space around it. The power of this magnetic field, while a protective force for Jupiter, is also a reminder of the extreme and complex nature of the solar system's radiation environment. Jupiter's magnetic field is not just strong, it is immense, shaping the very fabric of space around the gas giant in ways that are both awe-inspiring and complex. This field dominates a vast region known as the magnetosphere, extending millions of kilometers into space. The magnetosphere serves as a shield, capturing charged particles from the solar wind and generating a dynamic environment rich with cosmic phenomena. One of the most striking consequences of this magnetic force is the formation of auroras near Jupiter's poles, radiant displays of light, much like Earth's auroras, but orders of magnitude more powerful. In fact, these interactions create radiation belts that dwarf the Van Allen belts surrounding Earth, radiating energy far beyond anything we experience on our home planet. Exploring the depths of Jupiter's magnetosphere offers far more than just a glimpse into the behaviors of a distant planet. It provides valuable insights into the internal structure and dynamics of gas giants, offering a broader understanding of magnetic processes that likely occur on similar worlds, both within and beyond our solar system. Studying Jupiter, therefore, not only enriches our knowledge of this giant planet, but also deepens our grasp of the forces that govern other celestial bodies. Now, turning to gravity, one of the most profound forces shaping our universe, it holds a remarkable ability to influence the passage of time itself. This concept, first laid out by Albert Einstein in his theory of general relativity, suggests that mass does more than just exert force on objects. It bends the very fabric of spacetime, the four-dimensional continuum that merges space and time into a single entity. The more mass a body has, the more it warps this fabric, and in turn, the more time is affected. In practical terms, time does not flow at the same rate everywhere. In regions of stronger gravitational fields, time moves slower compared to places where gravity is weaker. For instance, a clock placed at sea level, where Earth's gravitational pull is strongest, will tick ever so slightly slower than a clock placed at higher altitudes, where gravity is weaker. This effect is so minute that only the most precise atomic clocks can measure the difference, but the discrepancy perfectly aligns with the predictions of Einstein's theory. However, the most dramatic example of gravity's influence on time is found near supermassive objects like black holes. As one approaches a black hole's event horizon, the gravitational pull becomes so intense that time dilation intensifies. For an observer far away from the black hole, time appears to slow down dramatically for anything near the event horizon. If a spaceship were to orbit a black hole, the crew would experience time at a vastly different rate than someone watching from a distant, safer location. This is more than just a cosmic curiosity. It has practical consequences here on Earth, particularly in the realm of modern technology. The Global Positioning System, GPS, for example, relies on satellites orbiting Earth. These satellites experience both gravitational time dilation due to their higher altitude and relativistic time effects because of their speeds. To keep GPS systems accurate, two sets of corrections are applied to the satellite clocks, one to account for their altitude and the other for their velocity. This ensures that the satellite clocks remain in sync with those on the ground, demonstrating that time's relationship with gravity is not only a theoretical concept, but one that impacts the technologies we use daily. Ultimately, the relationship between gravity and time reshapes our very understanding of the universe. It reveals how the presence of mass alters the very fabric of reality itself. In Einstein's revolutionary model, the concept of space-time unifies the three dimensions of space, length, width, and height, with time into a single, intertwined continuum. Before his work, space and time were seen as separate, independent dimensions. But through his theories of special and general relativity, we now understand that they are deeply interconnected, and their behavior is dramatically altered by the forces that shape the cosmos. Einstein's framework revolutionizes our understanding of the universe, presenting an intricate, interconnected view where time and space are not separate entities, but are woven together in a single, unified structure: space-time. In this four-dimensional model, every event in the cosmos is described not just by its location in space, but also by when it occurs. To pinpoint an event in space-time, you must account for both its spatial coordinates and its temporal moment. This fusion leads to some extraordinary, often mind-bending consequences. Take, for instance, the concept of time dilation. Time does not pass at a constant rate for all observers. Instead, the speed at which time flows depends on two factors: the relative motion of the observer and the strength of the surrounding gravitational field. This phenomenon, which can be demonstrated in the behavior of satellites in orbit, reveals that time can stretch or shrink depending on where and how you are situated in the universe. For example, clocks on satellites move slightly slower than those on Earth due to the differences in gravitational pull and velocity. Moreover, space-time drastically reshapes our perception of gravity. Traditionally, we think of gravity as a force that acts across space, pulling objects toward one another. But under Einstein's theory, gravity is not a force in the conventional sense. Instead, it emerges from the curvature of space-time, caused by the presence of mass. Imagine space-time as a fabric, with massive objects like stars or planets sitting on it like heavy balls. The mass of these objects distorts the fabric, creating indentations that cause smaller objects, like moons or spacecraft, to move along curved paths. This explains why planets orbit stars and why objects fall toward the Earth. They are simply following the curves in space-time, which are created by the planet's mass. This rethinking of gravity also opens the door to some of the most profound mysteries of the universe. Concepts like black holes, where space-time becomes so distorted that even light cannot escape, challenge the boundaries of our understanding. In these regions, the laws of physics as we know them cease to function in the way we expect. And then there is the expansion of the universe itself, an idea that is intricately tied to the fabric of space-time. The way the universe is stretching, with galaxies moving away from one another, is a direct consequence of the geometry of space-time. This framework does more than just deepen our grasp of gravity and motion. It has transformed our approach to cosmology, fundamentally shaping how we think about the universe's origin, structure, and future. The scientific journey through the cosmos has, in many ways, become a journey through space-time itself. For astronomers, the concept of space-time offers a unique ability, the ability to look back in time. When observing distant stars and galaxies, they are not seeing them as they are in the present moment, but rather as they were in the past. This is because light, which travels at a finite speed of about 300,000 kilometers per second in a vacuum, takes time to reach Earth. The farther away an object is, the longer its light takes to arrive. For instance, a star that is 10 light years away is seen by astronomers not as it is today, but as it was 10 years ago. This time delay becomes even more significant when astronomers observe galaxies billions of light years away. The light they are studying left those galaxies billions of years ago, allowing scientists to witness cosmic phenomena that occurred in the distant past. This time machine effect provides a unique opportunity to study the universe's evolution, tracing its history back to its early stages all the way to the Big Bang itself. Telescopes, particularly advanced instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope, play an indispensable role in this exploration. These instruments can detect light across a wide range of wavelengths, visible, ultraviolet, and infrared, giving astronomers the ability to peer deeper into the cosmos, unlocking new insights into the universe at different points in time. For example, by studying the light emitted from ancient galaxies, scientists can understand when they first formed, how they have developed over time, and what they might look like in the future. By looking at the distant past, astronomers can study cosmic events like the formation of stars, supernova explosions, and even the moments immediately following the Big Bang. The cosmic microwave background radiation, an echo from the universe's birth, provides a snapshot of what the cosmos looked like when it was just a few 100,000 years old, offering valuable clues about its evolution. This ability to look back in time also allows scientists to test and refine their theories about the universe. It provides a means to challenge existing models, develop new ones, and answer some of the most fundamental questions of existence. What is the true nature of dark matter and dark energy? What is the ultimate fate of the universe? By piecing together data from distant objects across the universe, astronomers can map out the cosmic timeline, revealing the universe's growth from its infant stages to its present state. Ultimately, the study of the cosmos through the lens of space-time opens up an ongoing dialogue with the universe, providing a window into its deepest mysteries. Each discovery, each observation brings us closer to understanding the intricate relationships between time, space, and matter, reshaping our view of the world around us and our place within it. Imagine compressing the entire history of the universe into a single calendar year. This is the concept behind the cosmic calendar, a mind-expanding tool that allows us to visualize the vast timeline of the cosmos in a format we can comprehend. From the birth of the universe to the rise of humanity, the cosmic calendar condenses the grand narrative of time into a single, relatable structure. In this conceptual model, the universe's 14 billion years of existence is scaled down to just 365 days, with each passing day representing over 38 million years of cosmic history. We gain an entirely new perspective on the timing of key events. It begins at midnight on January 1st, when the Big Bang ignites the birth of the universe. From there, events unfold at a staggering pace, but each moment represents a huge leap in our understanding of the cosmos. By the end of January, galaxies and stars begin to form, with the first galaxies appearing around late February. The Milky Way itself takes shape by early May. Then, in early September, we reach the formation of our solar system, Earth included, around 4.5 billion years ago. Life on Earth begins in late September in the form of simple, single-celled organisms, marking the dawn of biological history. As the calendar pages flip into the later months, the story of life unfolds in unexpected ways. Complex, multicellular organisms begin to develop toward the end of November, and by early December, the age of the dinosaurs arrives, lasting for much of the month. The reign of these incredible creatures stretches from around 250 million years ago to their extinction about 65 million years ago, which takes place just before the final few hours of the calendar year. Then, in the final moments of December 31st, anatomically modern humans, Homo sapiens, emerge. But there's a catch. Despite the grandeur of human history, our species has only existed for a mere 200,000 years, which is nothing more than a few seconds in the vast timeline of the universe. Even more staggering is the fact that recorded human history, everything we know about civilization, comprises just the last few minutes of December 31st. This startling perspective drives home an important realization. The universe has existed for billions of years, while human history is but a fleeting moment in comparison. It's a sobering reminder of the rapid pace of change and the immense stretches of time that preceded our existence. Yet, it also offers us the opportunity to reflect on how far we've come and the interconnectedness of life itself. The cosmic calendar encourages a deeper appreciation for both the immensity of time and the fleeting nature of human life within that expanse. As we ponder the cosmos, we're confronted with not just the age of stars and galaxies, but the profound weight of our own existence. By breaking down the vastness of time into a more tangible format, we see ourselves as part of a far larger story, one that stretches across the eons, shaping and being shaped by forces far beyond our understanding.
Time dilation.
The mind-bending consequences of relativity for space travelers. Time dilation is a concept so strange it almost seems like science fiction. Yet it's an effect that is both real and predicted by Einstein's theories of relativity. When objects move at speeds approaching the speed of light or experience extreme gravitational fields, time itself bends in a way that we don't normally experience. This phenomenon has profound implications for anyone who dares to venture far into space. Imagine a group of astronauts embarking on a long journey across the cosmos. As they travel at near light speed, they experience time passing much more slowly compared to people on Earth. While the astronauts might age only a few years during their voyage, decades or even centuries could pass on Earth. This is the essence of time dilation. Time for the astronauts flows at a different rate than it does for those who remain in the stronger gravitational field of Earth. This isn't just theoretical. It has been demonstrated in real-world experiments, such as those involving atomic clocks flown aboard fast-moving aircraft or orbiting satellites. In these tests, clocks on board the fast-moving objects ticked more slowly compared to those on Earth. And while these effects may seem small, the potential consequences for future space missions are profound. Astronauts venturing into deep space at speeds nearing that of light could return to find that those they left behind on Earth have aged far more than they have. Time, as we experience it, is not the absolute constant we once thought it to be. Out there in the cosmos, it can stretch, bend, and twist in ways that defy our everyday understanding. Time dilation, a fascinating consequence of both special and general relativity, has profound implications for space exploration. This phenomenon can occur when the influence of gravity or high velocities alter the passage of time. For instance, imagine space travelers embarking on a mission to a planet with much stronger gravity than Earth's, perhaps orbiting a massive celestial body like a black hole. The gravitational pull in such a region would slow down time for these astronauts relative to those on Earth, meaning that while years might pass on Earth, they could experience only a fraction of that time in their spacecraft. This slowing of time, known as time dilation, opens up an array of intriguing possibilities and challenges, particularly in the context of planning space missions. Astronauts working in a high-gravity environment would not only experience time differently, but also find that their personal timelines diverge dramatically from the rest of humanity. For example, astronauts on such missions could age more slowly than their loved ones back home, leading to emotional and psychological complications. Decisions surrounding communication with Earth and the timing of return missions would have to account for this differential passage of time. The further the mission ventures into extreme gravitational fields or velocities approaching the speed of light, the more critical these factors become. At the heart of this discussion is the concept of proper time, a cornerstone of relativity. Proper time is the time experienced by an observer moving along with the clock, at rest relative to the observer. In space, the movement of objects and their proximity to massive gravitational sources, like black holes, influence the passage of time. If an object moves close to the speed of light, it experiences time differently than an object at rest. This phenomenon is particularly significant in special relativity. An object traveling at high speeds will measure less time passing for itself compared to a stationary observer. To the astronaut on the fast-moving spacecraft, their journey may feel like only a few months or years, while an observer back on Earth may perceive the passage of decades. Proper time represents the true experience of time for an object or observer, unaffected by external influences. In the context of general relativity, this concept extends to the effect of gravity. As gravitational fields become stronger, time itself bends. For example, a clock near the surface of a massive planet will tick more slowly than one in deep space, far from any gravitational influence. This difference in the experience of time due to gravity is crucial when considering the nature of space travel near dense objects like black holes or neutron stars. The clock in deep space, far from the gravitational pull of any large object, would measure time at a different rate than a clock closer to the gravitational source. The study of proper time and its relationship with movement and gravity provides a critical framework for understanding the dynamics of time dilation. This is not just theoretical. As humanity pushes farther into space, these principles will guide the planning of missions and the psychological preparation of astronauts. The experience of time will differ fundamentally depending on where an astronaut is located, how fast they are traveling, and how close they are to strong gravitational fields. In the end, time is no longer a constant, rigid force, but a dynamic, flexible dimension influenced by motion and gravity. By understanding how time behaves differently depending on an observer's location and speed, we gain a deeper appreciation of the universe's underlying structure. As we journey further into the cosmos, the way we experience time will continue to evolve, challenging our perception of reality and our place in the vast, ever-changing expanse of space. Atomic clocks, marvels of modern science, operate based on the fascinating principles of quantum mechanics and the intrinsic behavior of atoms. Unlike traditional clocks, which depend on mechanical components or the rhythmic motion of a pendulum, atomic clocks harness the natural oscillations of atoms to keep time with astounding precision. The key to their accuracy lies in the behavior of atoms, specifically the transitions between different energy levels. One of the most common types of atomic clocks uses cesium atoms. In these clocks, a beam of cesium atoms is directed through a microwave field. When the frequency of the microwaves matches the natural frequency of the cesium atoms, the atoms undergo a transition between two energy states. These transitions are counted, providing a consistent and reliable measure of time. The precision of atomic clocks is so high that they define the standard of a second, precisely 9,192,630,770 oscillations of the cesium atom. This standardization not only showcases the accuracy of atomic clocks, but also reinforces the trust we place in these instruments. But what makes atomic clocks truly indispensable is their role in the vast expanse of space exploration. Their ability to provide highly accurate timekeeping is essential for various space-related applications, most notably for global navigation. The Global Positioning System, GPS, relies on a constellation of satellites, each equipped with an atomic clock. These satellites constantly broadcast their position and the time the signal was sent. On Earth, devices receive these signals and calculate the time it took for the signal to travel, allowing for precise location data. The synchronization of time between the satellite and the receiver is crucial to obtaining accurate distance measurements and positioning. Beyond navigation, atomic clocks are also indispensable for cutting-edge research in physics, particularly for studies of time dilation. In the context of Einstein's theory of relativity, time dilation occurs when objects move at speeds close to the speed of light or are under the influence of strong gravitational fields. Astronauts traveling in space experience this firsthand. Time passes at different rates for them compared to those of us on Earth. By using accurate atomic clocks, scientists can measure these differences in time, providing insights into relativistic effects that are central to our understanding of the universe. Moreover, atomic clocks are vital for coordinating space missions. Whether it's synchronizing the movements of spacecraft for docking operations or ensuring consistent communication, accurate timekeeping is a cornerstone of efficient space exploration. As humanity continues its journey beyond Earth, the role of atomic clocks will only grow, ensuring that we can safely and effectively explore the solar system and beyond. The incredible influence of atomic clocks doesn't stop with our own planet or the reaches of space. Their significance stretches to the very boundaries of our understanding of time itself. Near the event horizon of a black hole, where gravity is at its most extreme, time experiences an unimaginable distortion. According to Einstein's general theory of relativity, the closer an object is to a massive body, the greater the curvature of space-time. This causes time to slow down as an object nears a black hole's event horizon, the point beyond which nothing, not even light, can escape. To a distant observer, an object approaching the event horizon would appear to slow down as it gets closer, seemingly frozen at the boundary. Light emitted from the object would be stretched to longer wavelengths, losing energy and eventually becoming undetectable, a phenomenon known as redshift. However, from the perspective of the object falling into the black hole, time would continue to pass normally. The object wouldn't notice any unusual effects on its internal clock as it crossed the event horizon, although the extreme tidal forces beyond that point would likely lead to its rapid destruction in a process called spaghettification. This stark contrast in the perception of time, one observer witnessing a slowdown and the other experiencing the passage of time without interruption, underscores a core aspect of relativity. Time is not absolute. Rather, it is shaped by the curvature of spacetime, which is determined by the mass and energy present in the universe. The bizarre nature of time near a black hole challenges our understanding of the laws of physics and raises profound questions about the nature of reality itself. What happens to information that crosses the event horizon? Does it truly vanish, or is it somehow preserved, awaiting discovery? These are the questions that atomic clocks and the study of time continue to explore as we push the boundaries of science further into the unknown. As scientists push the boundaries of our understanding, the mysteries of the cosmos continue to unfold. Among the most intriguing phenomena is the study of black holes, revealing the extreme and often mind-boggling behavior of time and space. This exploration sheds light on the universe's most profound truths, especially when we look at the expansion of the cosmos. The expanding universe has a powerful impact on how we perceive time, particularly when we view it across the vast scales of space. As the universe stretches outward, galaxies are gradually moving away from us. Interestingly, the farther away a galaxy is, the faster it seems to be receding. This phenomenon doesn't just challenge our understanding of space, it fundamentally alters our perception of time itself. Here, time and distance become inseparably linked, reshaping the very framework of cosmic chronology. A crucial aspect of this is the relationship between the distance of a galaxy and the time it takes for its light to reach us. When we observe light from a galaxy billions of light years away, we're not seeing it in the present moment. Instead, we're looking back in time, observing an image of the galaxy from millions or even billions of years ago. This time delay occurs because light takes so long to travel through the ever-expanding fabric of space to reach our eyes. By studying this delayed light, astronomers can reconstruct a timeline of the universe's evolution, piecing together events that have led to the current structure of the cosmos. This phenomenon also ties into something known as redshift, a concept that plays a pivotal role in our understanding of cosmic expansion. As light travels through the expanding universe, its wavelength stretches, shifting it toward the red end of the spectrum. The further away a galaxy is, the more its light gets stretched, a shift that provides vital clues about the universe's rate of expansion and its age. The larger the redshift, the more distant the galaxy, and the older the light we're observing. These subtle shifts in light create a complex dance between distance, time, and expansion, adding layers of complexity to our understanding of time at the cosmic scale. As the universe continues to expand, it will have long-term consequences for the fate of galaxies. Over immense time periods, many galaxies will eventually move beyond our observable horizon, receding so far that their light will no longer reach us. This could leave future civilizations or distant observers looking out at an increasingly empty sky where galaxies appear to fade away. This shift will dramatically alter their perception of cosmic time, as the universe's history fades from view. The expansion of the universe then does more than just stretch space. It reshapes our very experience of time. By intertwining time with distance, influencing the light we see from far-off galaxies, and even determining the ultimate fate of cosmic structures, the universe challenges and refines our understanding of time itself. This interconnectedness highlights the dynamic and ever-changing nature of the cosmos, offering us a deeper, more nuanced view of the universe's past, present, and future. The concept of the arrow of time further deepens our understanding of the universe's directionality. This idea posits that time flows in one direction, from the past into the future, and that certain processes in nature are irreversible. The arrow of time helps explain why events unfold in a particular order and allows us to distinguish between the past and the future. It can be understood in multiple contexts, such as thermodynamic, psychological, and cosmological arrows. The thermodynamic arrow of time is perhaps the most familiar, rooted in the second law of thermodynamics, which states that the entropy of an isolated system will always increase over time. Entropy, a measure of disorder or randomness, means that systems naturally evolve from states of low entropy, more ordered, to high entropy, more disordered. For instance, if you leave a hot cup of coffee in a cold room, it will eventually cool down, moving toward thermal equilibrium. This shift from order to disorder mirrors the universe's evolution from its birth to the present day. The arrow of time in cosmology is tightly connected to the universe's expansion. The Big Bang represents the moment when the universe began, an event marked by extreme heat and low entropy. As the universe expanded and cooled, matter began to condense into galaxies, stars, and eventually life itself. This ongoing expansion not only reflects the directionality of time, but also gives shape to the universe's past, present, and future. The further the universe expands, the higher its entropy becomes, marking the passage of time from a state of ordered beginnings to an increasingly disordered future. Through this lens, the universe's expansion isn't just a scientific phenomenon. It is a fundamental force shaping time itself, both for the universe as a whole and for every individual galaxy within it. This cosmic dance between time, distance, and entropy reveals the intricate, ever-unfolding story of the universe, a story that continues to evolve with each passing moment. The psychological arrow of time is deeply embedded in our human experience, shaped by how we perceive the flow of time. We vividly remember events from the past, yet we cannot foresee those yet to come. This perception, integral to our understanding of reality, is a reflection of how we interact with the world, where change, growth, and the continuous progression of time from past to future guide our daily lives. In the realm of cosmology, the arrow of time extends its reach, offering profound implications for how we understand the fate of the universe. As time progresses and entropy relentlessly increases, we are confronted with a chilling possibility. The universe may ultimately reach a state of maximum entropy, often referred to as the heat death. In this scenario, thermodynamic processes cease to operate, leading to a uniform distribution of energy. The result? The cessation of all physical processes as we know them, marking the universe's inevitable progression toward a cold, lifeless state. The arrow of time thus encapsulates the irreversible unfolding of events, illustrating the inevitable passage from past to future. It illuminates our comprehension of entropy and the universe's evolution, standing as a pivotal concept in both physics and philosophy. It shapes our inquiries into the nature of reality and the temporal aspects of existence itself. Meanwhile, on the far reaches of human ambition, the dream of terraforming Mars remains one of the most daunting challenges of modern science. Transforming the Martian environment to make it hospitable for human life involves a multi-layered and complex strategy that aims to change the planet's climate and atmosphere to support the basics of life: air, water, and temperature regulation. While groundbreaking scientific advancements are still needed to bring this vision to life, a number of theoretical methods have already been proposed to begin the process. A primary goal in terraforming Mars is thickening its atmosphere to provide sufficient pressure and a breathable composition for human survival. Currently, Mars's atmosphere is exceedingly thin, composed mostly of carbon dioxide, which renders the planet inhospitable. To address this, one proposed method is to introduce greenhouse gases into the atmosphere, warming the planet and increasing both surface temperatures and atmospheric pressure. Technologies that could produce gases like carbon dioxide, methane, or ammonia, potentially sourced from Mars itself or transported from elsewhere in the solar system, could play a key role in this process. Additionally, deploying giant mirrors or orbital solar reflectors to direct more sunlight toward the Martian surface could further increase heat, triggering vital atmospheric changes. But thickening the atmosphere is just one part of the puzzle. Water availability on Mars is another critical factor that must be addressed for successful terraforming. One potential approach is to melt the polar ice caps, which contain both frozen carbon dioxide and water ice, releasing these resources into the Martian environment. This process could not only increase the amount of liquid water on the surface, but also help elevate the atmospheric pressure and temperature, making the planet more hospitable. If melting the ice caps proves insufficient, another option might involve importing ice from comets or asteroids to supplement the planet's water resources. However, transforming Mars into a truly habitable world also requires the development of a sustainable biosphere capable of supporting human life. One promising avenue is the introduction of specially designed microorganisms and plants that can thrive in Martian conditions. These organisms could assist in converting carbon dioxide into oxygen and organic matter, slowly creating a self-sustaining ecosystem. In order to support their growth, it would also be necessary to develop suitable soil, potentially using Martian regolith as a medium for planting. As these microorganisms and plants establish themselves, they could gradually foster a more balanced and livable atmosphere on Mars, providing humanity with a foundation needed for long-term settlement on the red planet. The quest to terraform Mars is undeniably ambitious, but it offers a glimpse into humanity's potential to reshape the cosmos, making distant worlds more accessible and ultimately more livable. The challenge, however, is immense, one that will require not just scientific expertise, but also bold imagination and the unwavering determination to chart a course toward a new chapter in our exploration of the universe. Terraforming Mars is a monumental concept that continues to capture the imaginations of scientists, engineers, and dreamers alike. However, such an endeavor must be approached with caution, carefully weighing the long-term consequences of altering an entire planet. The ethical considerations surrounding the potential destruction of Martian ecosystems, or even life forms, are paramount. We must ask, how far can we push our technological capabilities without overstepping our moral obligations to preserve the intrinsic value of another world? The time frame required to terraform Mars is another complex factor. Estimates suggest that creating a habitable environment on the red planet would take centuries, possibly even millennia. This would demand sustained efforts, significant advancements in technology, and a deep commitment across generations. However, while these challenges are daunting, the very exploration of the idea ignites innovative thinking, pushing the boundaries of planetary science, sustainability, and humanity's broader role in the universe. Mars is but one frontier in a much larger narrative, the exploration of the cosmos. As our knowledge and technological capabilities advance, the idea of transforming a barren world into a thriving habitat becomes more than just a science fiction fantasy. It stands as an exciting prospect for the future of human exploration, a tangible step toward establishing a multi-planetary civilization. But terraforming Mars is just one piece of a far greater puzzle. The possibilities that lie in the realm of interstellar travel have long intrigued us. For decades, humanity has dreamed of venturing beyond the confines of our solar system, reaching stars that have only existed as points of light in the night sky. Despite the limits of current technology, there is hope. Emerging theories and innovative technologies present tantalizing possibilities for making interstellar travel a reality. Concepts that were once confined to the pages of science fiction novels are now being explored in the laboratories of physicists and engineers. One of the most promising ideas is fusion-powered propulsion. This technology, inspired by the energy-producing processes in stars, could provide the immense thrust necessary for long journeys to nearby star systems, such as Proxima Centauri or Alpha Centauri. Fusion propulsion would harness the energy released during nuclear fusion reactions, potentially providing continuous acceleration for an extended period, thus drastically cutting travel times compared to traditional chemical rockets. Proposals have already surfaced for spacecraft that could rely on this power source, significantly reducing the time it would take to reach distant stars. Then there's the concept of solar sails, also known as laser sails. These spacecraft would utilize massive reflective sails that are propelled by the pressure exerted by sunlight or powerful laser beams fired from Earth or space-based installations. While this technology is still in its infancy, With enough energy, a laser-powered sail could accelerate to a significant fraction of the speed of light, making it possible to travel across vast distances in space in a fraction of the time it would take using current methods. Projects such as the Breakthrough Starshot initiative are already pushing the boundaries of this concept, aiming to develop ultra-lightweight spacecraft that could, theoretically, reach nearby stars within a human lifetime. Beyond propulsion and sails, even more mind-bending concepts are on the table. Ideas like wormholes and warp drives, which have long been the stuff of speculative fiction. Wormholes, as theorized in the field of physics, could act as shortcuts through the fabric of spacetime itself, allowing for instantaneous travel between distant points in the universe. Similarly, a warp drive could manipulate spacetime, contracting it in front of the spacecraft and expanding it behind, enabling faster-than-light travel. While both concepts are still purely theoretical with no experimental evidence to support their existence, they remain a tantalizing possibility for the future. While we are still far from being able to travel to distant stars or terraform distant planets, the pursuit of these ambitious ideas serves a crucial purpose. They challenge us to think beyond our immediate boundaries, forcing us to ask what is possible, not just for our generation, but for the many that will follow. These theoretical technologies, though currently beyond our reach, are a testament to humanity's unrelenting desire to explore and push the limits of our understanding. As we continue to advance in science and technology, who knows what possibilities await us beyond the stars? Interstellar travel, a concept that has long captivated the imagination, presents an array of formidable challenges. While the development of efficient propulsion systems is critical, it is only one aspect of what is required to sustain human life on such a journey. Beyond the need for advanced propulsion, spacecraft must be equipped with life support systems capable of maintaining human health and well-being over long durations. Prolonged exposure to space poses risks like radiation, and these systems would need to protect crew members from such hazards. Furthermore, the psychosocial effects of extended isolation in the vast emptiness of space must also be considered, as the psychological toll of such an environment can have profound effects on the crew's mental health. The question of propulsion technology itself is an even more daunting issue. To reach distant star systems within a human lifetime, we would need to achieve speeds that are far beyond the capabilities of current technology. With today's propulsion systems, space journeys to even the nearest stars could take decades or even centuries. This discrepancy between the enormous distances of space and our limited technological reach raises significant obstacles, not only from a scientific and engineering perspective, but also from the standpoint of humanity's long-term aspirations. As the dream of interstellar travel takes root in the collective imagination, it has catalyzed rapid advancements in science, engineering, and technology. But it also prompts deeper philosophical questions about humanity's place in the cosmos. What does it mean for our species to venture beyond our home planet? How does the pursuit of reaching other star systems reshape our understanding of life, existence, and our role in the universe? These inquiries drive the field forward as research in astrophysics, propulsion technologies, and space exploration continues to evolve. Despite the current limitations, the dream of interstellar travel remains a tantalizing possibility, inspiring future generations to break new boundaries and push the limits of human potential. The prospect of achieving interstellar travel also inspires a broader vision of advanced civilizations. What would it take for a civilization to achieve the energy capabilities necessary for such journeys? Theoretical models suggest that advanced civilizations might eventually harness the energy of entire stars or galaxies. These ideas often revolve around massive engineering projects designed to capture and manipulate energy on a scale that goes far beyond what we can currently comprehend. One of the most well-known concepts in this regard is the Kardashev scale, a classification system that categorizes civilizations based on their energy consumption. A Type 1 civilization uses all available energy resources on its home planet. A Type 2 civilization, on the other hand, would harness the energy of its star, perhaps through a structure called a Dyson sphere. And a Type 3 civilization would govern energy on the scale of an entire galaxy, manipulating cosmic forces in unimaginable ways. The The Dyson sphere, a concept proposed by physicist Freeman Dyson, represents one potential method for a Type II civilization to harness the power of a star. This hypothetical megastructure would enclose a star, capturing a significant portion of its emitted energy. There are several proposed designs for a Dyson sphere, from a solid shell encircling the star to a swarm of satellites or solar collectors orbiting it. While still purely theoretical, such a structure could provide the vast amounts of energy necessary to power immense technological projects or even enable interstellar travel, allowing a civilization to venture to far-off star systems. Another potential means of harnessing energy for a Type II civilization is through stellar mining. This idea involves extracting materials like hydrogen from stars, which could then be used for fusion power generation. Such energy would be nearly limitless, though reaching a star's core presents a number of serious challenges. Extreme temperatures, intense radiation, and the difficulty of surviving within such an environment make stellar mining a very low probability method at our current technological level. For a Type III civilization, the energy of an entire galaxy would be at its disposal. This could involve manipulating massive cosmic structures such as black holes or supermassive stars. One intriguing hypothesis proposes building a structure around a black hole, a Dyson net, to capture the immense gravitational energy these objects emit. Alternatively, a civilization could use gravitational slingshots or other methods to extract usable power from the intense gravitational fields that surround black holes. This idea extends beyond traditional space exploration, where spacefaring civilizations would be able to harvest energy from the very fabric of the universe itself, tapping into the forces that shape galaxies. In the search for interstellar travel and the exploration of advanced civilizations, we are confronted not only with enormous technical challenges, but also with the very limits of human imagination. As we continue to explore these ideas, it is clear that the future of space travel holds the potential for discoveries that could forever change our understanding of the cosmos and humanity's place within it. Advanced civilizations might one day harness the faint afterglow of the Big Bang, known as the cosmic microwave background (CMB) radiation, as a source of energy. While this radiation is incredibly diffuse, it represents a vast, untapped energy reservoir on a cosmic scale. If innovative technologies could be developed to capture and convert this energy into usable forms, it would open new frontiers in the search for sustainable power. Though these ideas remain theoretical, far beyond current human capabilities, they push the boundaries of our understanding in both physics and engineering. The exploration of how advanced civilizations could harness stellar and galactic energy invites deep reflection on the future of humanity and the potential for intelligent life beyond Earth. As our technologies advance, concepts like the Kardashev scale, used to measure the energy consumption of civilizations, continue to fuel our imagination. This scale stimulates thoughts about the enormous possibilities the universe holds, especially regarding extraterrestrial intelligence. Detecting such advanced alien civilizations is one of the most profound challenges in the fields of astrobiology and astrophysics. Several methods have been proposed to uncover signs of extraterrestrial intelligence, often focusing on the impact these civilizations may have on their environment. Here are some of the most notable approaches currently being explored. One of the most widely discussed strategies is the search for technosignatures, indicators of technology or industrial activity similar to our own. This could include the detection of radio signals, which have been a central focus of initiatives like the Search for Extraterrestrial Intelligence, SETI. Advanced civilizations might transmit intentional communications or produce unintended leakage signals from their technologies, such as radar transmissions, television broadcasts, or other electronic emissions. By scanning specific regions of the sky with radio telescopes, scientists aim to intercept such signals, hoping to detect patterns or emissions that could indicate intelligent origins. Another promising method involves searching for megastructures around distant stars, like the famous Dyson sphere. A Dyson sphere is a hypothetical structure designed to capture energy from a star on a massive scale, potentially generating significant thermal emissions that could be detected by infrared telescopes. If a star displays unusual brightness patterns or spectral signatures, it may signal the presence of such a structure. Space telescopes equipped with advanced observational capabilities can help identify these anomalies, which may point to extraterrestrial civilizations engineering vast cosmic projects. The study of exoplanets. The study of exoplanets is equally crucial in the quest for alien life. By analyzing the atmospheres of planets located within the habitable zones of their stars, scientists search for biosignatures and technosignatures, potential signs of life or industrial processes. Gases like oxygen or methane, especially in unusual concentrations, could indicate biological activity or even technology. Missions such as the James Webb Space Telescope, with its high-resolution spectroscopic data, will significantly contribute to this effort, offering deeper insights into the atmospheres of distant worlds. Additionally, scientists propose that examining large-scale cosmic phenomena, such as unusual astronomical events, could offer further clues to the existence of advanced civilizations. For instance, periodic or anomalous variations in the brightness of stars or strange gravitational patterns could indicate artificial manipulation of celestial bodies. Some hypotheses even extend to more exotic scenarios, such as searching for signals or transmissions emanating from neutron star collisions, events that might reflect the influence of advanced technology manipulating cosmic forces. In exploring these possibilities, we are not only expanding the scope of our understanding of what might be achievable for extraterrestrial civilizations, but we are also taking the first steps toward uncovering the mysteries of our own place in the vast universe. The quest to uncover artificial light emissions from distant regions of space introduces an entirely new frontier in the search for extraterrestrial life. Light pollution from advanced civilizations could stretch far beyond the confines of their home planets, potentially visible across vast interstellar distances. If detectable, significant light sources, such as bustling cities or massive power plants, might offer tantalizing clues about the presence of intelligent life elsewhere in the cosmos. The idea of identifying advanced alien civilizations remains speculative, but our ongoing efforts to explore extraterrestrial intelligence continue to evolve. Each method we employ, whether through the detection of electromagnetic signals or the observation of distant exoplanets, adds to our expanding knowledge of the universe. As technology advances and innovative techniques emerge, the future holds the promise of breakthroughs that could finally answer one of humanity's most profound questions. Are we truly alone in the vastness of space? In our own solar system, the moons of gas giants present an exciting possibility for future human settlement and exploration. Moons like Europa, Ganymede, and Titan are of particular interest due to their potential resources and possible habitability. While the challenges of colonizing these distant worlds are immense, theoretical strategies exist that could pave the way for human presence beyond Earth. One of the primary challenges is securing resources for survival and construction. For example, Europa, one of Jupiter's most intriguing moons, is believed to have a subsurface ocean beneath its icy crust. If we can find a way to access this water, it could provide vital sustenance for human life, along with hydrogen and oxygen for fuel and life support systems. Melting or drilling through Europa's thick ice to reach this hidden ocean would be a monumental first step. Similarly, Titan, Saturn's largest moon, holds vast lakes and rivers of liquid methane and ethane, compounds that could potentially serve as energy sources for future colonies. Harnessing these resources would be crucial for sustaining life on these moons, but the next phase would involve developing habitats capable of withstanding extreme environmental conditions. The surface of Europa, for example, can plunge to temperatures below -100 degrees Celsius, requiring insulated, resilient structures to ensure human safety. Building such habitats could involve a combination of local materials and prefabricated components sent from Earth. Inflatable habitats, as well as 3D printing technologies capable of using the moon's regolith to construct buildings, might provide the flexibility needed to adapt to these hostile environments. Transporting humans and supplies across the vast distances between Earth and the moons of the gas giants is another major hurdle. To make regular missions feasible, we would need highly efficient propulsion systems and potentially in-orbit refueling strategies to conserve fuel on long-duration journeys. Once in space, Establishing a reliable transportation network will be vital to ferry equipment, materials, and personnel between Earth and the moons. This infrastructure would also serve as the backbone for long-term settlement. Life support systems would need to be meticulously designed to recycle air, water, and waste, creating a self-sufficient ecosystem. Growing food in controlled environments, possibly using hydroponics or artificial lighting, could ensure a steady food supply without the constant need for resupply missions from Earth. However, such colonization efforts would also bring up profound social and ethical questions. What if microbial life exists on moons like Europa? How can we prevent contamination? And what frameworks must be put in place to protect these distant ecosystems? As we push the boundaries of space exploration, these challenges must be carefully navigated. But the potential rewards, harnessing resources from alien worlds and expanding humanity's reach beyond Earth, make it an exciting prospect. With continued advancements in technology and a deeper understanding of the gas giants' moons, the dream of human settlement on these distant worlds may one day become a reality. Looking beyond our own solar system, the next generation of space telescopes is poised to revolutionize our understanding of the universe. These ambitious projects are designed to complement and extend the capabilities of the James Webb Space Telescope. Their primary focus will be to unravel the mysteries of everything from distant galaxies to the elusive nature of dark matter and dark energy. One notable mission on the horizon is the Roman Space Telescope, set for launch in the mid-2020s. With a field of view roughly 100 times larger than that of the Hubble Space Telescope, this telescope will allow astronomers to conduct wide-ranging surveys of the sky. Its primary objectives include studying dark energy, examining supernovae, and searching for exoplanets through techniques such as microlensing. Meanwhile, the European Space Agency's Euclid mission, scheduled to launch in the early 2020s, will create a three-dimensional map of the universe. By analyzing the distribution of galaxies across space and time, Euclid aims to shed light on the forces shaping the universe's expansion, particularly the enigmatic nature of dark energy and dark matter. Looking further into the future, two proposed missions, HabEx and LUVOIR, are among NASA's most exciting conceptual projects. HabEx, or the Habitable Exoplanet Observatory, seeks to detect and analyze the atmospheres of potentially habitable exoplanets orbiting nearby stars. Equipped with advanced coronagraph technology to block out starlight, HabEx will be able to detect the faint signals reflected from these planets, offering a glimpse into their potential for supporting life. The Large Ultraviolet Optical Infrared Surveyor, LUVOIR, on the other hand, would be a massive observatory capable of observing a broad range of cosmic phenomena, including exoplanet imaging, galaxy formation, and the evolution of the universe itself. Together, these next-generation telescopes will enable us to probe deeper into the cosmos, unlocking new insights that could fundamentally reshape our understanding of the universe and our place within it. In the vast expanse of space, concepts like the Origin Space Telescope are set to push the boundaries of what we can observe. Focusing on the formation of stars and galaxies, as well as the origins of life, this mission would enable us to peer into distant, cool, and unseen corners of the universe by observing in far infrared wavelengths. By doing so, the telescope promises to provide groundbreaking insights into the most remote astronomical objects, offering a view of the cosmos we've never had before. Each of these proposed missions is not just an extension of what we've already achieved with previous space telescopes, but also an evolution in technology. They are designed to tackle some of the most profound and complex questions in astrophysics, questions that go beyond our current capabilities. The next generation of space telescopes will not only enhance our understanding of the universe's vast history and the formation of celestial bodies, but will also deepen our understanding of the potential for life beyond Earth. This quest to unravel the cosmic mysteries is inspiring a new generation of astronomers, scientists, and explorers, all eager to discover what lies beyond our home planet. Meanwhile, our own survival on Earth is also at stake from potential cosmic threats. The possibility of a hazardous asteroid hurtling toward Earth is a concern that has caught the attention of planetary defense experts. To address this looming danger, a variety of strategies have been proposed, each aimed at altering the asteroid's trajectory just enough to avoid a catastrophic collision. Among the most discussed techniques is the kinetic impactor method. This strategy involves sending a spacecraft on a high-speed collision course with the asteroid, transferring momentum and effectively changing its velocity. The idea is to intervene years ahead of a potential impact, ensuring that even a small change in the asteroid's path would prevent a collision. NASA's Double Asteroid Redirection Test, DART, mission is an active example of this technique. It aims to target the binary asteroid system, Didymos, to test how well this method can shift an asteroid's trajectory in a controlled environment. Another proposed method is the gravity tractor technique. Instead of relying on direct impact, this approach leverages the subtle gravitational pull of a spacecraft placed near the asteroid for an extended period. Over time, the gravitational attraction of the spacecraft would gradually alter the asteroid's orbit, offering a more controlled and gentle way to change its course. While this method could take years, if not decades, it has the potential to deflect smaller asteroids in a way that minimizes the risk of fragmenting them into multiple hazardous pieces. Finally, if the asteroid is particularly large or resistant to non-destructive methods, the use of nuclear devices may be considered. In this scenario, a nuclear explosion would be detonated near the asteroid, not impacting it directly, but instead creating a shockwave or vaporizing surface material to nudge the asteroid off course. While this could be an effective strategy in some cases, it comes with significant risks, particularly the possibility of fragmenting the asteroid, creating multiple debris pieces that could still threaten Earth. These efforts, each at the cutting edge of scientific exploration and technological development, reflect the growing recognition of the importance of planetary defense. As we venture further into space, the challenge of protecting our planet from external threats becomes increasingly critical. The solutions proposed to deflect these celestial dangers may be complex, but they highlight the ingenuity and resilience of human innovation in the face of global threats. In the vast expanse of space, innovative ideas are emerging to tackle some of the most daunting challenges we face, such as planetary defense and space exploration. One fascinating approach being studied to address the potential threat of hazardous asteroids is the use of solar sails or reflectors. These devices are designed to harness the immense energy of sunlight by deploying reflective materials. The concept is simple but elegant. As sunlight hits the reflective surface, it generates a small but continuous force through solar radiation. Over time, this subtle push could alter an asteroid's trajectory, gradually shifting its path away from Earth's orbit. However, this method does come with its own set of challenges. It requires considerable time to be effective, making it more suitable for dealing with distant threats rather than imminent ones. Still, the potential for such a strategy is clear, especially if we can detect these threats well in advance. Early detection and constant monitoring of near-Earth objects, NEOs, are paramount for effective planetary defense. To stay ahead of potential dangers, scientists advocate for a global network of telescopes and observation programs that can track these celestial bodies over extended periods. By spotting potential risks many years before they pose a threat, we can implement deflection strategies long before it's too late. These efforts could be vital for protecting our planet from the unpredictable and ever-changing environment of our solar system. While no single solution may be sufficient to defend Earth from a dangerous asteroid, a combination of advanced technologies and early detection efforts could significantly enhance our ability to safeguard the planet. By merging these two powerful tools, humanity could develop a robust defense system capable of mitigating risks from deep space. In another corner of space exploration, antimatter propulsion presents a tantalizing possibility for advancing human space travel. Antimatter is an exotic form of matter made up of particles that mirror the properties of ordinary matter, but with opposite charges. When antimatter comes into contact with regular matter, the two annihilate each other, releasing an extraordinary amount of energy. This annihilation process holds the potential to fuel spacecraft with an energy density far beyond what current propulsion systems can achieve. Einstein's famous equation, E = c², reveals the staggering energy output that could be harnessed from antimatter. For instance, just 1 gram of antimatter combined with 1 gram of matter can produce around 100 billion joules of energy, the equivalent of a small nuclear bomb. Such an immense release of energy could make antimatter-based propulsion a game changer for space travel, offering propulsion systems far more efficient than conventional chemical rockets or even nuclear fission. One promising application is antimatter-catalyzed propulsion. In this concept, antimatter is used to trigger reactions in traditional propellants, greatly enhancing thrust and efficiency. This approach could provide the necessary energy for deep space missions while using relatively small amounts of antimatter. Even more exciting is the idea of antimatter-based rockets, where the energy from annihilation could be converted directly into thrust. This could be achieved by using the gamma radiation from the annihilation, or by creating high-energy plasma that is expelled to generate thrust. Despite its immense potential, the use of antimatter as a practical fuel source for spacecraft faces considerable hurdles. The production of antimatter is extremely energy-intensive, requiring vast amounts of conventional energy. In fact, producing just a tiny fraction of a gram of antimatter can consume more energy than most countries use in a year. Additionally, antimatter must be stored and handled with great care to prevent it from coming into contact with regular matter. The storage process presents significant engineering challenges, as antimatter must be kept in a containment field to avoid catastrophic annihilation events. Moreover, there are significant safety concerns. The annihilation process not only releases energy, but also produces high levels of radiation, which would require extensive protective measures, especially for crewed missions. These safety protocols would be critical, as mishandling antimatter could lead to devastating consequences. While antimatter propulsion offers promising possibilities for deep space exploration, it is not without its challenges. The technical, logistical, and safety issues currently limit its practical application. However, as research continues and technology advances, antimatter could one day play a pivotal role in humanity's journey through the cosmos, unlocking new pathways for exploration and perhaps even paving the way for interstellar travel. Building and maintaining habitats in the harsh environment of space is another formidable challenge. Space presents extreme temperatures, high levels of radiation, microgravity, and the need for life support systems, each requiring innovative solutions. As we push the boundaries of space exploration, we must find ways to protect astronauts and create sustainable environments for long-term missions. Together, these advances in planetary defense and space exploration technologies not only push the limits of what is possible, but also bring us closer to a future where humanity can thrive beyond Earth, safely exploring and colonizing new worlds. In the race to establish sustainable living environments for the future of space exploration, from the Moon to Mars and beyond, a series of innovative strategies and technologies are being developed. One of the most pressing concerns for space habitat design is radiation protection. Space is not a quiet, empty void, but a vast expanse teeming with high-energy particles and cosmic rays, which pose serious health risks to astronauts. To counteract these dangers, scientists and engineers are looking to create habitats that can shield occupants from harmful radiation. One promising solution is the use of thick shielding materials. For instance, regolith, the layer of loose, fragmented material covering planetary surfaces, and water are particularly effective at absorbing radiation. On celestial bodies like the Moon or Mars, using local materials for construction offers a sustainable way to provide this vital protection, significantly reducing the need to transport bulky materials from Earth. In addition to these shielding materials, another approach gaining traction is building habitats underground or within lava tubes. These natural formations, found both on Mars and the Moon, provide an effective barrier against radiation and micrometeorite impacts. They also help maintain a stable internal temperature, creating a more comfortable environment for humans. Beyond the physical structure, life support systems are essential to sustaining life on other planets. These systems will need to provide air, water, and food, which are critical for long-term survival. Sustainability becomes even more vital when considering the limited resources available on distant worlds. To address this, closed-loop systems, which recycle air and water, will be crucial. Advanced technologies such as regenerative life support systems can treat and purify wastewater, convert carbon dioxide into breathable oxygen, and manage waste effectively. Biological systems could also play a key role, with plants helping to produce oxygen, filter air, and recycle nutrients. Growing food in space is another monumental challenge, yet it opens up exciting new possibilities for astronauts. Techniques like hydroponics and aeroponics, which allow crops to grow without soil, are being explored as potential solutions. These systems require minimal water and space, which are invaluable in the limited confines of a spacecraft or lunar habitat. Vertical farming, utilizing energy-efficient LED lighting for plant growth, is also being investigated to maximize food production within these compact environments. With these technologies, astronauts could cultivate their own food, reducing reliance on Earthbound supplies and enabling more extended missions in space. The future of space exploration hinges not just on our ability to travel beyond Earth, but on our capacity to create self-sustaining, resilient habitats. From radiation protection and life support systems to food production and construction methods, every aspect of habitat design must work in harmony to support human life in the harsh conditions of space. In the pursuit of long-term human habitation in space, the importance of maintaining a habitat's structural integrity and functionality cannot be overstated. Regular maintenance protocols, along with robust monitoring systems, are essential for ensuring the safety and sustainability of these environments. To ensure this, redundancy in critical systems will be vital. These strategies will help guarantee the longevity of human life in space, mitigating risks and enhancing operational stability. Teleoperated and autonomous robots are pivotal in this regard. These robots would assist astronauts in performing routine repairs and maintenance tasks, reducing the need for spacewalks. Spacewalks are not only perilous, but also expose astronauts to the harsh and unforgiving conditions of space, increasing the risk to human life. By deploying robots, we can minimize these risks, ensuring astronauts remain safe while keeping habitats in optimal condition. Equally important is the psychological and social well-being of astronauts. Living in confined spaces for extended periods can have profound effects on mental health. Therefore, habitat designs must account for privacy, social interaction, and recreational spaces. Providing areas for personal solitude as well as communal spaces for interaction helps to maintain a healthy psychological state. Additionally, incorporating virtual reality and telecommunications systems will allow astronauts to stay connected with Earth, alleviating feelings of isolation and fostering a positive living environment. These technological innovations ensure that the emotional and mental health of astronauts is not overlooked. Building and maintaining space habitats is an ongoing challenge that requires innovative engineering, sustainable practices, and a deep understanding of the psychological needs of the inhabitants. As technology advances, so too does our capacity to meet these challenges. The dream of sustainable life beyond Earth is no longer a distant fantasy. It is steadily becoming a tangible reality. With each breakthrough, we pave the way for humanity's future in space. One of the most critical obstacles in long-duration space flights is the creation of artificial gravity. Prolonged exposure to microgravity leads to a range of health issues, including muscle atrophy and bone density loss. To combat these, scientists and engineers have proposed several methods to simulate gravity in spacecraft. One of the most widely discussed techniques is rotational or centripetal acceleration, a method grounded in the principle of centrifugal force. In this approach, a rotating spacecraft creates a sensation of gravity for the occupants. The design typically involves a large wheel or cylinder that spins, with occupants experiencing artificial gravity along its outer surface. The rate of rotation and the radius of the spacecraft's spin determine the strength of artificial gravity experienced. This concept, while often seen in science fiction, is a promising area of research. As our understanding of space engineering deepens, this method could become a practical solution for long-duration missions. Another proposed method involves linear acceleration. In this scenario, a spacecraft continuously accelerates in a straight line, creating a force akin to gravity. By maintaining a constant acceleration, astronauts would experience a sensation similar to gravitational pull. However, this method is highly dependent on a propulsion system capable of providing sustained thrust. Current propulsion technology, while improving, is still limited in terms of efficiency and power output, making this approach challenging, especially over long distances. In addition to these methods, alternative concepts such as magnetic levitation and electrostatic forces are being explored. These innovative systems would apply forces to objects or astronauts inside the spacecraft, simulating the effects of gravity. While these methods are still in the early stages of research, they represent a fascinating avenue for future space travel technology. Ultimately, the road to creating sustainable, long-term human habitation in space is paved with both technological and human-centered innovations. As research continues and our understanding of space and engineering deepens, humanity's dream of living beyond Earth is increasingly within reach. In the quest for sustaining human life on long-duration space missions, one of the most intriguing concepts under investigation is the creation of artificial gravity. While several methods have been proposed, many of them remain in the realm of theoretical research and have yet to be rigorously tested for practical applications. The challenge is monumental. How do we simulate the gravitational force that Earth's environment provides when astronauts are in the vast, weightless expanse of space? One promising approach is the concept of intermittent gravity, which could revolutionize how we think about life aboard spacecraft. This strategy suggests that astronauts could alternate between periods of artificial gravity and microgravity. For example, they might spend a portion of their time in environments designed to simulate gravity, while at other times they would experience microgravity to perform specific tasks. This alternating system could potentially alleviate some of the detrimental effects of prolonged exposure to weightlessness, such as muscle atrophy and bone density loss. During artificial gravity periods, astronauts could engage in vital physical activities, preserving their muscles and maintaining their overall health. While these ideas are undoubtedly exciting, the path to their implementation is far from simple. The development of artificial gravity in any form demands not only cutting-edge engineering and technological breakthroughs, but also a deep understanding of the physical, psychological, and logistical challenges that come with space travel. The creation of such environments will require a complete rethinking of spacecraft design, everything from how the ship is built to the way it functions on long-term missions. And with destinations like Mars and beyond on the horizon, these challenges become even more critical. As we continue to push the boundaries of space exploration, the importance of artificial gravity solutions cannot be overstated. They hold the key to preserving astronaut health and performance, ensuring that humanity can embark on interplanetary journeys with the best chances of success. But the road to implementation will require decades of rigorous testing, design, and iteration. If we are to truly unlock the potential of space travel, we must address not only the technology, but also the impacts on the human body and mind. In closing, as we look to the stars and envision the future of human exploration in the cosmos, we can't help but feel a sense of awe. From the infinitesimal particles that shape the fabric of the universe to the vast interconnected structures that stretch across galaxies, we have only scratched the surface of what lies ahead. The mysteries of space, from the familiar planets in our own solar system to the farthest reaches of the universe, beckon us to explore, learn, and expand our understanding of the cosmos. The journey has only just begun.